Yeah, by all means.
Okay, so welcome everyone to the afternoon session. So we have 3 talks lined up for this session. The first talk is by Bindusar Sahoo from IIT Roorkee, and he'll be speaking on rudiments of N equal to 3 supergravity in 4 dimensions. Okay, so over to you, Bindusar.
Okay, thank you, Bobby, and thank you, Alok and all the organizers of ISM 2021 to give me an opportunity to speak, and also for arranging this nice online meeting. Okay, yeah, it's nice to meet you all online, although we would at some point like to meet also physically. Okay, so today I'm going to speak about rudiments of N equal to 3 conformal supergravity. Okay, so there is 2 parts up to this. First is N equal to 3, and then conformal supergravity. So let me first tell you why do we need to worry about N equal to 3 supergravity. Okay, so I mean, it's quite well known that if you take a non-gravitational CPT invariant N equal to 3 supersymmetric theory, then there is always a 4th supersymmetry, and the theory becomes N equal to 4. So I mean, so there is no genuine CPT invariant pure N equal to 3 theory. So if you take any CPT invariant N equal to 3 theory, it's always N equal to 4. And this can be understood by analyzing the representation of the N equal to 3 supersymmetry algebra. In particular, if you look at the multiplet of massless states with maximal spin 1, and if you add the CPT conjugate, you always get a representation of N equal to 4 supersymmetry. Okay, and this means that the N equal to 3 vector multiplet is the same as N equal to 4 vector multiplet. And however, once you have gravity in the picture, this is no longer true. Okay, and in fact, the massless representation of N equal to 3 supersymmetry algebra with maximal spin 2 is different from N equal to 4. Okay, although one cannot have a genuine CPT invariant N equal to 3 supersymmetric field theory Lagrangian, there have been some studies on this so-called pure N equal to 3 superconformal field theories using techniques from holography, and these are some of the reference. So this reference by Aharoni and FTKF from 2015, they basically assume that suppose there is a pure N equal to 3 theory, so what would be its so-called properties? And these people in this paper in 2015, they explicitly constructed a N equal to 3 superconformal field theory, and which satisfied also all the properties that was discussed in Aharoni's paper. And as expected, these do not have a Lagrangian, so these are kind of non-Lagrangian theories. Hence, study of N equal to 3 supergravity is important if you want to understand the holographic dual of such theories. And there have been work going on in this direction. So N equal to 3 supergravity has been understood from a different perspective, the so-called group manifold approach. And yeah, there was a paper in the early 80s by Castelloni and his collaborators, who looked at matter-coupled N equal to 3 supergravity theory from this group manifold approach. So why do we need to worry about this conformal supergravity approach is the following. So so why do we need to worry about conformal supergravity? Because conformal supergravity plays a vital role in the construction of these matter-coupled supergravity theories with higher derivative corrections. So in the other approaches, in the group manifold approach, it's hard to construct high derivative corrections in a systematic manner, and conformal supergravity gives us a nice framework to construct these supergravity theories with higher derivative corrections. And if you want to also learn about ADS-CFT correspondence, where the supergravity has high derivative corrections, we would like to construct such supergravity theories with high derivative corrections, and therefore we worry about conformal supergravity. Okay, and why is that? I mean, because essentially conformal supergravity has more symmetries, and so this large high degrees of symmetries, this allows the degrees of freedom to be arranged in shorter multiplets, and this makes the problem of constructing matter-coupled supergravity theories, including high derivative corrections, quite tractable. And finally, one can use some of these matter multiplets as compensators to gauge fixed additional symmetries to go from conformal supergravity to the physical Poincare supergravity. So there is a systematic procedure to do this. And in the pre-learn session, I think Madhu talked about some of these techniques called superconformal multiplet calculus. Okay, so I will briefly discuss about them. Okay, so so basically, conformal supergravity, has this gauge equivalence program. I mean, you can think of conformal supergravity as a gauge theory. Okay, so what you do is you essentially start with, if you are interested in any extended conformal supergravity, you start with the gauge theory based on the superconformal algebra SU2,2/n. So SU2,2/n has a number of generators. In particular, if you're interested in n equal to 3, these are the generators of SU2,2/3 algebra. So this is a local translation. This is local Lorentz transformation. This is a spatial conformal transformation. This is dilatation, and there are two R symmetries, U1 and SU3. And there is one ordinary supersymmetry, and there is a spatial supersymmetry because it's a superconformal algebra. So there is a spatial supersymmetry. And corresponding to all these generators, you have a bunch of gauge fields and field strengths. Okay, so this is the gauge theory. And as Madhu discussed earlier, so in order to convert this gauge theory into a theory of gravity, we need to impose some constraints on the curvature. So for example, we need to impose this constraint that the curvature associated with the local translation has to be set to 0. So that basically converts the local translation into a general coordinate transformation. Okay, and because we are in a superconformal theory, so we need some additional constraints also. And these constraints essentially make some of these fields dependent. So for example, this constraint will make this 𝗰𝗵𝗶𝗿 dependent on 𝗰𝗵𝗶 and other fields. Okay, and you can interpret, you will get the standard interpretation of this as a spin connection and this as a Weyl-bind, which we want in a supergravity theory. And this constraint will make this gauge field corresponding to spatial conformal transformation also dependent. And this constraint will make the gauge field corresponding to the S supersymmetry dependent. Once you do this, you count the number of degrees of freedom, you will see that the bosonic and fermionic degrees of freedom are not matching if you have n greater than 1. And therefore, you need to complete the field representation by adding additional auxiliary fields. And you have to accordingly also modify the superconformal algebra. And in this modified superconformal algebra, the structure constants actually becomes field dependent and they become structure functions. Such superconformal algebra are known in the literature as soft superconformal algebra. And in this whole procedure, the multiplet that you have obtained, which basically includes these gauge fields and the additional auxiliary fields, that they are known as the Weyl multiplet. Okay. Now we'll discuss about n equal to 3 Weyl multiplet. Because to understand n equal to 3 conformal supergravity, you need the n equal to 3 Weyl multiplet. So as we discussed, we need some additional auxiliary fields to close the Weyl multiplet. And typically, these additional auxiliary fields are found by the so-called current multiplet method, wherein you find the current multiplet for a rigid multiplet, for example, the vector multiplet. Okay. And this current multiplet couples to the linearized Weyl multiplet. And therefore, the components of the current multiplet and the transformation loss gives us the linearized Weyl multiplet along with the auxiliary field content. Okay.
I have a question.
Yes.
Does this Weyl multiplet have a superfield representation? Can it be derived from some D term of some?
Exactly. You can write a superfield representation. In n equal to 2, it is very easy to write. It's basically a chiral superfield. For n greater than 2, it is a little bit complicated, but you can do that. Okay. But we will work in the component method. We will not go to the superfield. Okay, so yeah, so in this way you will obtain the linearized Weyl multiplet along with the auxiliary field content, and then you just have to run the crank and complete the full nonlinear transformation of the Weyl multiplet and the superconformal algebra. Yeah, so that is the technical part. But this is the current multiplet approach is the way to construct this Weyl multiplet. However, as we have discussed earlier, in n equal to 3. There is no genuine vector multiplet, which is a different vector multiplet. Like as I said, the n equal to 3 vector multiplet is the same as n equal to 4 vector multiplet. And therefore, if you take a rigid n equal to 3 vector multiplet and try to obtain its current multiplet, you will get the same current multiplet as n equal to 4. And therefore, if you couple it to some linearized Weyl multiplet, it will be the n equal to 4 Weyl multiplet. Okay, so it doesn't help to construct the n equal to 3 Weyl multiplet. However, in 2017, Van Proijn and Van Muyden, they found a way to overcome this hurdle. So what they did is, instead of constructing the n equal to 3 current multiplet from an n equal to 3 rigid vector multiplet, they truncated the n equal to 4 current multiplet directly to n equal to 3. And in this way, they obtained the n equal to 3 while multiplet. Okay. And these are the field contents of the n equal to 3 while multiplet. So these are the gauge fields that we had discussed earlier. This is the Weyl-Bind. This is the gauge field corresponding to dilatation. This is the gauge field corresponding to the SU3R symmetry and U1R symmetry. And these are the auxiliary fields that we need. These are the bosonic auxiliary fields. And these are the fermionic auxiliary fields. And this is the gravity. Okay, and these are the dependent gauge fields as we had discussed earlier. So this is the n equal to 3 while multiplet that was constructed by these people in 2017. Okay. Yeah. So after we have obtained the n equal to 3 while multiplet, the next step is to obtain an action for this while multiplet. So we are interested in this n equal to 3 conformal supergravity action for the while multiplet. Okay, and so now I'm going to discuss how to construct this action. And this is from our recent paper with Loganayagam and Madhu. Yeah. So in order to construct actions in conformal supergravity, one often resorts to well-known density formula. And this is something also Madhu has discussed in the pre-learn session. So density formula are invariant action given in terms of some simple multiplet. For example, in n equal to 2, conformal supergravity, one has chiral density formula. And this is even in terms of chiral multiplet, or you can have a linear vector density formula given in terms of a linear and vector multiplet. So chiral density formula is very simple because in n equal to 2 chiral multiplet, if you see, the highest component of the chiral multiplet under supersymmetry transforms into a total derivative. Okay, and therefore, if you write down a Lagrangian density, which is just proportional to the highest component of this chiral multiplet, you get an invariant action. Now, this is in rigid supersymmetry. If you have supergravity, you just need to add terms, systematically add terms proportional to gravity, to make it invariant. And this has been done, and this gives us a well-known chiral density formula. And same with the linear and vector multiplet also. And once you have this density formula in terms of these multiplets, and you want to construct invariant actions in n equal to 2 conformal supergravity, for example, invariant action for the while multiplet, what you need to do is basically you need to write down a chiral multiplet whose components are basically composite expressions of the while multiplet or the vector multiplet, right? And once you do that and you basically substitute this embedding in the chiral density formula, you get an action for the while multiplet or the vector multiplet. So this is a standard approach that was followed for n equal to 2. But this approach kind of breaks down for n greater than 2 because this chiral density formula does not have a nice generalization to n greater than 2. Yeah. So in order to overcome this hurdle, earlier in our study of n equal to 4 conformal supergravity, as mentioned in these papers, we found an action principle based on something called the method of superforms, which can be used to construct density formula. So we don't really rely on some well-known density formula. We can actually construct density formula based on this action principle. And from this density formula, we can construct invariant actions. So we started this method for n equal to 4. Okay, but this method can be applied to any supergravity theories. So not only for n equal to 4, we also found its application in n equal to 2. So in this paper with Loganayagam, we found new density formula in n equal to 2 and new actions in n equal to 2. So which are not constructed from a chiral density formula or a linear vector density formula.
I have another question.
Yes.
So if you have the superfield formulation for while n equal to 3 while multiplet, why can't you simply directly construct the action by taking the d term, by taking some...
It's not, as I said, first of all, for n equal to 3 is a very recent thing. I don't think anybody has found, I think n equal to 3, supergravity is known in kind of harmonic superspace.
Yeah.
It's a bit complicated. It's not like n equal to 1 and n equal to 2 where you just take the d term and get the action. It's a little bit more complicated than that. I mean, eventually, people have studied n equal to 4 in conformal superspace, but nobody had n equal to 4 conformal superspace, nobody had studied. N equal to 2 people have studied in superspace language. N equal to 4 is n equal to 3 and n equal to 4. These are not as straightforward as n equal to 1 and n equal to 2. So it is not like taking the, I mean, in n equal to 4, of course, the superfield formulation is known, but n equal to 3 is not known. I mean, it's just started. I mean, 2017 only the Weil multiplet was constructed.
But can't you get down from the n equal to 4 formulation to the n equal to 3 formulation as you were talking about?
Yes, we can do that. And in fact, yeah, we can do that. But it's not, as I said, n equal to 4 also, the superfield formulation is not very straightforward. I mean, we cannot write down an action in superfield formulation. I mean, the action that we wrote down in this paper, we had to resort to component methods. In superspace, maybe it's possible, but it's not known till now.
Okay.
Okay. Right. So this action principle actually follows from a very simple observation in differential geometry. So this is the principle. Let me explain it using the language of differential geometry. So consider a d-dimensional manifold curly M. Okay, it's a larger manifold. This capital D is a larger manifold, and in that manifold you have a small d-dimensional submanifold M. Okay, and let us consider the integral of a D form on this submanifold. So you consider this integral on this submanifold. Okay, J is a D form, and you are considering this integral on this submanifold. And under arbitrary diffeomorphism in M, so under arbitrary diffeomorphism in this larger manifold, this D form transforms as a Lie derivative. So this is the transformation of this D form. And as we know, Lie derivative is just the anti-commutator of the exterior derivative and the interior product, and that's what it is. Okay. So if this action has to be invariant under arbitrary diffeomorphism in M, okay. I mean, this action, just by being a D form in M, it is already invariant under arbitrary diffeomorphism on M. But if we want this to be invariant under arbitrary diffeomorphism in this larger manifold, then it is clear from here that dj has to be 0, because the transformation of j has a total derivative piece. So if this manifold is has no boundaries, or even if it has boundary and a nice fall of condition for the fields, this will eventually go away. But to make this 0, you need dj to be equal to 0. Okay, so this action would be invariant under the full diffeomorphism on this M if dj is equal to 0. Okay, that's what I've written here. So if you require the invariance action of the action under arbitrary diffeomorphism in this larger manifold, you would require dj to be 0. So that is j to be a closed form. Okay. So now we would be interested in the case where the submanifold M is actually the full space-time manifold, and this larger manifold is a manifold where some gauge symmetries have been geometrized. Okay. So in this formalism, if you are able to construct this action integral, which is also gauge invariant, so now gauge transformation becomes a diffeomorphism in the larger manifold, right? Because you have geometrized these gauge symmetries. So ensuring gauge invariance of this action would basically mean ensuring diffeomorphism invariance of this action in the larger manifold, and which basically boils down to finding a closed form J in the larger manifold where you have geometrized this gauge symmetries.
One question. Sorry to interrupt. This formalism of this action principle, it seems quite general. So the chiral density formula for n equal to 2, that cannot be derived from this.
Yes. That can be derived from this. That can be very easily derived from this action principle. Yeah.
Okay. And you can derive other density formulas apart from the chiral one.
Exactly. So it can already derive the already well-known density formula. Other than that, it gives us a framework to derive more general density formula and hence more general actions.
Yeah. But those will all be like independent density formulas, or
yes, they would all be like independent density formula. Yeah.
Okay. Thank you.
Okay. So now, So basically, as I said, if for constructing gauge invariant actions, you need to geometrize these gauge symmetries, and you need to find a D form J which satisfies the closure condition. And in particular, for constructing supergravity action, supergravity is also a gauge theory, you need to geometrize supersymmetry and impose the closure condition. Okay. So what you need to do is basically you need to start with the larger manifold where supersymmetry has been geometrized. Okay, so these are the coordinates of your larger manifold N. Okay, so the x mu are the coordinates of this smaller manifold, which is the space-time manifold, and these are the extra coordinates that you add to geometrize supersymmetry. And the super Wielbein one forms of this larger manifold are this basically. Okay, so these are one forms basically in the larger manifold. So it has legs not only along the space-time direction but also along the theta direction. Okay, so however, I mean, if you truncate it to the space-time manifold, then these are your standard Wielbein and standard gravity now. Okay, so what you now need to do is you need to construct a fourth form, okay, which satisfies the closure condition. Okay, as if you can find such a fourth form, then this action integral evaluated on the space-time manifold would be invariant under supersymmetry. Okay, so this is what we need to do. However, as we had discussed in superconformal gravity, apart from supersymmetry, there are a bunch of other gauge symmetries, like S supersymmetry, local Lorentz transformation, R symmetries, etc., etc. But these symmetries are very easier to realize. They are not like the ordinary Q supersymmetry, which is harder to realize. These symmetries are easier to realize. So we will not geometrize these symmetries to find invariance under those symmetries. So we will only geometrize the Q supersymmetry, and the other symmetries we will ensure that they are invariant by explicitly demanding that this fourth form that we are constructing is manifestly invariant under these symmetries. Okay, so therefore the action becomes manifestly invariant under these other symmetries, and the invariance under the Q supersymmetry is realized by ensuring its closure condition. But now, since J is manifestly invariant under the other symmetries, the closure condition, I can replace it by this covariant closure condition, where this covariant exterior derivative is covariant with respect to the other gauge symmetries. Okay, because J is manifestly invariant under those symmetries, so dJ is the same as nabla J, and so we can instead demand nabla J equal to 0. I mean, the reason why we are doing this is because it gives a nice systematic way to carry out our work. Otherwise, this is the same as dJ is equal to 0. Okay, so now, and then we need to take an answer. So since it is a fourth form, okay, we expand it as wedge products of the super Wielbein one form. So I have not written the wedge products explicitly, but there is a wedge product in between these one forms. Okay, so these are our super Wielbein one forms, and our super Wielbein one forms are basically this Wielbein one form and the gravity no one form. And now when I expand it out, I have this whole bunch of terms with 4 gravity no, with 3 gravity no, and 1 Wielbein, 2 Wielbein, 2 gravity no, and so on. Okay, so this is our answer, and we need to find a J such that it satisfies this covariant closure condition. Okay,
I have a question.
Yes.
These super Wielbeins are superfields, right? They are superfield constructed out of the EAs and the Xis, right?
Exactly. So in the larger manifold, where we have geometrized supersymmetry, I mean, you can think of that larger manifold as a superspace. So the super Wielbeins are basically superfields. Okay, so these are all superfields. So these take values in the larger manifold where we have geometrized supersymmetry. Okay, but when we actually construct the action, we are writing down the integral of this fourth form on the space-time manifold. So when we truncate the super Wielbein on the space-time, they become the standard Wielbein and the gravity. Okay, so this.
So is the understanding that you take this G, DC, BA, EA, EB, EC, ED, and then you integrate over the thetas or something like that? No.
We are basically taking this. So
by the thetas, I mean the Grassmann.
No, we are not integrating over the super. So this is our action. So we are integrating this fourth form J on the space-time manifold. Okay, and our space-time manifold is basically defined as a larger manifold with this truncation, theta equal to d theta equal to 0.
No, what I'm worried about is, in general, you would have.
I think, please, can I suggest that we keep discussions for the discussion session? Because I think we have been, don't mind, but we have been running over time. So let's, only short questions, I think, should be allowed during talks.
Yeah, okay. We can discuss this in the discussion session. Yeah, you can ask me during that time. Yeah. So yeah. So this is the answers, and we need to impose this covariant closure condition. So we need to know how this covariant exterior derivative acts on all these objects that are appearing in the answers. Okay, we need to know how this covariant exterior derivative acts on this Villebine and the gravity in one form, and also on these objects JDCBA, which are basically super covariant objects. So these JDCBA are super covariant objects. Okay, so its action on the super Villebine is well known if you understand the Weil multiplet, because that is given by this super torsion 2 form. Okay, and this is this we know because we understand the Weil multiplet, and this is the result. This is the result for the action of the covariant exterior derivative on the Villebine 1 form and the gravity in 1 form. Okay, so these are given. So these are all 1 forms, and this exterior, this wedge product is implicit in these equations. Okay, and on the super covariant.
5 minutes.
Okay. And on the super, so there were some questions, so I maybe can take some extra time.
Yeah, sure.
Okay, so on the super covariant blocks, the covariant exterior derivatives acts like this. Okay, so so this is basically the super covariant derivative of this covariant object, and this is the delta alpha. This nabla alpha is the supersymmetry generator. So you can think of this part as a supersymmetry transformation of this object, where the supersymmetry parameter has been replaced by the gravity in 1 form. Okay, so that is essentially what this covariant, how this covariant derivative acts on the super covariant object JDCBA. Okay, and when you impose this nabla j equal to 0, this basically relates these different blocks appearing in that answers to each other via supersymmetry, and also imposes some constraints. Okay, so and this actually gives us this action integral. So you can think of this JDCBA, all these JDCBA, as some component of an abstract multiplet in terms of which we have this action. Okay, and these components are basically related to each other via supersymmetry, which is ensured by this closure condition, and also satisfies some constraints, which also come from this closure condition. And this is what we call as a density formula. Okay. Yeah. So in order to get an invariant action, basically you need to find these blocks JDCBA, which forms a component of an abstract multiplet in terms of the multiplet for which you want to find the action. For example, if you want to find the action for the Weil multiplet, you would need to find these objects in terms of the fields in the Weil multiplet. Okay. So in n equal to 3, so the answer is basically, the starting point of the answer is basically you have to tell what is the answers for this j, which comes with the maximum number of gravity. It turns out that for n equal to 3, the answers that comes with the maximum number of gravity needs to have this structure. Okay, where CMN, this is symmetric in M and N. These are my SU3 index. Okay, and then imposing this closure condition, you would find that the Cij needs to satisfy these conditions. So this basically tells that in the left supersymmetric transformation of this object Cij, there is nothing in transforming in the 15 of SU3. And this tells us that in the right supersymmetric transformation of Cij, there is nothing that transforms in the 10 of SU3. Okay. And now in order to find an action for the n equal to 3 Weil multiplet, we need to find a Cij in terms of the Weil multiplet fields that satisfies this constraint. Okay. And you take the Weil multiplet fields and try to find this composite expression. You find that the composite expression has this structure. Okay, with some overall constant which can be complex. Okay, and if you take alpha equal to 1, this leads to the supersymmetrization of the Pontryagin density, and if you take alpha equal to y, this leads to the supersymmetrization of the Weil square term. Okay, so in this way we can find the n equal to 3 conformal supergravity action, which is a linear combination of the Pontryagin density and the Weil square term, supersymmetrization of that. Okay, the action is quite big, so I'm not giving it here. Okay, but this is essentially what we find.
Bindusar, it's almost time, so maybe in 5 minutes or so.
Just some future directions. I will just finish.
Sure.
Okay, so what next? So next, in the next step, we would like to go from conformal supergravity to Poincare supergravity. So we have already seen the construction of conformal supergravity. Okay, so as we had discussed earlier, in order to go from conformal supergravity to Poincare supergravity, we need what are known as compensating multiplets. Okay, so these are the multiplets that you need to gauge fix the extra symmetries that are present in the in conformal supergravity. Okay, and also eliminate the auxiliary fields that we had in the while multiplet, and okay, then you go from conformal supergravity to Poincare supergravity. It turns out that in n equal to 3, you would need at least 3 vector multiplets to play the role of compensators. One can also add additional vector multiplets, which will play the role of matter multiplets in n equal to 3 Poincare supergravity. Okay, and now n equal to 3 vector multiplets and its coupling to conformal supergravity can be obtained systematically by truncating the n equal to 4 vector multiplet coupled to conformal supergravity that was obtained by Day-3 in 1984. Okay. I'm loosely using the word truncating here. It's not actually truncating. As I said earlier, n equal to 3 vector multiplet is the same as n equal to 4 vector multiplet. But by truncating, I'm basically saying that I'm rearranging the degrees of freedom. So the degrees of freedom are the same in n equal to 3 vector multiplet and n equal to 4 vector multiplet. So by truncating, I am basically rearranging the degrees of freedom of n equal to 4 vector multiplet to n equal to 3 vector multiplet. Okay. And just like n equal to 4 vector multiplet, the n equal to 3 vector multiplet is also an on-shell multiplet, meaning the commutator of supersymmetry transformation on the n equal to 3 vector multiplet does not close without using the equations of motion. So you have to use the equations of motion to close the algebra on n equal to 3 vector multiplet. It's just like n equal to 4 vector multiplet. And these equations of motion are you can also obtain by this systematic truncation of the n equal to, or rearrangement of the n equal to 4 vector multiplet. So all these things we have obtained already, and eventually one can obtain an action for this n equal to 3 vector multiplet by using this previously discussed density formula and the equations of motion. So we have to also use the equations of motion because the density formula is blind to the equations of motion. So it will give us action where the equations of motion has been eliminated. So terms proportional to the equations of motion has been eliminated. So we have to basically use the action constructed from the density formula and the equations of motion to construct the genuine action for n equal to 3 vector multiplet coupled to conformal supergravity. And this is actually a work in progress with Devanshu, Madhu, and Subramanya. And then we basically use this action for the vector multiplet to go from n equal to 3 conformal supergravity to Poincare supergravity. Yeah, so this is some work in progress. And apart from that, there are some other work that we would be interested in. You know, as I said, the prime motivation of studying n equal to 3 supergravity is ADS-CFT correspondence. So what we have discussed so far is the construction of ungauged supergravity. Whereas for ADS-CFT correspondence, you would like to have a gauged supergravity. That is what we would like to study. And there are some more directions related to the double copy. So maybe I can go through this if somebody asks question, but maybe since I'm run out of time, I can stop here. Thank you.
Okay, thank you. Any questions? Yeah.
Bobby, can I ask a small?
Yeah, sure. Ricardo wanted to ask a question, then maybe after that.
Yeah.
No, go ahead, Alok. I can ask later.
No, I just wanted Bindusar to say something about the double copy that you couldn't finish if you.
Yeah, sorry. Yeah. Yes. Yeah. So basically.
Actually, if it will take too much time, then we can have.
Okay, sure.
It will not take too much time.
Okay.
So basically, what has been shown for n equal to 0, 1, and 2, and 4 conformal supergravity by Johansson and his collaborators, is that there is a double copy structure for this n equal to 0, 1, and 2, and 4 supergravity.
Mm-hmm.
That structure is basically this. One copy of the gauge theory is this so-called df square min, and the other copy is this super Yang-Mills. Equal to 1, 0, 1, 2, 4 super Yang-Mills. So this df square is a gauge theory that is purely made out of dimension 6 operators in d equal to 6 counting. This is the Lagrangian for df square gauge theory. where you have some scalars in some representation of the gauge group. And this df square mean is basically just the kinetic term, nothing else. So if you have the df square mean in one of the gauge theory, then what you get is basically the conformal supergravity. If you replace the other one,
right. Okay, I see.
Yeah. So we would like to see this for n equal to 3 conformal supergravity also. But the point is that there is no n equal to 3 super Yang-Mills Lagrangian, as I had discussed, because you cannot have a genuine n equal to 3 super Yang-Mills Lagrangian. So whatever n equal to 3 Lagrangian you write down, it becomes n equal to 4. So all these n equal to 3 super conformal field theories has been understood from a non-Lagrangian point of view. So we really don't know how to address this question because we need, to understand this double copy, we need a Lagrangian. So
But the perturbative amplitudes you have computed in your conformal supergravity to 3 level, or
yeah, that can be computed. We have not computed. We have just written down the action. But Hansen and all these people have done for all these other conformal supergravity. Basically, they computed the amplitudes for this double copy.
Yes.
From the amplitude, they basically constructed the conformal supergravity action in some
right.
And they matched that with the conformal supergravity action.
Right. Yeah, it goes from the amplitude side. That's why I was asking. Yeah. Thank you. I think. Yeah.
Rito, you have.
Whether I've understood correctly that I want. So in the last part, you commented that in writing down the n equal to 3 action, we didn't have to impose the equation of motion, right?
Vector multiplet. Yes.
Yeah. But like when you are writing S as integral of J over N, you are using the fact that J is a closed form, right? So
Right. So J will be a closed form. So as I said, so we have to impose this nabla J equal to 0. So when we actually do that, so this this J, the J had various blocks, right? This J, D, C, B, A.
Yeah.
So when we impose this nabla J equal to 0, this various blocks gets related to each other by supersymmetry, and also there are some constraints that are imposed on these blocks. Okay, so typically, if you ensure only a preliminary set of constraints, then the other constraints are satisfied just by demand if the supersymmetry algebra is closed. Okay, but if you have an on-shell multiplet, the supersymmetry algebra is closed on this on-shell multiplet up to equations of motion. So what I'm saying is, because of this, so the action that you will construct from the density formula will be blind to the equations of motion. So they will be proportional to the equations of motion that the action will simply eliminate from your.
Okay.
If there are some terms proportional to equation of motion in the action which should be there, this action principle will not basically show that to us. Okay, so we basically therefore reconstruct those terms by using the equations of motion.
Okay, since they are like these constants are related by the supersymmetry, that's why this happens. Since this nabla J equal to 0 condition, you said it relates by supersymmetry different constants, the different blocks of J. So that is what helps in this fact, right? If I understood correctly.
Yeah.
You don't need.
Yeah. So
sir, maybe we can continue this discussion because I think we're already 8 minutes late.
Okay.
And I think there's a question by 𝗰𝗶𝗶𝗫, but if it's okay, we could just do that in the discussion as well.
Sure.
Okay, thank you, Bindusar. So the next speaker is thanks a lot. The next speaker is Suresh Govindarajan from IIT Chennai, and he'll be telling us about Lie algebras from Umbral Moonshine. So Suresh, yeah. Suresh, you're muted, I think.
Now, can you hear me?
Yeah, but
yeah, I'll share my screen again. No, you lose track of some things then.
Yeah.
Okay. Now, can you see my screen?
Yes.
Okay. Thank you, Bobby. And I would like to thank the organizing committee as well as Alok and the rest of the team at IIT Roorkee for this invitation to speak here. And I'm going to talk about Lie algebras from Umbral Moonshine. And So the plan of the talk is as follows. I'll give an introduction where I'll just state the problem we are trying to address. And then I'll give a practical introduction to BKM's Lie superalgebras, and then get to the meat of our work, which first, this is about embedding affine SL2 hat into a bunch of Lie algebras and how they lead to vector valued modular forms. And then we'll go beyond vector valued modular forms and I'll conclude. So let's start with the introduction. And the introduction is that in this talk, we'll focus on a family of 5 Siegel modular forms. Okay, they're parameterized by a positive integer n, which takes only 5 values, 1, 2, 3, 4, and 6. And of weight k, f k of n is given by this formula. And I just want you to remember that for n equal to 6, the weight is 0. Okay, and these are modular forms of a paramodular group at paramodular level n. So this positive integer n, decides a group, and that group we'll call it gamma n, and it's a subgroup of sp4q. So q is rationals, and if you look at the entries here, stars correspond to positive to integers, and n is of course, but you can see here in red I've given you an n inverse, so you can see that there is an entry which is rational. Okay, so this forms a group, and if you put n equal to 1, you end up with sp4z, the usual genus2 symplectic group, but this is a natural generalization of that. And then if you given any such modular form, it will have a Fourier Jacobi expansion, and the coefficients here. So the thing is that, so let me explain first what z is. Z is a point in upper half space, so it has 3 coordinates, tau, z, and tau prime. And we will so tau prime, in the limit where tau prime goes to I infinity, this quantity s, which is e power 2 pi I prime, tau prime goes to 0, and you get an expansion, and all the coefficients are Jacobi forms, okay, of suitable index. This is just something you can remember. And so the proposition or the idea is that the 5 Siegel modular forms are the denominator formula for suitable extensions of the Cox-Moody Lie algebra G of an constructed from rank 3 Cartan matrices an. Okay, I have to tell you all these things, and as the talk goes along, we will see these things. And so let Wn be the Weil group, which is generated by the real simple roots with Cartan matrix an. Okay, so under simple Weil reflections, it transforms like an odd function. This we can check for all these properties. And in fact, for n equal to 1, 2, 3, and 4, these are indeed WKB, which is Weil, Katz, Borchards, denominator formula for known BKM Lie superalgebras that appear in the work of Gritsenko and Nikulin long ago. Okay, so in other words, these are what we will call Borchards extensions of an. The 0 shouldn't be there. And then there is a no-go theorem due to Gritsenko and Nikulin, which implies that it cannot be that the case for 6, the modular form cannot arise from denominator formula for some Borchards extension of G of A6, which is a Cox-Moody Lie algebra. Okay, and the aim is to really understand the open case of n equal to 6 and obtain the Lie algebra, if any, associated with the Cartan matrix A6. So this is the crux of the idea. And just I would like to comment that BKM Lie superalgebras, etc., are very, very special. And so that you will never find series of them. You'll only find finite numbers of them. So that is why, for instance, I'm looking at 5. Actually, there are more than them, but I'm looking at only 5 such examples because each of them are special. And there is a sense in which these are very simple. Okay. So just a quick recap as how we got to these guys. And so let phi of z denote the Siegel modular form. That's a generating function of quarter BPS states in CHL models that are obtained as Zn orbifolds of type 2 strings on K3. When you take the square root of the generating function, it will give you another Siegel modular form with integer coefficients. This happens only for 1, 2, and up to 6. 1, 2, 3, 4, 5, and 6. And just call delta as square root of phi z. I'm not giving you the weights, etc. They're all this thing. For n equal to 1, 2, 3, and 4, the square root is, in fact, the denominator formula for a family of Borchards Cox-Moody algebras. And this again, all these examples were actually implicitly known in the work of Gritsenko and Nikulin, but in the context of CHL models, this was shown by Dijkgraaf, Verlinde, and Verlinde, and not Jhatkar and Sen, actually, it should be Cheng and Dabolkar. I did these two things got flipped. And for n equal to 4 was shown by me and my student. And so these are Borcher's extensions of the Cox-Moody Lie algebras, which arise. So you give me this Cartan matrix, and you can construct a Lie algebra by a standard procedure. And this thing, but it's not known in this case whether there's a Lie algebra associated with the square roots for n equal to 5 and 6. Okay, these two examples are distinct from the ones which I just mentioned. But by considering twining by symmetries that commute with the order folding, one obtains a large set of examples, and I called it the periodic table for Cox-Moody algebras. And I had only 4 by 4 entries. And then recently, with a couple of years ago, with my student Sutapa, we extended it by adding a few more examples. And so all except this guy in this corner, they all arise from in the context of 𝗦𝗲𝘀𝗀𝗀𝗃 moonshine or whatever. And these are all where the square roots make sense and we get Lie algebras, and they're all associated with. So if you go horizontally, you get a same Cartan matrix for the real simple roots. Okay, but the ones which we're going to discuss today are the ones in the diagonal. And so that's all I wanted to tell you. And delta 0 here does not arise from any diagonal counting that I know of. Okay, and these Cartan matrices are known, and and they are known because of with two things. Ashok Sen worked out the walls of marginal stabilities in the case of CHL models, and Cheng and Verlinde showed that every wall is associated with a real simple root, and from that we can extract these matrices. Okay, so A1, A2, A3 are finite, so 3 by 3, 4 by 4, 6 by 6. But A4 onwards, you get infinite this thing. So A4 is infinite dimensional, so this index Mn runs over all integers. And more generally, A6 is also, there's also A5. You can write a nice, beautiful combined formula for all of them, where lambda is just the roots of this quadratic A root, doesn't matter which one. And you get these formula, you get these recover these Cartan matrices. Okay, so what is the connection with Umbral Moonshine? So Umbral Moonshine is a generalization of 𝗦𝗲𝘀𝗀𝗀𝗃 moonshine. It relates finite simple groups, not necessarily sporadic, but to class functions that are Jacobi forms, mock modular forms. And actually, it's a very, very rich story. I don't understand all of it. But there are 24 examples, again finite, associated with the Niemeyer lattices, with 𝗦𝗲𝘀𝗀𝗀𝗃 moonshine being associated with the root lattice, which is 24 copies of A1. Okay. So for example, for the examples associated with lattices constructed from root lattices from the A series only, like A1, A2, A3, so on and so forth, one actually gets a Jacobi form of weight 0, that is the analog of the elliptic genus of K3. And using this Jacobi form as a seed, one obtains a Siegel modular form phi of Z using a multiplicative lift due to Clarion Gritsenko, and this was done by Sutapa and myself. And then we found that we were able to show that 4 of them already appeared in the context of generalized 𝗦𝗲𝘀𝗀𝗀𝗃 moonshine or in that periodic table. But the extra one was, we got a few more, but at least what I showed there is phi 0, which is associated with A6. Okay, so the 5 modular forms that we are considering are the only ones for which the square root leads to Siegel modular forms with integer coefficients. Okay, in the context of Umbral Moonshine. There are many more examples in Umbral Moonshine, but we can't take square root, doesn't make sense in there. So there's 1, 2, 3, 4, and 6. And the Clary-Gritsenko lift actually provides a modular formula for all these 5 modular forms. So what we have is 5 modular Siegel modular forms of some paramodular group at some level, and we have a product formula for it. So how would this be associated with a BKM Lie algebra? And I'll be a little fast through all these things, but please feel free to stop me because most of it will be standard Lie algebra stuff, which you might know. It's mostly for me to set notation. So if you're given any Cox-Moody Lie algebra, you can decompose it into the Cartan and positive and negative roots. Okay, R plus and R minus. And the simple roots, we'll call them E alpha I, or sometimes I'll just say alpha I. They provide a basis for R plus. Okay, remember this Lie algebra is also vector space. So all the other positive roots will be linear combinations of these. And in the Chevalier basis, you get the crucial one. There is H alpha with A alpha J is AJI A alpha I. Okay, so this AIJ, you write it as a matrix, so it will be an R by R matrix. It's called the Cartan matrix. Okay, so you can work backwards, and if you're given a Cartan matrix, you can do all these things. But then you get the Lie algebra by adding one more thing, which is imposing this kind of condition, which is called the Ser relations. Okay, so you just, if you give me a Cartan matrix, then you can add, you start with simple roots, and then you write this kind of Lie algebra and impose Ser relations. Okay, imposing Ser relations can be complicated. Modally speaking, you get a Cox-Moody Lie algebra, which I call G of A, where A is the. So Cartan matrices are typically symmetric. They may have 2's on the diagonals, and negative and 0 entries for only the off diagonal terms, And it's also such that if Aij is 0, Aji is 0. And I'll skip this. So, but if you're given any real simple root, there's a reflection that you can define, which is reflection. But the whole point is the examples that we will look at, these roots don't live in Euclidean space, but in Lorentzian space. But the same feature goes through. It's still a reflection. So Si of alpha I goes to minus. So it reflects itself. So you get this thing. And the while group is just it's the Coxeter group, which is generated by all these while reflections. So if you are generators, S1, S2, up to SR. Okay, so in our example, some of them will be infinite. So the while group is as infinite generators. So it's pretty complicated. Okay, so there's one more character which comes into play, the while vector rho, which has a property that rho alpha, with alpha i's are, remember, the simple real roots. It has equal to minus half times the norm of this. So if the norm is 2, you will write it will be minus 1. By the way, that's a convention. I'm following with a minus 1. Don't ask me why. I mean, standard books will follow plus 1. Okay, I know why, but okay. But so please, I apologize for that. And so if you take rho while vector and use this thing, you can see that Si rho minus rho, this gives you back alpha I, which is an element in R plus. So the while cuts denominator formula is the following. So let's look at the left hand side. It says that you sum over all roots which belong in the positive, all positive roots, and it's a formal thing, 1 minus e power minus alpha times the multiplicity of alpha. That is the product side, and the sum side is a sum written as a sum over the while group, and determinant of W. These are only permutations, so it'll be plus or minus times the while. Okay, so this is a non-trivial inequality. So the left-hand side knows about the simple roots. They generate the while group. The right-hand side provides the details of all roots. Okay, but the hard problem is to generate the multiplicities of these roots in general. For affine Cox-Moody algebras, the answer is known by connecting to the denominator formula to Jacobi forms, starting from the famous work of McDonald. Okay, so now we'll go through some examples quickly. So SU3, which is the first, rank 2 algebra, it's alpha 1, alpha 2. Its Cartan matrix is this. It's a good exercise to see, can you go through the Ser relations, etc., and derive the standard SU3 Lie algebra that you know, starting from this Cartan matrix. It has 3 positive roots, alpha 1, alpha 2, and usually alpha 3, which is alpha 1 plus alpha 2. Okay, so E alpha 1 plus alpha 2 is just the commutator of these things. Okay, and Ser relations imply that there are no more positive roots. And the while group is just the permutation group in 3 objects. It's order 6. And the while denominator formula works with rho equal to minus half alpha 1 plus alpha 2. You take this as rho, you can check that it has the properties that you need. So the product side, if you write, you get this thing. So you get multiplicities of all these guys are 1, and you multiply it by e power minus rho. And lo and behold, you get, so if you expand this, you get 8 terms. But this is sum over S3, which is ordered 6. And you will have only 6 terms. So there is some cancellations that happen, and you end up getting pi equal to sigma. It's trivial to check. Slightly more non-trivial example is, again, it has 2 simple roots, but now the Cartan matrix is 2 minus 2 minus 2. And the root delta, okay, has alpha 1 plus alpha 2 as 0 now. And now the set of positive roots now includes imaginary roots. And so they are like m delta, n minus 1 delta plus alpha 1, this thing, and m runs from all positive integers. Okay, so you get all these things. And the product side, now you can just take, I've given you what R plus is, you can just write it out this way. Okay. And so you can, so if you write this out, and if you make the following identifications, you make I'm doing it formally, but you can make it by putting in some norm. E power minus alpha 1, you call it QR. E power minus alpha 2, you call it R inverse. E power minus delta, the delta is just alpha 1 plus alpha 2 is then Q. Okay. If you plug this in, what you get is the Jacobi theta theta function up to a factor of S. Which S is okay, S power half. It's just the index of this Jacobi form is half, so I just put some power of half, and you get this product formula. And the sum side again, you can work out what the sum side is, because there's a nice presentation of the while group as a semi-direct product of Z2 and Z, and so you get this term. And showing that these two are equal is a non-trivial identity. Okay, so I'll just. So the idea, so far what has happened is that we had only real simple roots, and what Borcherds did was to add imaginary simple roots. So let me explain what is meant by imaginary. When is a root imaginary? When its norm is 0 or negative. Okay, that's the definition. Okay, and in Lie algebra thing, norm is actually what we will call norm square in physics. Okay, the diagonal elements in the Cartan matrix now have non-positive entries. Need not be 2. And the denominator formula gets modified, leading to the Weil-Kac-Borcherds formula. Okay, so there is a product formula. But on the sum side, there's a modification, which I indicate as T, which gets contributions. So first, the while group is still generated by only the real simple roots. The imaginary roots, even though they're simple, they don't generate any reflections in this setup. And there is a correction term. Okay. So this guy we'll just call this combination delta, and so there's a sum. Delta can be written as a sum. It can also be written as a product. And Borcherds' idea was to add enough imaginary simple roots such that the above sum or product becomes a suitable modular form, which is called the automorphic correction. Okay, there might be more than one way, distinct automorphic corrections given a particular thing, and that's also allowed. And such modular forms admit product formulae, but it's fairly non-trivial to find a situation where you also have a sum, where you can write it in this form. So I'll give you a simple example. So we consider the addition of the following set of imaginary simple roots SL2 hat, m distinct copies of simple roots of weight. Delta, remember, was alpha 1 plus alpha 2 over and above what exists. So these are simple roots. So there's one with weight alpha 1 plus alpha 2, other one with 2 delta, 3 delta, so on and so forth, m of each. And now the Jacobi form, which you get by, if you look at the product side, you just keep multiplying these things. It's just theta 1 with Dedekind eta function power m. Okay, so the product side now becomes just this. And you just, originally it was just 1, which was there, but now we have added m such terms. And I'm also keeping track of the powers of Q. Okay. And so this thing has a different weight. This had originally index half and weight half, but now it will have a higher index. And now there is a Borcherds correction term, and that is just given formally by this adding this term T to the sum side. So what we will do is this became Lie superalgebra, we'll call it as B SL2 hat of M. Okay, so that is just the Borcherds extension of SL2 hat, where we add these M sets of distinct bosonic simple roots. Okay, so this concludes my introduction, and now I'll get on to my work, which is first step is to embed SL2 hat into AN the algebra. So, so all these things, if you notice, they have this 2 minus 2 minus 2. They have a subalgebra, and so the idea is that I don't know the full Lie algebra, but I know a subalgebra. What will happen if I decompose this so-called potential denominator formula using this subalgebra? Okay, so that's the idea. And so let's just understand what SL2 hat is. You start with SL2 written in math notation. So E F is equal to H. So E is okay. So there are just the E, H, F are the generators, and these are the standard commutation relations. The affine Lie algebra SL2 hat is taken by SL2 hat tensored with C of T inverse. That means formal Laurent series in T, that is plus C of k hat, which is the central extension, and C of some derivation. Okay. So, and this is this thing. And from the physics viewpoint, X tensor T power n, these are like the modes of the SL2 current algebra. Okay, so these are the different modes which come. And the Cartan subalgebra is actually 3-dimensional. H tensor 1, which is the SL2 Cartan, k hat, which is like a central extension, and D. Okay, and these are their inner product. So what we do is, so the general structure is something like this. So we pick the first two roots, we just call them 1 and 2, E1, E2, and then we want to express them in terms of E, F, and H with all these tensors with T. So we just take this, and this idea is actually used, some old idea of Feingold and Frenkel, which we thought we can use. So I take E2 to be E tensor 1 and F2 to be F tensor 1. E1 is F tensor T and F1 is E tensor T inverse. So if you put these things together, you can check that then we can identify H1, H2, and H3 in terms of, so that's a 3, here also the Cartan is 3-dimensional. So we get a nice relationship between the Cartans H1, H2, H3, and H tensor 1, k hat, and D. Okay, so standard formula. So now we will look at the denominator formulae, potential denominator formula, because we haven't proved it for 6. So what we'll do is we'll focus on this expansion of delta k. Remember I told you that it has this nice Fourier-Jacobi expansion. So I'm just looking at the first 2 terms. So the first term is just a Jacobi form, which has the same weight k and index half for all of them. And from our viewpoint, S is just, anytime you have something, the power of S is the bookkeeping parameter, which keeps track of the index. Okay. And so what you get is it has this structure, phi 0 k 0 n is theta 1 with eta tau power something. So you can see that this term looks like the denominator formula of some Borchardt extension of SL2 hat, number 1. Number 2, you look at this term, so it's like it's the first non-trivial term. So in CHL orbifolds, you'll have intermediate powers, and that's the reason this is simple. This guy is a Jacobi form associated with Umbral Moonshine at lambency n plus 1. If you don't know what that means, it doesn't matter. But what I'm trying to say is that these Jacobi forms are class functions of some finite group, which appears in Umbral Moonshine. So this is the structure which is in this thing. And so the denominator formula for SL2 hat we already saw gives theta 1, and this is like the Borchardt extension, which I already told you. Okay. So for instance, so phi k half is skip this thing. So the idea here is that since we have a subalgebra, we can ask, can we decompose these guys for starting with size 0n in terms of irreducible representations of both SL2 hat and the Borchardt extension, relevant Borchardt extension. Okay, so first let's do it in terms of SL2 hat. And so what we find is that you get, so these are the characters, I put a tilde for them. And otherwise these are just like the characters of SL2 hat. And so these are the characters, and there is a symmetry in the problem, which says that these two come together with the same sign. So you get effectively n plus 1 independent functions of tau. Okay, so each term in this Q series corresponds to an irreducible representation of this Borchardt algebra. Okay. So the vectors, you can combine these into an n plus 1 dimensional vector, and it's Q expansion, like I said, it's a multiplicities of various irreds. From a practical viewpoint, actually, it's much easier to work with SL2 hat because we know much more about these things. So these two only differ by powers of eta. So, I mean, going back and forth between the F and G's is trivial. So we find it easier to work with this because we know the modular transforms of these guys. Okay, so now comes the interesting point. So we have n plus 1 dimensional vector, which I denote by boldface G, which is we want to work out its modular transformation properties. We know the modular transformation of this guy. We know the modular transformations of all these characters. So that in turn implies the modular transformations of these things. Okay, and what it says is that they mix among each other. That's because the chi's also mix among each other. And so the G's. Somebody asked a question?
No, 5 minutes.
Are vector valued modular forms. Okay. So using their modular transformations, we fix G using only the first few terms, which we can actually numerically compute. So G1, G2, you can compute the first 10 terms. You don't need that much. Okay. So for n equal to 1, 2, 3, 4, we show that these satisfy a modular matrix differential equation considered by Gannon. And in principle, this should have been discussed by Shabir, but he never got to it. Okay. So, then for n equal to 6, we had a problem, but we solved it through some other method. Okay, so we got all the vector value modular forms. So we had a complete understanding of that. So now what can we say about the higher order terms? So starting from here. Okay, so from a second quantized version of Umbral Moonshine and generalizing ideas that I used in the context of Umbral Moonshine, we obtain a formula where all the higher order terms are completely determined in terms of psi 0. Okay. And so I'm writing it here. So basically, delta is this prefactor of phi remains. It's exponential of psi 0n with some Hecke operator acting on it. And the Hecke operator is something well defined. So what is key is that if you give me psi 0n, then I get all the other terms. So all our work in getting vector valued modular forms is not for waste. Okay. But there is, so you get another product formula for delta k of z. And if you combine, if you use this thing and put it together, you get a product formula. Okay, that's some work. It's just a page of algebra, but you get another product formula. And it turns out in this case, we have to check this, that it actually agrees with the Clary-Gritsenko product formula. Okay, and I want to emphasize it doesn't happen in general. So treating the product as a product side of a denominator formula gives us actually explicit formulae for the multiplicity of positive roots, both real and imaginary. Even for n equal to 6, we don't know the Lie algebra, but if it exists, that would be the case. And what happens is that for n equal to 6, we see the appearance of a second set of infinite real simple roots with multiplicity -1. Okay, these are interpreted as being fermionic roots. Okay. And so the structure, I'll skip this. Okay, now the question is, what about the sum side? For n not equal to 6, there's a second construction of Siegel modular forms called the arithmetic lift, and that helps one go ahead and prove. But this fails for n equal to 6 because n equal to 6 has weight 0, and all these formulae, these expressions for arithmetic lift assume that the weight is greater than 0. So we need a new approach to organize the sum side. Okay, so at order s power 2n, if you just follow the Hecke operator, you get a nice formula like this. Okay, and this has a very, very nice interpretation. So what we will do is, so we will denote by Vn, a graded, of course, because it's fermionic and bosonic, it's supersymmetric. There's a graded vector space such that the Umbral Jacobi form psi 0n is obtained as a super trace over this Vn. And Vn, of course, is SL2 hat module. Then what it says is that psi 0 to n is obtained as superspace of the direct sum of two SL2 hat modules. One is the antisymmetric part of lambda Vn, and the other one is what we call a scaled Vn. Okay, how do you understand scaled Vn? You just take, remember there was a C of T and T inverse. You just replace, you only take even powers. So this is subalgebra of the original SL2 with a 2 put in there, but it's actually isomorphic to SL2. You can check because it's only coming this way. I could have called it T prime and T prime inverse. Then it would have been SL2. So isomorphic is this thing. Okay, so the following the work of DMBV in the context of the second quantized elliptic genus, we actually can obtain explicit formulae which are not very transparent at all orders. Okay, and then a key point here is terms involving other SL2 hat modules. We add with M scaling, so replace 2 with M, they also appear. And just experimentally, it's interesting to observe that there are real simple roots for all n greater than 1. They appear in these scaled modules. So we conjecture that all simple roots, not just real, imaginary ones, also appear in the scaled modules. And there is a sense in which terms like this are trivial. Okay, but we don't have a proof of this conjecture at this point. And I'll just conclude here with just pointing out how to handle some of the things. there are imaginary simple roots of zero norm that appear with Borchardt corrections. So let A be such a root, and then below and behold, you get, so this is like the analog of T, which comes from this same, the theta function, the eta power something, right? Same guy, it shows up, and you get these coefficients. And so there are terms which are the Borchardt corrections of some imaginary simple roots. Okay, but it's really these additional fermionic simple roots, they do not seem to fit the term, but there seems to be a guess which seems to work. And so which looks like a new kind of correction, but we haven't been able to quantify it, which should appear and is giving a suggestion as to what route we should go. But at this point, we have not completed proving this thing. So we just have some simple checks that's going on. Okay, so I'll just conclude. The vector valued modular forms provide explicit formula for most the imaginary roots, which are not necessarily simple. And so this is a new result. The results were known for roots which had zero norm. And so we have got explicit formulae. Our goal is actually to organize the Siegel modular forms in terms of orbits of the full Weil group. And this result is only a first step. The infinite dimensionality of generators of the Weil group presents a complication. And so playing around with the Weil group, it is very important to have a nice presentation for it so that you can write out terms nicely. For instance, for SL2 hat, it's a Z2 cross semi-direct with Zn. So you can write the sum side as a difference of two terms which are related by C2. Okay, so we would like to obtain and classify all kinds of corrections that are terms that appear on the sum side. For n less than or equal to 0, Kritz and co-equivalent show that these are Borchardt corrections. So for n equal to 6, we will anticipate there'll be new kinds of corrections, not just one, that go beyond what Borchardt did and will help us understand A6 better. As of date, of course, we have not completely understood the sum side, and hence we do not have a clear picture or whether even such a new Lie algebra exists. Okay. The worst case scenario would be that we will end up with a Lie algebra with a module over it. Okay. So thank you.
Thank you so much. Any quick questions?
Okay, so thank you.
Okay, thank you, Suresh. Thanks a lot. Okay, so the next speaker, final speaker, is Chethan Gowdigere from IIT Bhubaneswar, and he'll be telling us about classifying 3-character rational CFDs. Okay, Chethan.
Yeah, can you hear me?
Yeah.
Okay. So first, let me start by thanking the organizers for giving me this opportunity, and also thanking Alok and his team for all the hard work that has gone into this conference. So the title of my talk is Classification of 3-Character Rational Conformal Field Theories. So it is based on these two papers which have fortunately been published in JHEP. And I should point out my collaborators here. All of them are PhD students. Arpit Das is a PhD student in Durham University. Jagannath Santara is a PhD student in NICER, where I work. And Jagannath is actually graduating soon, and he will be soon applying for postdocs. And Sachin is a beginning graduate student. Okay, so a classification scheme for rational conformal field theories is known as the MMS program. It's named after Mathur, Mukhi, and Sen, the founding fathers of this program. This program was set up more than 30 years ago, and I believe at least 2 of the founding fathers are participants in this conference also. So though the program was founded more than 30 years ago, it lay dormant for a long time, and it was revitalized around 2015, about 5-6 years ago, by one of the founders, Sunil Mukhi. So a series of papers he wrote with his students and Gabardiel have contributed very heavily to this program. And besides Sunil Mukhi and his collaborators, other groups have contributed to this study. It includes Harvey and collaborators. It also includes the Chaos group. The Chaos group, I've written two important papers which I found very useful. It also includes Perlmutter, Kaidi, Lin, Para Martinez, a couple of papers, recent papers from that group. And there have been a lot of mathematics groups from mathematics departments and mathematicians who also study this problem, study the problem here for their own purposes. And I'm highlighting one such paper, which will come up in this talk later.
Can I make a comment?
Sure, sure, sure.
Yeah, I think Gannon's results are much more general than Frank and Mason.
Please repeat.
There are some Frank and Mason's work. There are some limitations, and probably you should look at Gannon's work.
Oh, Gannon's, yes.
Yeah.
Thank you very much. Thank you. Yeah, thank you. Yeah, Gannon's work. Yeah, I will look at it. I have looked at it, but not enough. I will.
Yeah, they force the exponents to be between 0 and 1. That's
I
put in mind, which is not necessary.
Okay. Anyway, so in the MMS program, the program identifies the rational conformal field theory by two non-negative integers. What is usually referred to as N and L. What is N? N is very simple. The partition function of a rational conformal field theory takes the form of a finite sum of products of holomorphic and anti-holomorphic factors. And N is simply this number of these independent factors. So these independent factors are known as characters, and N is simply that thing. Now, N is clearly a positive integer. In this talk, we'll mostly look at N equal to 2 and N equal to 3. And N is also, N being the number of independent characters could be different from the number of primary fields. We'll see examples as we go along. N is easy. The question is, what is L? L for a long time didn't have any name, and recently it was named the Wronskian index by, again, Sunil Mukhi. So let me try to explain what is the Wronskian index. For that, let us recall the Q-series expansions of the characters of rational conformal field theory. So here I've given you chi-naught of Ti, which is the identity character, and the other non-identity characters have is in the second line here. And the leading behaviors are also known as the indices. So the index of the identity character is minus C by 24, and the indices of the other ones are H minus C by 24. So the important thing is that these characters, they are solutions to a modular linear differential equation, which I'm sure has come up in various talks. At least I could see that it came up in the previous talk. So these are differential equations in the tau space, where the derivative is something slightly special. It's called the Serre-Ramanujan derivative. It's given here. Basically, the important thing to remember is that the Serre-Ramanujan derivative takes a modular form and returns a modular form again with weight 2 times more than that. Now let's get back to the differential equation. The coefficient functions of a modular linear differential equation, just like ordinary differential equations on the whole complex plane, can be written in terms of Wronskians. Okay, and now let's recall what's a Wronskian. Wronskian is a determinant of matrices where the derivatives of the solutions are there. And the usual Wronskian is the one where the nth derivative is missing, but there are all these other Wronskians also. So the Wronskian of the characters of a rational conformal field theory is what one focuses on, and we can show that it's modular with weight n into n minus 1, and here so there's a valence formula for modular objects. So when we apply the valence formula to the modular object, you get the formula like this. So here on the right hand side, the first term basically encodes the behavior of the characters on the Wronskian at infinity, and the second term encodes the zeros of the Wronskian. So L is the Wronskian index. L by 6 encodes the zeros of the Wronskian. Something is missing. You can't see any picture here, right?
No.
Okay. Okay, there's something wrong. Okay, basically this picture here was supposed to be the well-known, everybody knows this, the upper half plane with the SL2Z fundamental region showing. So basically we know there are cusps at the omega, the cube root of unity, and the square root of -1, there's a cusp there, and there's also a cusp at infinity. So basically, the Wronskian index of a rational conformal field theory contains information about the zeros of the Wronskian, which can either be at the finite cusps or in the interior or on the boundary away from the cusps. So a simple zero at omega gives a contribution of 2 to the Wronskian index. A simple zero at I gives a contribution of 3 to the Wronskian index. And similarly, anywhere else, it gives a contribution of 6 to the Wronskian index. So these two objects are the things that the MMS classification program identifies a RCFT by. Okay, so these two little somewhat different kind of a data is set up as an identifier for the RCFT in this classification program. So now that we know what is the important parameters, what are the important properties of a RCFT which goes into the classification program, one asks the question: well-known RCFTs, what are their NL values? So I start by discussing the very well-known Bindusar minimal models, and you can it's very well known. We know the central charge. We know the models are identified by 2 co-prime integers, and we know the scaling dimensions. So this is one example where the number of primary fields is also a number of characters. And if you put everything together with a little bit of high school algebra, we can show that the Bindusar minimal models have a vanishing Wronskian index. And this was, of course, very well known even 30 years ago. It appears in one of the foundational papers already. Now you can also ask the question, other CFTs like super Bindusar minimal models. So here I'm considering just the unitary series, which is labeled by integer m bigger than 3. The central charge is given here, and the superconformal primaries are also given in this formula here. So we just here need to ask the question: how do superconformal primaries split under the subgroup under the conformal subgroup, so subalgebra rather? And for the Neveu-Schwarz fields, these are the branching rules which we can read from some old papers. And similarly for the Ramond fields, there is a branching rule again. So one can do a little bit of algebra and compute the characters. And this time we find the Wronskian index is actually mostly non-vanishing, except for m equal to 3, which is also the tricritical Ising model, which is also part of the Bindusar series. That's the only one which has a vanishing Wronskian index. Everything else has a non-vanishing Wronskian index. Another class of rational form field theories, which one would like to know what their NL values are, is Weismuller-Witten CFTs. And all of us know that the Weismuller-Witten CFTs are parameterized by a simple finite algebra and a level K. And the formulas for the central charge is given here, very famous. And the Weismuller-Witten primaries are obtained, the number of Weismuller-Witten primaries of the theory are obtained by solving, finding non-negative integer solutions to an equation such as this, which involves the level. And every Weismuller-Witten primary carries a representation of the finite simple Lie algebra. And using the data of the finite simple Lie algebra, we can compute the scaling dimensions. Now, in this problem, the number of characters and the number of solutions, the number of characters and the number of primary fields are usually different, not always same. Okay, this is because of some symmetries in the Dynkin diagram. Again, there's a big blank space here and something wrong with my setup here. The diagrams which I wrote by hand are not showing up. So basically, the diagram shows the Dynkin diagrams of D4 and DR and AR and E6. So these are diagrams which have a symmetry, and in all these CFTs, the number of primaries are not equal to the number of characters. You have to study solutions to this equation modulo the symmetries of the Dynkin diagram. And this is not the main part of my talk, but we wrote a paper where we studied all these CFTs and identified them according to the MMS identifiers. So some results are displayed here. One thing is that SU2 Weismuller model at all levels have a vanishing Wronskian index. And we also show that all the algebras at level 1 have a vanishing Wronskian index. And we also found exact formulas for Lie algebras at level 2. And there you find that the Wronskian index doesn't vanish except for small ranks. And there are some surprising results like A2 at any level and G2 at the same level have the same N and L values. Okay, so let's go on with the main problem of MMS program, which is classifying RCFTs. So the main point is the following: that for any given NL, give me an NL value, there's a unique MLDE up to some constant parameters associated with it. And the main point here is that all RCFTs with the same NL values solve this MLDE. So all NL RCFTs solve one single MLDE, of course, for different values of the parameters of the MLDE. So I want to illustrate this very nice principle by examples only. The main thing is to remember that the coefficient functions of the MLDE are related to the Wronskins of the solutions. So, for example, when the Wronskian index is 0, the Wronskin has no zeros, and hence all the coefficient functions have no poles and are holomorphic. And we can just use we can quickly construct the MLDEs. Okay, so I've given you shown you 3 examples here, and I've adopted a small notation here. The parameters of the MLDEs, I've written it as mu AB. That's the parameter which accompanies the term E4 power A and E6 power B. So a 2.0 MLDE has 1 parameter, a 3.0 MLDE has 2 parameters, 4.0 MLDE has 3 parameters, etc. So similarly, I'll give you one more example for n at comma 2 MLDEs. So the Wronskin is a 0 at the cube root of unity, and hence it can have a pole there. Is a question there?
Yes, sorry, Chethan, sorry to disturb. One question. So when you calculate N and L, you calculate them from Virasoro characters or characters of whatever chiral algebra is at work? For example, for the Kac-Moody, for the WZW models, do you use the Kac-Moody group, or maybe you said that and I missed?
No, I use the Virasoro characters. I'm counting the Virasoro primaries.
No, you're not counting the Virasoro primaries. As you said, the partition function is a sum of mod squares, right? Of terms, and that's a finite set of terms. So you're using those. So those are not all the Virasoro primaries.
I see. So the characters under the biggest chiral algebra is.
That's correct. But we don't even have to know what is the chiral algebra. We just we just specify the number of characters in advance, right? So in principle, one doesn't even know what the chiral algebra is at that stage.
Okay.
The N of Chethan defined N and L. So that N is the number of characters under some generalized chiral algebra, what the biggest one, as you said.
I see.
But one doesn't know what it is. But it's not the Virasoro characters, huh, Chethan? Bezume-Inovitan models have infinitely many Virasoro characters, but you're not summing over those.
Yeah, but linearly independent characters is what.
No, but they're not Virasoro characters. Virasoro characters, by definition, are just characters of the Virasoro algebra only.
Yeah. Sorry. Yes.
Yeah, I think that is just terminology, but I think it's
okay. I see. And then the chiral algebra could be a label in addition to N and L, right? In the
no, I think that's an output of this procedure, so it's not a label.
Okay, thank you.
Okay, so let me continue. So the point here is that given N and L, you can construct an MLDE, and you are meant to solve that MLDE to find all CFTs with that particular N and L. So this was implemented early on for 2.0 and 2.0 MLDEs and 2.0 CFTs in the original Mathur paper, MMS papers, and also for 2.2 MLDEs and 2.2 CFTs starting from that time and completed more recently. So I want to start solving MLDEs. So basically, the story is quite simple. We just use Frobenius method, and we call something as admissible character solutions, where your characters are where you impose that the identity character Fourier coefficients are positive integers, and the non-identity character Fourier coefficients are positive rationals, but then they can be made positive integers by multiplying with a common denominator. So this is the point here. One has to scan the space of parameters of a MLDE and look for admissible character solutions. So more parameters there are on the MLDE, the problem becomes technically harder. Okay, so now the 1 parameter MLDEs are the 2.0 and 2.2 MLDEs, which was studied long back, and 2 parameter MLDEs are 3.0 and 3.2, which I will talk about in the rest of the talk, and 3 parameter MLDEs are 3.3, 3.4, 4.0, which I'll probably come in there's future work coming up in that direction. So we start with 3.0 CFTs. So here we have 2 parameters in the MLDE. So the strategy we follow to solve this thing is that we take 2 equations. One is the the leading order equations from the Frobenius solution and the next to leading order equations from the Frobenius solution. And we evaluate these both these equations for the identity character and solve the two parameters in terms of identity character objects such as alpha naught and M1. So that's the main point here. We exchange quickly the parameters for identity character objects. And then we go to the next Fourier coefficient, that's the M2. And this is this big equation, which is written in small print. The main point here is that if all these equations are there in the original MMS papers itself. The main point here is that this is an equation where everything is an integer. Okay, everything is an integer. So we can conclude that n needs to be an integer by the integral root theorem here, because there's an equation for n and all coefficients of that equation are integers. So we use the integral root theorem to conclude that n is an integer. And so what this means is that the central charge, which can be written as n by 70, and this is where our computations become simpler. What it's telling us is that the central charge is always an integer divided by 70. So if I want to study CFTs in a range of 1, say, I only need to do 70 computations now. Earlier I had to do a lot more computations. So this is what I do.
Sorry, I'm confused about something. If yes. I have a polynomial equation whose coefficients are integer, doesn't mean the solution is integer, right?
No, the coefficient of n power 4, the leading power is also 1.
Yeah, but I can have a quadratic equation in x squared plus ax plus b equals 0. That certainly doesn't have integer solutions for all integer a and b.
If this equation admits a rational root.
If it's rational, then it's integer. Okay,
yeah,
that I can.
RCFT. Yeah.
Okay. If it's rational, then it will be integer. Yes.
Yeah. So this is actually this equation is from your old paper, and this conclusion is also from your old paper. Very nice conclusion. We just managed to take that conclusion and say that now our central charge will always look like an integer by 70. Okay, so if I want to study, look for CFTs between 0 and 1, I just need to do 70 computations now. So this is just what we did, and we get 2 Diophantine equations for 4 variables, and we just have to solve one by one. And this is just what we did. We studied up to C less than 96. We had to do 6,720 computations, and we found many admissible character solutions. There were 303 discrete solutions and 2 infinite series. And I want to try to, I just put some tables from our papers just to show that these solutions are there, a lot of them. So the first row indicates the solutions to the 2 Diophantine equations, and the first 4 columns, and the other columns indicate other data of the CFT, which was the potential CFTs, which was derived. So we organized all these solutions into 5 categories of solutions. I'll only talk about 4 of them. The first category is simply well-known RCFTs, which are being rediscovered here. So I won't spend more time on them. And then there's a third category of solutions, which we call the third category. So these are Frank Mason vertex operator algebra solutions, which is being rediscovered here by us. But these solutions already existed in the literature. But these are still at the level of admissible characters, and we still don't know whether they will give any potentially new CFTs. And the fourth category of solutions is what is known as the GHM dual. So GHM, Gabeldiel, 𝗰𝗶𝗶, and Mukhi showed us how to construct new CFTs starting from a metamorphic CFT and an affine subtheory. And we refer to these as denominator theories and coset theories, or duals, GHM duals. And there is a situation where both the coset and the denominator are 3-0 CFTs. And in such a situation, the central charges have to add to 24, and the scaling dimensions have to add to 2. So what we found is that there are 15 of the solutions that we found are actually just GHM duals of known solutions. And many of these, many or probably all, are constructed or anticipated by GHM in their paper. They're just being rediscovered here. And the last category of solutions, so we just have 7 solutions, the fifth category, 7 solutions. And here we actually found some solutions which seems to us to be new. And Jehep also agreed that it is probably new. So we have, after finding so many solutions, there are only 7 of them which are really potentially new admissible character solutions. So I have just written down the characters of these 7 solutions just to show that we actually got it. And I have to mention here that this 3.0 CFT work was done by us, but it was also done by 2 other groups. And you can see the archive numbers here. We were within the space of 4 or 5 days, we put our papers unknown to each other. At least I didn't know any of that they were working on this work. So 3 groups kind of discovered the same kind of results using very different methods, actually.
Chethan,
yes.
Can those characters be written in terms of hypergeometrics?
Yes, they can be actually, but
they're all hypergeometric type.
Yeah. There's a way to go to that lambda. That lambda is that gamma naught. So there is a, you can go to
in terms of J. You have to use a J function and write.
J. We can do it with J, and we can also do it with the Hopf module of some other of gamma naught 2 or something.
Okay.
That's
right. I mean, that's the analog of J.
Yeah. Okay, so that was 3.0.
5 minutes.
Yeah, so that was 3.0 CFTs, and 3.2 CFTs. The technical content is similar. It's also a 2-parameter MLDE. So we follow the same procedure, hoping to find new CFTs. So I won't repeat the procedure. It is just that this time the problem is a little more harder. The central charge is an integer divided by 210. Okay, so if I want to search for CFTs in a central charge range of 1, I will need to I will need to do 210 computations. And we did do this 210 computations for every central charge 1 range for up to C less than 96. And we managed to find only 9 solutions, only 9 admissible character solutions. And these solutions are not very satisfying because they are just the 2.0 CFTs which were discovered by MMS 30 years ago. Those solutions adjoined with a constant character. A constant character is a solution where the Q series is just the number 1. Okay, so the scaling dimension is exactly C by 24, so that the index is 0 and all Fourier coefficients vanish. So such trivial solutions, well, in some sense they're trivial because you don't get probably a new CFT. You have an old CFT adjoined with a constant character. So we just get back those solutions. We just get some old solutions in some new bottles. So the next question one can ask is, okay, now we have admissible characters. How do we get to CFTs? And this is also something in the papers of when the program was established 30 years ago. Beautiful papers were written and whole procedures were set up how to go about this story. And since I'm not doing too well in time, I will probably not spend too much time on it. So I'll just say that one can ask the question. One can go to the one can go from the tau plane to the lambda plane, where lambda is this object associated with the Hopf function of some particular congruent subgroup. And then you have a hypergeometric function, hypergeometric differential equation. And there we can compute how the S transformation of the SL2Z acts on the character. There it acts as the monodromy matrix of the solutions of the differential equation. And once we know S, we can do many things with it. For example, we can ask the question, we can compute the number of primary fields associated to the characters. And so we did this for, this is work in progress, and it is still many doubts are there, many questions are there. But we seem to get these theories where the number of primary fields are really large numbers like this. And yeah, there is more work to be done here. And this is just a direction of what is happening in this work. And there are some more results that's coming out of this classification is that we found many pairs of CFTs which are potentially GHM dual pairs. That means they have central charges which add up to 24 and scaling dimensions, which conformal dimensions which add up to 2. And among these pairs, some of them are pairs of well-known CFTs, and some of them are two unknown things, but they seem to be dual to each other. So these are also questions which can, these lead to many questions. Is there what is the meromorphic CFT that is underlying this suggested GHM duality? Yeah, so this is the upcoming work. We hope to make progress in solving 3-parameter remedies along the techniques established for 2-parameter remedies in this talk, and also explore more aspects about the GHM duality which we are observing within the 3-0 classified RCFTs. Okay, I will end my talk here. Thank you very much for your attention.
Thank you, Chethan. Any questions?
Yeah, can I ask the question?
Yeah.
Chethan, how do you determine the S matrix? I mean, T matrix you get from H. That's very easy. But how do you get the S for any of these characters?
S matrix is let me try to. I'll try to say it in. The way the S matrix S acts on lambda is it acts on lambda in a certain weights. I think it's lambda by 1 minus lambda or something. And you just you just write the solutions of the differential equation in terms of hypergeometric functions.
Okay.
And then you just impose, you just ask the question, what happens to this character when lambda goes to that? And then, yeah, that's how you do this procedure. I'm speaking very stupidly, but that's roughly kind of the thing that's going on.
Yeah, I had a couple of questions.
Yes, sure.
And a comment. So one comment is I think Suresh asked if these are hypergeometric, but I'm pretty sure these these solutions of this are not hypergeometric functions, right? Because these are sets of 3 functions that go into each other under monodromy. And my understanding was that hypergeometric are you have 2 functions, you don't have 3.
No, Ashok, not Ashok, sorry. Sunil, rank 3, you have, I mean, all the Frank Mason rank 3 things are hypergeometrics.
Okay, I mean, in 1989, there was a paper by myself with Sudhakar Panda and Ashok Sen, in which we showed that this general equation has a solution in terms of contour integrals. Now, it might be that those contour integrals are some rank 3 hypergeometric functions, but just to add to what Chethan said, that those contour integral representations are enough to calculate the Sij. And a year ago, I wrote a paper with Palash Singh and Rahul Poddar called something like contour integrals and modular S matrix. So that does a much more general class of cases.
Oh, very nice.
So that's one thing. The second comment I had was, can you go back, Chethan, to that case where you have a list of your 7 exotic theories and you found some very large number of primary, no, not this, very large number of primaries. You had a table.
Yeah, just
somewhere near the, this. Yes. Now, in this list, you don't have central charge 8 and 16, is that right?
Yeah, no, these are the new ones which there's no 8 and 16.
But 8 and 16 were found actually, in fact, they were found first by 𝗵𝗶𝗶 and myself, but we didn't understand what they were. And then the Korean group discovered them again. And I was working with them. We were able to show that those also have very large degeneracies, like these kind of 6 or 10 digit numbers in the partition function. And it's a very interesting open problem to find out what CFTs these are, because they obviously have some number theoretic significance because of these very large degeneracies.
Have you tried putting these numbers on OEIS?
Yeah, I don't know. Yeah, I have tried a few things with the numbers, but yeah, maybe
put them on OEIS and see if they show up somewhere.
Yeah. Okay, thanks.
Okay, thank you.
Okay, any other questions? Okay, then thank you, Chethan. I think
thank you very much. Thank you.
Okay, Alok, maybe you can take over.
Okay, great. Thanks, Bobby, and thanks to all the speakers again. So we reconvene and at 4:15. Sunil, is that okay? 4:15, 4:15?
Yeah, that's fine.
Perfect. So let's meet after 15 minutes. Thank you.
Radhaji, Gyan here.
Hello, Jan. How are you?
Fine, fine. How is your health? How is your health?
My health is okay. My health is okay. Yeah.
Good to see you.
Nice to see you.
Nice to see both of you.
Sunil.
Nice to see you, Sunil.
You are as evergreen as ever. Huh?
Oh, thank you.
So
I think,
yes.
I'll ask the speaker. Loga, are you there? Maybe you can try sharing your screen just to see it all works. Loga?
Okay, I'll switch off.
Maybe Loga has gone for tea or coffee or something.
No, I'm here. I'm here. Sorry.
Sorry, did you say you're there?
Yeah.
Oh, your voice is almost inaudible.
Okay. Okay, good. I'll correct.
Yeah. So,
Hello. Is this better?
yes, that's a lot better. We can see you now and also we can hear you clearly.
Yeah.
So just try sharing your screen, see if that works.
Yeah. Just. Okay. Is this fine?
Yeah, that's good.
Let me just.
Yes, it's fine actually. Perfect. You can leave it up. Yeah. Okay. Great.
Sorry, just one minute.
Yeah, try present a slideshow. What? Better. Perfect.
Okay.
Okay, it is 4:15 and I think we should start. Alok, is it okay if we start?
Yes, by all means, please.
Okay.
Thank you.
Okay, so we have a long session ahead of us, 3.5 hours with no break. So let's start right away. I'm happy to welcome Loganayagam, and he'll talk about Wilsonian boundary conditions in the fluid gravity correspondence. Please start.
Hello, everyone. I should thank the organizers for giving me this opportunity to give this talk. I would have, of course, liked to visit IIT Roorkee in person, but the times are what they are. I hope everybody is doing well. And what I wanted to tell you guys about over the next half an hour or so is some work we have been doing, in last 1 or 2 years with various collaborators, and Jwel Ghosh and Siddharth Prabhu and Vishal, they're all postdocs at ICTS. Temple and Julio are postdocs at UC Davis, working with Mukund. And Akhil is a graduating student, like a PhD student who's graduating this year from ICTS. Okay, so what I wanted to talk to you about was an aspect of the papers that I have noted here, and it is about how to think about Wilsonian boundary conditions in fluid gravity correspondence. I'll explain what I mean in due course. So let me maybe start with just the title. What do I mean here by Wilsonian? So this is something that we are all familiar with in effective field theories. So it's a particular kind of a strategy to construct effective field theories. And as an illustration, I'm talking a very old example, like going back a century, what is called as a Born-Oppenheimer approximation in atomic physics and chemistry and so on. So the idea is that when you have a system with some slow modes and fast modes, so fast modes are modes whose dynamics is set by a time scale which is very small, and slow modes are kind of very long-lived modes whose dynamics is very slow. And in this case, like the example that Born-Oppenheimer considered, the slow modes are the nuclei, which move very slow because they're massive objects compared to electrons, which move very fast, and whose evolution is very fast. And the idea is to first freeze the slow modes. Okay, so the idea is to understand the dynamics is to freeze the slow modes. In this case, nuclei. That is, think of nuclei as being in a very specific positions, and then you solve for the fast modes. Okay, in the slow mode background. Okay, so you kind of solve for the dynamics. So you only solve for the dynamics of electrons. We will now say that nuclei are kept off shell, and you kind of integrate out the electrons. Okay, to kind of get an effective theory. And what Born-Oppenheimer got was an effective potential for the nuclei, in the sense that effective potential where the nuclei then move, which are generated by these slow modes, which are electrons in this case. So I want to kind of think about a similar kind of, like fast-slow separation and integrating out things and freezing the slow modes and so on and so forth. But in the context of fluid dynamics, it's a much more complicated problem, but conceptually the idea is the same. So you have fast modes, which are the microscopic degrees of freedom, and the slow modes are the fluid modes, which evolve at a microscopic scale. For example, if you take a glass of water and you stir it, the microscopic molecules of water, they exhibit very fast motion at a microscopic time scale, at a very small time scales, whereas the fluid settles over, like a macroscopic time scale over a few seconds or something. Okay, and the idea is to kind of, like integrate out the fast modes and generate some effective theory for the fluid, of the fluid modes, which is essentially just fluid dynamics. Okay, and I want to, like basically think about how to do this in a dual gravitational theory when the fluid dynamics is of a CFT with a gravity dual. Okay, so the broad outline of my talk is, I have divided into like 3 parts. Okay, so in the first part, I will just be saying something about, why we should be Wilsonian in fluid dynamics, why this is a good thing to do, why this is a sensible thing to do to separate things out. I think, most of us probably already accept it's sensible, but it's useful to kind of go through this argument a bit more. And also why in practice, okay, nobody ever is Wilsonian, in the sense that whenever we derive fluid dynamics, we do not know how to actually implement the strategy I just outlined, and what are the difficulties. So that will be the first part of my talk. And in the second part, I will move on to the gravitational side, and then describe how gravity does it, how gravity separates this. It's easier to separate on the gravitational side the slow modes from fast modes via a simple scalar model. Okay, so I will just describe and sketch what happens in the scalar model, what did we learn by studying the scalar model, and I will then conclude with further directions. So I kind of leave out most of the technical details and so on, for which I will refer all of you to these papers that I had in my last slide. And also, there's a talk that Akhil is supposed to give on Friday where he will cover some of the details. Okay, so let's start. So now why we should be Wilsonian fluid dynamics, why we should kind of freeze out the fluid modes, integrate out the microscopic modes, and get this theory and so on. I mean, the one-line answer is, of course, this is the right thing to do, and you do it for the same reason that Born-Oppenheimer did Born-Oppenheimer approximation, because there is a very distinct separation of scales, and the physics become much more clearer if you separate them out. But even if you could integrate our fluid dynamics, we should not do it, because the fluid dynamics are very long-lived modes. And when you integrate them out, the thing that you get will be is usually such a mess. Let's say if you calculate correlation function, integrate them out, that it's very difficult to parameterize and see what is happening if you integrate out everything, okay, including the fluid dynamic mode. So this, I think, all of us would readily accept. But despite this argument, the fact, I think, is that all current microscopic derivations of fluid dynamics, we never quite succeed in doing this separation, okay, as Wilson tells us to do. And we essentially integrate out everything. Basically, you solve the dynamics of everything. Maybe you do kinetic theory, you solve the full Boltzmann equation, and then you recast it into some hydrodynamics. That's the thing that you usually do in weakly coupled theories. Or you do something else, right? So, but the point is that you kind of essentially integrate out everything. The main reason for this is that it's very hard to actually do this separation. I mean, this is, while we all accept that the slow and the fast modes have to be separated, it is very hard to separate them as a part of a single system. Born-Oppenheimer got away with it because there were electrons and there were nuclei, and they were kind of visibly different systems. And you could just cleanly identify what the nuclear degrees of freedom are and what the electron degrees of freedom are, and kind of integrate them out in a systematic way, freeze some of them, and so on and so forth. But when you have something like a quantum field theory, and the slow and the fast modes, the microscopic degrees of freedom and the macroscopic degrees of freedom are very closely intertwined. It's very difficult to actually separate them out. Okay, and you have to kind of use quite an amount of intuition and wisdom to do that. Okay, and our life is made more difficult by the fact that actually in weakly coupled theories, which is a thing where we know how to calculate quantum field theories, everything is actually slow, because the dynamics is slow, the thermalization is slow, the scrambling is slow, collisions, because essentially the leading order is like a free theory, and in free theory basically the evolution is trivial in some sense. Okay, and any non-trivial evolution, okay, takes a long time to settle it. Like say, if you hit the theory, it takes a long time to for that energy that is given in to thermalize and so on and so forth. This is also true also of most integrable theory, which is another playground where we learn things. So basically, our luck is very bad, because the two main sources from which we gain all our theoretical intuitions from, this separation is very hard in them by the nature of the systems. Okay, and in fact, in weakly coupled theory, the slow-fast distinction emerges only at very non-perturbatively long time scale. So everything is slow, but in some sense, the fast modes are kind of evolve at some non-perturbatively long time scale, and slow modes are even slower. Okay, in some sense. Okay, so unless you kind of do some desummation or something, okay, you have to be very clever to extract out something. The second reason is that, like unlike the standard Wilsonian effective field theories, the effective field theory that we are seeking to derive is a dissipative effective field theory. Many of you have heard me talk about this. It's what we would call as an open quantum field theory, and there are various kind of peculiar features to it, which I don't want to go into today. But the point is that like these differences mainly mean that we don't understand like all this integrating out very well, and it is difficult to and the reason our theoretical understanding is so bad is again because we have like very little examples because of the reason one. And it's difficult to construct clean examples and study the renormalization group effects and so on. So you can try to push the effective field theory paradigm as much as possible from what you know, but in the absence of clean examples, like it's very hard. That life is very hard. Another reason, which is not always appreciated, but it is true, is that the fluid dynamics, which is also related to the statement that it's an open theory with dissipation and so on, is that the fluid dynamics also has slow and fast fluctuations. So, but first of all, it has fluctuations, which means that it's should be described like a stochastic theory, like Langevin theory or something. Another thing which is true about it is that these fluctuations also show a slow fast separation. There are slow fluctuations and there are fast fluctuations. Okay, so all fluctuations are not the same. And one needs to separate out those fluctuations also, okay, in principle. And we don't understand the fluctuation very well to the extent even we understand fluid dynamics. Fluid dynamics we basically get by because of experiments. These fluctuations are not experimentally measured also, so we don't know how to separate them slow, fast, even at an intuitive level. Okay, we just know that they probably should exist in principle, and that's it. Okay. So we do not yet know how to implement the Wilsonian strategy in fluid dynamics, and this has terrible consequences. Like this means that our kind of understanding our calculations on deriving fluid dynamics are kind of messy, and so basically like the usual thing that one does, one opens a textbook or one of the standard references where people calculate viscosities of various things like large and gauge theory, say. Okay, you open this paper, what you see is that basically you integrate out everything else, you calculate the correlators, and because you've integrated all the slow modes also, and fluctuations and everything, you get some, like correlators with some complicated IR divergences, and then, like you kind of squint at it to see how to extract out hydrodynamics out of it. Okay. A lot of times, like Largen helps. Okay, you can kind of, like kill the fluctuations by hydrodynamics. You can kind of look at the Largen counting and kind of separate out the fluctuation contributions to kill the IR divergences and extract out by Kubo formulae the viscosity and so on, which is what mostly people do. Okay, but once you kind of, go beyond Largen, or once you want to take into actually study these fluctuations rather than just throwing them out, just like that. Okay, you do not know what to do. So the fact is, the hydrodynamics, stress tensor, fluid dynamics cannot even be defined within a Wilsonian framework. Okay, in the sense that like usually ordinary books say, oh, you take the stress tensor, you look at such and such a structure, you say this is pressure, this is viscosity, and so on. But actual stress tensors, if you actually include fluctuations and so on, are horribly IR divergent, and you can't identify anything. Okay. You can identify probably viscosity, but the viscosity that you identify at long distances is, would have with fluctuations is very different from the Wilsonian viscosity. So one should kind of distinguish between the 1 pi viscosity and the Wilsonian viscosity. And this 1 pi, so to speak, one particle irreducible, where you integrated everything in analogy with quantum field theories. Okay, one particle irreducible hydrodynamic coefficients are not even well defined. They're all kind of horribly IR divergent. It's very similar to what happens when we think about S matrices in QED or something, where you have the soft modes, and you have to be very careful. You have to ask the correct question to get the right answer, and it's not always clear what the correct question is. Okay, so the infrared structure we don't understand, and so for these reasons, we are, though we all, I think, like everybody in the field, we understand that, that one needs to be Wilsonian and one needs to separate them out to get a sensible answer. In practice, like one doesn't know how to do it. and then one kind of tackles them, like and one does things like going to large N and then throwing out things that create trouble for you and so on and so forth. Okay, which is not very satisfactory. Okay, so the question that I want to ask today is whether is there anything that you can learn from gravity? Okay, so this is on the side of field theory, and as I said, like a weakly coupled field theory by its very nature, this separation is very hard to study in that framework. Okay, so it's natural to ask, like now that we know ideal CFT and so on, whether we can recast this problem into gravity and make progress. So if the fluid dynamics is that of a CFT, of a conformal field theory with a gravity dual, then the fluid dynamics is basically the study of slowly varying black hole solutions, okay, on the dual gravitational side. Okay, and the question is that like how do we think about slow modes and fast modes on the other side, and whether they're cleanly separated, and whether we can understand like how these things are, how these things work. One main reason for optimism is that gravity is dual to a strongly coupled theory. Classical gravity is dual to a strongly coupled theories. Okay, and strongly coupled theories, for the same reasons that I had described a few slides ago, their timescales, there the timescales are much more cleaner, because like at strong coupling, these slow modes and fast modes are the separation is very much cleaner, because the timescales are shorter in strongly coupled theories. Okay, the timescales of fast modes really are fast. They die out fast, like in strongly coupled theories. And the idea is to kind of learn how such modes interact and how these things work, and hopefully, like that will tell us how to disentangle even the weakly coupled problem, or maybe intermediate coupling problem in some way. Okay, so that is the hope. So like in these works that in last year and before that, like I and my collaborators, we showed that like this Wilsonian strategy can indeed be implemented at a quadratic level, at a leading order. Okay, and you can do separate slow and the fast modes. Okay, so you have to what it requires is that you have to write down the Einstein-Maxwell equations of the black brane, and you have to separate them in a clean way. And remember, I told you that the fluctuations also come in the slow and the fast versions. What that means is that like the Hawking modes, okay, the Hawking modes, which also you should solve for to understand the fluctuations in the hydrodynamics, also come in slow and the fast versions. So you have to separate out the Hawking modes also into slow Hawking modes and fast Hawking modes, okay, which people usually don't think about, but the fact is that like it's just a direct consequence of hydrodynamics that the fluctuations, the Hawking modes also should separate into slow and fast Hawking modes. And what we showed was that like indeed you can separate them, and you can integrate out the dynamics of the fast modes, both the fast like infalling modes and the Hawking modes, and write down some effective theory for like the slow infalling modes and the Hawking modes. Okay, and I will not kind of describe the details, but this is what we did. Like you can look at the paper or like Akhil's talk on Friday. So, but what I want to talk to you about, like over like rest of the time I have, is a simple scalar model which basically captures the essential features of what is happening without going into all the details about gauge fixing, Gauss constraints, and all these things. You can look at your paper. Okay, I mean you have to kind of do it in some clever way and separate things out in a clever way to get it working. But the point is that like I just want to talk to you about basically some simple scalar model where this fast mode slow mode separation and what happens there is kind of clearer. Okay, so maybe I will just pass here and ask like are there any questions, comments at this juncture?
So is the field theory a weakly coupled theory or a strongly coupled theory?
I want to do gravity, so it can't be a weakly coupled theory, right? I mean, classical gravity.
No, the dual theory.
That's what I'm saying. So the dual theory has to be strongly coupled to get a classical gravity. So
okay, it's a strongly coupled theory. Okay.
Yeah, and I want a strongly coupled theory because I want this fast slow separation. It's much cleaner in strongly coupled theories.
But for fluids, is it strongly coupled or weakly coupled?
Sorry, I don't understand the fluid modes. I mean.
Yeah, I mean, you're trying to address the fluid gravity correspondence, right? So ultimately, you're concerned with the fluid dynamics.
Yes, on gravity.
So is that
I'm also concerned about gravity.
Yeah, so is that a strongly coupled or a weakly coupled?
I'm not sure whether that distinction makes much sense. Fluid dynamics is an effective theory, okay, and in some sense, you know, the fluctuations in fluid dynamics are kind of suppressed. It's like a statistical theory. It is suppressed by 1 by n, and 1 by n is always small in fluid dynamics. So in some sense, okay, what I'm saying is that fluid dynamics by definition is always kind of weakly coupled, or else you don't have fluid dynamics or something. Because of this 1 by n, because the fluctuations to the mean behavior are always suppressed by some Avogadro number. So, yeah.
So the gravity would not apply here. The gravity.
Can we please undergo this discussion in the discussion session? And Loga, you have 5 minutes more.
Okay. Yeah. Right. Okay. So yeah. So yes. Maybe then I should proceed. I'll maybe, you know, like come back to it in the. Okay. So the point here is that, you know, like so let me take the scalar system and the question. So consider an ADS black brane with an ingoing iterative Finkelstein coordinates, and what you can do is that, you know, like so here B and X are the CFT coordinates, and you can write down a scalar system. This is basically like a Klein-Gordon equation, but a one parameter cousin of Klein-Gordon equation, and this one parameter is this m, which is an integer. So when m is d minus 1, okay, this is basically the Klein-Gordon equation in the ADS black brane. Okay, so you have a one parameter family of these scalars, and the basic claim here is that, you know, like by tuning this parameter m, you know, like we can make this phi m, you know, like represent a slow mode or a fast mode, and we can understand, you know, like how those slow modes and fast modes work in gravity by just studying these equations. Okay, so, you know, like so basically the idea is that, you know, like, yeah, there's a particular value of m for which you get a fast mode. For particular ranges of m, you get slow modes. Okay, and this might look like a kind of completely rigged up example, but many actual, you know, like systems of interest reduce to these things actually, and even like what I described, that, you know, the many Maxwell sectors and gravitational sectors actually reduce to such scalar equations, and more importantly, you know, like even if it doesn't reduce, I think it kind of captures something essential about how gravity treats these slow modes and fast modes, which I think is important. So the only fact we will need, you know, like today, is this statement. That the standard GKPW boundary condition, which frees the non-normalizable modes, reduced to Dirichlet boundary conditions on the fast modes and the normal boundary conditions on the slow modes. So in some sense, the gravity already knows about, you know, the fast modes and slow modes, and you get like the Dirichlet modes and Dirichlet boundary conditions and normal boundary conditions on the slow modes. And the main claim that I want to make, which we substantiate in detail in these works, is that the Wilsonian boundary condition, which means you should let the dynamics of the fast modes be whatever it is. So we just let it be Dirichlet boundary conditions, but we want to freeze the slow modes, right? You know, we want to freeze the dynamics of slow modes and take them off shell. And the statement is that, you know, like you can make them off shell by converting the normal boundary conditions on those slow modes to kind of Dirichlet boundary conditions, so that you impose Dirichlet boundary conditions on all the fast modes and the slow mode scalars. Okay, so the statement is that, you know, like the Wilsonian boundary conditions just amount to Dirichlet boundary conditions on this scalar system, on this phi. Okay, so for the want of time, let me just skip this slide. Okay, and let me just summarize, you know, like so for how, you know, like this system looks like from the gravitational side. So you have this mode, you know, like I have just divided into the case where there's a fast mode and case where there's slow mode. Here the pi is the conjugate field to the phi, okay, which you can write on an action and define canonical conjugate. Okay, and the point is this, that the GKPW boundary conditions, the standard non-normalizable mode boundary conditions, impose Dirichlet boundary conditions on the fast modes and normal boundary conditions on slow modes. And as I said, the Wilsonian boundary conditions amount to imposing Dirichlet boundary conditions on both of them. And this is also, you know, equivalent to the statement that that for the fast modes, okay, the force is the scalar itself, whereas like for the slow modes, the force should be thought of as the as the conjugate field, because like the GKPW boundary condition tells us that the non-normalizable mode should be fixed, and the non-normalizable mode actually sits in the conjugate field for these slow modes, okay, which is opposite of what happens in the usual ADS-CFT. And the point is that then you have to solve for this, okay. And the idea is that what we find is that you can always, for any m, you can solve the system by usual ADS-CFT things, in small omega k expansion, and you can always get a small omega k expansion for pi m, boundary value of pi m, in terms of the boundary value of phi m. Okay, so you can get like pi m equal to some omega square, k square, something times phi m in the Fourier domain. Okay, and what that means for the fast modes is that you have expressed the expectation value, okay, of this operator in terms of some local expression, some derivative expression in terms of the source, which kind of justifies the statement that it's fast modes, and it has very short correlations, and hence it can be derivative expanded. Whereas for slow modes, the same expansion should be interpreted in the opposite way. That what you have done is that you have expanded the source in terms of some derivatives acting on the expectation values. Okay, like of the operator. But what does that mean? That basically means that what you have written down is a dynamical equation for the expectation value, where you have said that some derivatives acting on the expectation value is equal to the force. Okay, and this is a characteristic of a slow mode. For example, if it's a diffusion equation, what you get is that in the terms of the source, you get a dynamical equation, right? Which if you solve it, you will get a very long-lived diffusion, which will take a long time, okay, depending on the wavelength. And if your source is very small, slowly varying, the solution will be as slowly varying as the source. Okay, so that's the point. Okay, the point is that so that's what we find, and this is how gravity basically implements this distinction between the fast modes and slow modes. It seems to take basically the same class of equations, and by just changing indices, you go from fast modes to slow modes. We also have examples in charge cases where sometimes this indices kind of changes as you kind of go into the bulk and so on and so forth. Okay, so there's if you're thinking about in terms of the scalar systems, actually it's a very useful thing. Okay, so since I'm kind of at the end of my time, let me just conclude with the summary and so on. Okay, so what I did was I presented I kind of showed you a scalar system, okay, which is much simpler than solving Einstein equations or Maxwell equations, like in the black-green background, which already shows this kind of a fast slow distinction, and in terms of which you can actually understand how the fast modes and slow modes work within the Wilsonian paradigm, and how they get separated within fluid dynamics. And one can so this is just solving free theory. You can start adding interactions, and we studied interactions in a paper 2 years ago, 1 year ago, and the point is to extend this and try to understand. One future direction is to extend this and understand how fast modes interact with slow modes and how they mix and so on and so forth, and it seems doable because of the separations. There are also other extensions where the slow mode can be some kind of a non-Fermi liquid and so on and so forth from a holographic side. But since I'm out of time, I will just leave this slide and just conclude here. So the basic idea, to just say in one sentence, is that there's a way to implement the Wilsonian strategy on the gravitational side by changing the boundary conditions, and you can do it at the scalar system and study it. Okay, so thank you.
Thank you very much, Loga. So we have time for a couple of questions. I don't see any hands raised, but you can unmute yourself and ask, or raise your hand.
Sunil, can I ask a small question?
Actually, Sachin just raised his hand.
Okay.
You can just ask, and then you. Yeah, Sachin.
Okay. Hello. So for you, it was very important to work at strong coupling so that you can actually separate out the scales. And for that, you went to gravity. But there are some models where in field theory, which are maybe exactly solvable models where you can look at strong coupling. And would you be able to do similar stuff there without using gravity?
Yeah, actually, like it would be good to have some kind of integrable models where, like this can be done. Okay. The point is that though a lot of so what you need is an integrable model, but which kind of thermalizes. Okay. Something like SYK or something, which are not easy to come by. I mean, solvable model, maybe not integrable, solvable models where, like you can capture. Because most solvable integrable models, they don't thermalize. They just have too many conserved quantities. And everything is just slow, and it doesn't help. It's as bad as the free theory, Okay. But it is possible that like with effort we can find some models, okay, some higher dimensional analog of SYK where you can study these things in some solvable way. That would be good.
Just one example. Suppose I take a 3D Chern-Simons matter theories. Those are at large n at least. Although the transport coefficient will be very, very suppressed 1/n, etc. But would that be a kind of, because there you can solve things, right?
Yeah, but you have a lot of higher spin conserved currents, which will all not let the system relax. Basically, okay. even if they're like only weakly even if they're like conserved only to a limited extent, already that it means that that's a problem even in free theory, right? Basically, like too many conserved quantities, and so the fast modes cannot decay fast enough. Okay, so you have to wait until this conservation goes out, and and fast modes decay, and that takes some non-perturbatively long time, and you are not in good shape.
Thanks. We can move on to Alok's question and then Sheshanshu, and then we'll stop. So Alok, please.
Yeah, Logan, hi. Just a small question. So if we, from the hydrodynamics perspective, if you look at in your Wilsonian paradigm, if you look at some collective excitation, then is there a bulk? I don't know if there's a bulk bulk understanding of collective excitation of slow-moving modes. I mean,
well, so basically, what happens? This is the thing. How gravity separates the weakly coupled and slow and the fast modes is that basically, like you have these modes which are falling directly into the black hole, okay, and they die down, okay. Yes. Then there are modes which hover around, okay, and then they last long, and in some sense, the collective modes are the modes that hover around somehow.
Okay.
Okay. I see. So that seems to be how the gravity geometrizes this stuff.
Okay, thank you.
Okay, let's move on to Sheshanshu. Please ask your question.
Hi, can you hear me?
Yes.
Yes.
Okay. So you said that you can see the Pauli exclusion principle from the gravity side. Can you please say a quick word on that?
Yeah. So what happens is that, okay, I will just say 2-3 words, but you can just look at these references. Okay, so what happens is that you can kind of, replace this black hole by some kind of a, like what is called, some kind of a gravitational Schwinger-Kelvin geometry, some kind of instanton. And what we see is that, like you basically, in that way of looking at it, you kind of have two exteriors of the black holes. And what you look at for these kind of factors to come in is how, when you kind of throw in stuff from one side, how things come out of the other side. Okay, and when you compute this scattering thing, you see that the fermions come with an extra phase, which exactly then like implements the Pauli exclusion. That's a short answer. Okay, but maybe yeah, you can look at Akhil's talk and like where like he probably described this geometry and so on and so forth and how this thing works. Or you can look at these references that I have just given.
Okay, thanks, Loga. We have to move on now. So if you can, thank you again for a very nice talk. If you can unshare your screen. The next speaker is Debajyoti Sarkar from IIT Indore. Debajyoti, are you there and can you share your screen?
Yeah, hold on one second.
Very good.
Is it visible?
Yes,
Yeah.
please start.
I guess this is better.
Yes, fine. Please start.
Okay, yeah. So, yeah, thanks, Sunil, and thanks to the organizers for having me here and arranging this very nice conference. What I'm going to talk about is based on these two papers and some ongoing works with 𝗬𝗀𝗀𝗀, Lifshitz, and Fuchs. And in this paper, in this talk, what I'm going to mainly talk about is some ideas from quantum information theory and their applications in field theory in particular. And some of the quantities that I'll be dealing with is density matrices and the corresponding modular Hamiltonians. So I will have in mind the usual, you have some system in some pure state psi, and then you divide the system into two subsystems like A and A complement, A bar, and correspondingly you have the density matrices and the corresponding modular Hamiltonians. Now, actually, one of the important point of this talk will be the fact that these types of bipartitions of a system into some subregion and its complement is actually a bit imprecise in quantum field theory. And correspondingly, these operators like subregion modular Hamiltonians, HA or for HA bar, these are not very well defined in field theory due to UV divergences and so on. And in fact, a better defined quantity is the so-called extended modular Hamiltonians, which is defined like this. And in this talk, I will mostly compute these modular Hamiltonians and associated this extended modular Hamiltonian H for some excited state. And that excited state will be obtained by perturbing some modular Hamiltonian of a known state. So in particular, perturbing the vacuum state by some unitary operator G. So in terms of equations, we know some vacuum state we have in field theory. Suppose we know the corresponding vacuum state modular Hamiltonians. Let me call it H0. I will have some equations in a moment. And I go to some excited state by acting with some unitary operator. The operator looks like this. It has some Hermitian, local Hermitian operator smeared over some space-like or null hypersurface, this sigma, and with some support function f of x. And I will study what will happen to this corresponding modular Hamiltonian in this excited state. And then, we will also have some perturbative expansion parameter epsilon. And in some cases, we know the results exactly. And in some cases, we'll only know the results to the first order perturbation in epsilon. Because in general, finding out, excited state modular Hamiltonians, it's actually a very tough problem. So the framework in our case will be a field theory in arbitrary d dimensions, and we'll compute this modular Hamiltonian delta HA to first order in perturbations, as I said. And for most part, our subregion will be Rindler half space. And these are all these assumptions or these restrictions are put in place because otherwise it gets a bit difficult to compute it. I talked about this HA bar being a bit imprecise and having H being the better defined thing in quantum field theory, and it has to do with non-factorizability of Hilbert space. And it actually shows up in an interesting way in this excited state modular Hamiltonian. We'll provide a general form of this change in excited state modular Hamiltonian. So as you go from the vacuum state counterpart to the excited state counterpart for perturbations by some arbitrary modular weight n operator Jn. So this O is Jn. Whereby modular weight, I would mean that if you study the modular flow of these operators, of these Jn x's, so modular flow by vacuum state modular Hamiltonian H0, it's defined like this. And because, in our calculation, mostly this will be a Rindler half space,
then these modular Hamiltonians are boost generators. And if the operator is modular weight n, then under this particular modular flow, it will transform like this. So in a sense, basically n will count the number of plus indices minus the number of minus indices for the J operator. And in fact, a good amount of work has been done on this problem. I mean, as you can see, there are papers starting from 2015, maybe even before. And in most of these in these papers, the expressions are quite abstract and formal. And in fact, I'll be using a paper result from Suresh Govindarajan, who has some formal expression given, you have some ground state to excited state transition, and there is a change in the corresponding density matrix. So there is a delta rho, and they gave an expression which connects the change in rho, this delta rho, with the change in the modular Hamiltonians delta H. So we'll be using that, in fact. But what we have in addition to that is that we kind of distinguish between origins of various contributions to this delta H. And that's where we'll see that there are some surprising results. And also, most of these papers talked about stress tensor perturbations to the states, and the generalization to arbitrary n was mostly absent. And in fact, similar results also appear for stress tensor perturbations in these papers, where people studied modular Hamiltonians under shape deformation. So what they had in mind is that you have some subregion and you deform the subregion a little bit, and how does the modular Hamiltonian change, which you can think of in terms of the state being perturbed by the stress tensor. Now, before going to the meat of the calculations, let me say a few general things about what our expectations are or could be, and what the results that we find, and what are the kind of surprises and new things. So, if you have some perturbation over some spatial slice, and suppose you could factor out the spatial slice or partition this spatial slice in A union A bar, then that will imply that the perturbation that you are providing is also factored out in this form, like GA tensor, some identity plus identity acting on the A region tensor GA bar. And since GA and GA bar commute, this is some space-like slice, it would seem that the corresponding unitary transformations also factor, like U equals to UA tensor UA bar. And then it's like a one-line exercise to show that the corresponding reduced density matrices, modular operators, which are defined like this, which are in fact better defined quantity in field theory, they transform in this fashion. So, if you have U, some transformation unitary operator UA tensor UA bar, it factorizes between A and A bar, then rho A goes to this, rho A bar goes to this. And as a result, the modular operator delta goes to this, and the modular Hamiltonian also transforms in this fashion. So you just take the modular Hamiltonian of the, let's say, the two-sided modular Hamiltonian, this H double arrow here of the vacuum state, and you just do U H naught U dagger, and you get the excited state modular Hamiltonian. And this is, I mean, in all these lines, in all these steps, there are no assumptions except for the fact that the spatial slice has this bipartition A union A bar, and as a result G looks like this. But if this is true, then the first order change in the modular Hamiltonian would then be given by this commutator term. Now I'm particularly talking about the first order change because as I said, I will have some other methods to compute it, and there will only be considering the first order changes, because going to higher order sometimes are pretty difficult. So in any case, this is the exact result in that case, in this case. And in this case, the first order change will be like this commutator piece. And throughout this talk, whenever I say delta H commutator, I'll mean such a commutator piece at the first order. And then in the second order, it will be double commutator and so on and so forth. But it is actually only true, as we'll see, in the discrete systems, and it doesn't hold for QFTs. And in fact, there is an explicit, what I'll call an endpoint contribution, which arises from the surface separating the two subregions A and A bar. Okay, so in fact, we will find that delta H is not just delta H commutator, but an extra piece. To first order, I'll call it delta H endpoint. And in fact, you can call delta H endpoint anything which is not a commutator piece. And these are our results. We'll see that this endpoint contribution vanishes for certain perturbations, especially for perturbations with modular weights -1, 0, and 1. And if you have perturbations by stress tensor, which is modular weight 2, n equals to 2 or 3, 4, etc., we have only studied integer modular weights, then the corresponding endpoint perturbation exists. It's a non-zero quantity, and it goes like this. So the total delta H is delta H commutator, which we'll expect, plus this quantity. And this quantity is interesting for several reasons. But first of all, I should mention that these quantities have been studied in literature. These are known as light ray operators. And in particular, here we also have moments of light ray operators. So basically, you see that as the endpoint piece, we have these perturbing operator Jn and their descendants. And they are integrated over x plus horizon for positive modular weight, and there is a similar result for negative modular weight, where the endpoint contribution will be a light ray operator over the x minus horizon. And then there are also quantities which appear here, which is fk0. So remember that in G, if you remember from few slides ago, there were the support function f of x. And if the support function is non-zero and the derivatives are non-zero, they will actually appear and make this delta H endpoint non-zero. And then I also have this theta parameter here, which basically tells me the location of this space-like slice sigma, how much it is tilted from the x plus horizon, because it's a space-like slice for now what I'm considering. I'll have some picture in a few slides. Okay. So this is the main result that I want to convey, that you get light ray operators and their moments, these various moments with k and l exponents going, taking these types of values. The simplest example is a stress tensor perturbation in CFT2, in which case, if you evaluate this quantity, it will be the so-called NX operator, which is basically the stress tensor integrated over the x plus horizon. Okay, so this is the result. By the way, feel free to ask me questions at any point of time, or we can just defer to the end of the talk. But having said all this, the results, let me now go back to a very simple case, especially for the case of stress tensor perturbation, where we can compute these quantities in a very simple and alternative way. And then I will talk about a more general way of computing this. So just to, make sure that I'm not being crazy, and you can see these calculations, these quantities arising very easily, or in a very well-defined setting rather. So I'll have in mind some CFT2 vacuum perturbed by stress tensor. There, for any even finite region, you don't even have to go to Rindler subregions. For any region U2V, the vacuum state modular Hamiltonian the expression is well known. And you can go to this excited state that I was considering by doing a conformal transformation Z to G of Z, some local conformal transformation to change the state. And you can, in fact, compute then what is the corresponding excited state modular Hamiltonians by just implementing this resulting conformal transformation in this equation. And the result turns out to be this. And to kind of touch base with the results I showed, we can take G of Z, this transformation, this conformal transformation, to first order epsilon as this. Sorry?
Shouldn't there be a Jacobian factor in the HUV compared to, because the measure should have a Jacobian factor, right?
Yeah, so you have some G prime of Z arising from there.
Okay.
Yeah. So we'll be interested in this linearized perturbation to, kind of match with the results I showed you before, the general result. And that will actually correspond to perturbation by stress tensor with this generator. The G, capital G, is the capital G I showed you before for stress tensor perturbation. And then, so you can, readily compute it. You just plug in this value of G of Z in here in this equation, and then you just expand to first order in epsilon, and the result is this. So the first order in epsilon is, of course, the leading order, the epsilon to the 0 order result is, of course, H0 UV. So the change in H, the H UV minus H0 UV is given to first order in epsilon by this quantity, what I have on the second line. Now, this is interesting because the first line only is the commutator contribution, which you can explicitly check because you can use TT commutator relations and you can compute minus epsilon g comma H0, and that will give you this first line. But the second line, you see, it vanishes if the support function were 0 at the endpoint. But in general, in QFT, it is not 0, right? Because the perturbation is all over the place from some, from across the endpoint. Some, if it is from U to V, so somewhere from less than U to greater than U, and if to V, then somewhere from less than V to greater than V. So this second line is the endpoint contribution, and it will vanish if it were so that FU and FV are 0. Okay, so in that case, of course, I can also actually bipartite the two systems as A union A bar, for the Rindler cases, for example. And you can also make contact with the Rindler results. So we have done it here. So you can zoom in on the endpoints by choosing some f of x, which looks like this. So we have assumed that, so this is one of the endpoints, this crosshair here. And we have assumed that this support function is constant across this endpoint. Doesn't matter if it's not constant, but here for simplicity, I've considered it to be constant. So f of x is of this form. And then if you go to the Rindler Hamiltonian case, which corresponds to some 0 to infinity subregion, so you put u equals to 0 and v to infinity, then you get this result. And then if you take a to b 0, a and b to 0, so a and b was some two very small separated regions across the endpoint. So the perturbation were straddling the endpoint. So only after computing this, I want to take that, the support of f to 0. And then you see that some non-zero piece is remaining. And this non-zero piece is precisely this NX operator that I was talking about before. Okay, so to begin with, if you naively thought that, okay, if A and B is 0, then it's, there is no perturbation there, and then everything vanishes. So there is no contribution of delta H coming from there, but that's actually not true if you do it properly. So this is, this is the very straightforward calculation, and it already shows you that indeed, if you just considered sigma as a union A bar, then you would be missing something in field theories.
Debajyoti, you have 5 minutes. Is that okay?
Yeah, I'll try my best. Okay, so I'll now try to derive this delta H in a general operator method. So, not for all operator perturbations, you will have this conformal transformation techniques. So I'll start with this vacuum state. I'll write it in this Smith decomposition form. From there, you can calculate rho A naught and rho A bar naught. And then we go to some excited state excited by these types of operators. So G is GA tensor GA bar, where GA tensor GA bar form is a more general case of what I was considering before, which was GA plus times identity plus identity times GA bar. And then you can get some expression of delta rho A, not important. Let's move on. Then you can actually simplify this result quite a bit by using something known as modular conjugated operator. So for Rindler subregion, this J becomes CPT. So in general, this J appears in Tomita-Takesaki modular theory, where if you know about this Tomita operator S, you can decompose as J delta to the half, where delta is the modular operator and J is the modular conjugation operator. But for Rindler, it's a CPT conjugate. So in terms of this GA bar tilde, which is the modular conjugate operator of this perturbation, which working on GA bar, you can write down delta rho A in this form. And as you can see, this delta rho is already not in the form of a commutator like GA comma rho A naught because of this GA bar piece. And then we use the Sarosiu-Gajin formula. This is the formula which relates delta rho A with delta HA. So the delta HA is given by almost a modular flow of delta rho A, the change in the density matrix as you went from one state to another. And basically what we will do, we'll substitute this expression in here. So that's what we did here. And basically, it can be written in this simple form by, realizing that the modular float operator, any operator at some modular parameter value S is defined by this quantity. So we'll be coming back to this expression for what we are doing next. So we'll have to identify what is G and what is G bar, and then implement it here. So now, so this is the most general case. So you have some space-like perturbation over this blue slice here. And here, naively, what we'll do is that acts from 0 to A, and by G bar, we'll define the perturbation which acts from 0 to minus B by some operator Jn with some support function f of x, as we discussed before. And the point is that we'll have to then be very careful about what goes on at the endpoint to actually extract the result. And then if you plug this G and G bar back into this Sarosiv-Gajin formula, what you will get is this. So there are many things that are important. For example, there are in the Sarosiv-Gajin formula, you will have a situation where the modular flow is by some imaginary modular parameter. And you also have this G bar tilde pieces, which you have to take care of. So for example, to take care of this imaginary modular flow, we have defined it to some imaginary value S minus IR, and then have taken from R equal to 0 to pi. So that helps us keep track of things. And for concreteness, we'll study this delta HA inside a correlation function of J and Y. And only in conjugation of that, in fact, we'll see that as you go to large modular parameter values, S going to plus minus infinity, or if you define W as e to the minus S for W equal to 0 and infinity, they have well-defined correlators. So basically, our goal will be to study the correlators of this type. So for concreteness, we will consider some CFT primaries as Jn, and so that we can write down these correlators. And we'll have various branch cuts in these correlators. And these branch cuts will look like this in this W plane. So now we are going from S to this W plane by e to the minus S is W. And in this W plane, the branch cuts will look like this. And all you have to do is to do this W equal to 0 to infinity integral here, this W equal to 0 to infinity integral here, keeping track of all those branch cuts and the rotation of the branch cuts as you take the modular flow in this S minus IR R from 0 to pi. Okay, so once you do that, the contour prescription will look like this. And basically, this will be your expression. And then you can hope to strip off this J and Y and to obtain the expression of delta H. And then I will just simply tell you the results because I'm out of time. So if the perturbations were acting on the A region alone, so that the A bar was, there were no perturbation in A bar at all, then the contour prescription will look like this. And there is also a pole at -1. So if you can do these integrals. In fact, what happens is that in these correlators, you can actually, due to this property, which I very briefly mentioned, you can actually close the contour at 0 and infinity. So because these are closed contours with a minus sign, you can actually enclose this -1 pole, and that gives you the commutator contribution here. On the other hand, if the perturbation was only acting on A bar, then all the branch cuts will be in this direction and the contours will not include anything, and it will give you 0. And this is exactly what you will expect, because if the perturbation is in A alone, there is no endpoint contribution and it will be the commutator piece. And if it is on the A bar alone, then the change in delta HA will just be 0, because you are not perturbing in the A region. And then if the perturbation straddles the endpoint, the calculation gets a bit trickier. I'll not bore you with the details, most importantly because I don't have time, but let me just show you the final results. Basically, the final result will look like what I showed you in the beginning. That in the discussion sections, if I am given the chance, or if you ask, I can go back and show you the calculations. But basically, the quantity that we are looking for here. Sorry, 1 second. So in this case, delta HA, if I write it as fx plus ix plus, then after some careful calculations, you can calculate this ix plus as this quantity. So the Ix plus gives you some commutator piece for the far away from the endpoint case, and some piece which is precisely what I advertised before, which are the moments of light ray operators. So the takeaways is basically, I have only 2-3 slides left, so I'll be very quick. The takeaways are that for a generic perturbations like this, the endpoint contributions are given by these light ray moments. And in fact, these light ray moments satisfy precisely the some of the properties that we wanted to satisfy. For example, if you just look at the generic properties of modular Hamiltonians, you can show that the modular Hamiltonian of any state actually annihilate the states. So if you apply H acting on psi equals to 0 and expand it to first order in epsilon, you can show that you get the delta H endpoint. If you define delta H as commutator plus the endpoint piece, then you can show that the delta H endpoint should annihilate the vacuum state. And precisely these these light ray moments are such that we are getting light ray moments of that many order that actually has the property that it annihilates the vacuum state. So everything seems to work out properly. So yeah, I think I'm over time, or maybe done with the time. So I'll just flash the future directions, that there are many things. We have actually more questions than we have answers. For example, for most cases, I considered Indlers, but what happens for finite subregions, something that can be done for time-like perturbations or higher order contributions. One can ask that, okay, for these NX operators, you have a statement of positivity, whether that also goes through for these light ray moments. We were interested in this from bulk reconstruction perspective, because there is a modular Hamiltonian way of doing bulk reconstruction. So we wanted to do it for excited state. So these are all some future questions. And with that, I thank you.
Thank you very much, Debajyoti. So we have time for 1 or 2 questions.
Yes.
Somdat has his hand up. Somdat, you can go ahead.
So when you are talking about zero state Hamiltonian and excited state Hamiltonian, what do you exactly mean? Because
I had in mind only vacuum state as the zero state, and the excited states are perturbatively close to the vacuum state. So if I can go back to very briefly to my this initial slides. So this is what I had in mind. So for vacuum state, I know what my modular Hamiltonians are for Indler subregions, and I used that and this ideas of modular flows to find out some modular Hamiltonians to this excited state.
Okay. No. Are there any more questions? Okay, if not, then let's thank Debajyoti. So you can unshare your screen now. The next speaker is Karunava Sil from IIT Bhubaneswar. Karunava, are you there?
Yes, can you hear me?
Yes, and you can share your screen now. Yeah, we hear you. Very good. So Karunava will now speak on pole skipping and chaos in anisotropic plasma, and he's from IIT Bhubaneswar. Please
okay, thank you. So I'd like to start by thanking the organizers for this opportunity. So today I'll be going to speak about this recently observed phenomena known as the pole skipping and its relation to many-body chaos for an anisotropic theory. So this is based on this paper. Recent papers. Okay, so that this is the outline. So my talk will be mostly in 2 parts, 2 main parts. So after a brief introduction, in the first part, I will try to discuss in some details the basic idea behind this pole skipping phenomena. And then in the second part, I will show some calculations of these pole skipping points for this anisotropic theory, and then I will summarize. Okay, so recently there has been a growing interest in the study of quantum chaos in many-body system. In particular, many interesting insights into quantum chaos has been developed, especially in the context of black hole physics. So, so for quantum system, we usually we usually diagnose the chaotic behavior by this certain out of time ordered correlation function. So this is first observed by Larkin and Ovchinnikov, and then further developed by Maldacena, Shenker, and Stanford. So the out of time ordered correlation function is given by this following thermal expectation value of this double commutator involving two generic operators W and V. And this commutator basically captures the effect of any early perturbation V at T0 and X0 to some later measurement W at some time T. Now, for a large class of system, including the holographic system, it is observed that this OTOC actually grows exponentially with some overall rate lambda L, which is known as the Lyapunov exponent. And also the growth rate also depends on another parameter called the butterfly velocity VB. And this butterfly velocity is actually computes the speed of the correlation in space. So now, yeah, so Maldacena, Shenker, and Stanford also observed that there is an upper bound in the Lyapunov exponent, which is in natural units equal to 2 pi by beta, and for maximally chaotic system, this bound actually saturates. Now, this computation of OTOC in some cases is not that easy to evaluate, especially at finite temperature. So on the other hand, the phenomena of pole skipping actually provides an easier and also efficient way to calculate the parameters of chaos, namely the butterfly velocity and the Lyapunov exponent. And also, as I will also explain, so you just need to do near horizon analysis of linearized Einstein's equation to get those parameters. Okay, so this is let me now discuss the basic idea behind this phenomenon. So what these authors, namely Blake, Lee, Liu, and also Grozdanov and collaborators, they have shown that, or they have realized that in addition to OTOC, one can also realize the chaotic behavior in many body system from at the level of energy density 2-point function. And in other words, this exponential growth of the OTOC has this manifestation in the energy density retarded Green's function, such that the quasi-normal modes for collective excitations has a direct relation with these parameters of chaos, mainly lambda, the Lyapunov exponent and the butterfly velocity, through this kind of relation. So these special points, or in the complex omega, on the complex frequency and momentum plane, actually what happens that at this special complex values, which are related to lambda L and VB, so the retarded Green's function, the energy density retarded Green's function, fails to be defined uniquely. So this, of course, I will explain in detail later. So this phenomena actually first observed by these authors, Blake, Lee, and Liu, for an effective field theory, a general effective field theory of chaos. And what these authors have shown that the exponential behavior actually originates from these interactions between interaction and propagation of hydrodynamic modes for energy conservation. Okay, so now this phenomena is an universal feature of any general holographic system. So the primary motivation to calculate the pole scale, to study this phenomena for this anisotropic plasma, actually just to show a greater generality of this phenomena for a large class of holographic system. Okay, so let's see what happens to this energy density Green's function at these special points. So these authors, Blake, Davison, Grozdanov, and also Hong Liu, they have shown that that the line of poles of the energy density retarded Green's function and also the line of zeros of this quantity actually process each other, pass through each other at right exactly at this special values of W and Q. and that are related to the parameters of chaos. So what happens that at these special points W and Q, the retarded Green's function actually takes this 0 by 0 form, and hence it is not well defined, or it is not uniquely defined at this point. So let's try to understand the at least the gravitational origin of this non-uniqueness of this retarded Green's function with this simplest example of a scalar field psi. So we know that a general solution of the scalar field propagating in an appropriate background at the near the boundary, which is at r equals to infinity, has this general form. So it consists of two modes. One is the non-normalizable mode, and the other one is the normalizable mode. And following the prescription as given by Son and Sarinets, the retarded Green's function is defined as the ratio of psi b to psi a. Now, for generic values of W and Q, once we impose the ingoing boundary condition near the horizon, psi b and psi a, this ratio is fixed exactly, and hence the retarded Green's function can be defined uniquely. However, at the special values of W and Q, what happens is that there exists one extra ingoing solution near the horizon. Okay, so we now have, instead of one, we now have two independent solution near the horizon which are ingoing, and hence the psi a and psi b now can take arbitrary values. Moreover, now we can take linear combinations of these two independent solutions, and we can construct a particular linear combination such that there is only this psi a is 0, okay, which corresponds to the pole of this retarded Green's function. And also we can construct some other combination, linear combinations, such that this time psi b is 0, which corresponds to the zeros of this retarded Green's function. So that means at this special values of W and Q, this retarded Green's function have this 0 over 0 form. So this is the reason for this non-uniqueness of the retarded Green's function. So now let's see with this example of a scalar field, the existence of an extra ingoing solution near the horizon. So for this, we consider this action of a scalar field, a massive scalar field, which is propagating in a planar ADS black hole solutions. The metric is written in terms of this ingoing Eddington-Finkelstein coordinate, because we are doing a near horizon analysis. So which is defined as this, where r star is the tortoise coordinate. And so what we'll do is that we'll write the ansatz for this scalar field as this form, where W is the frequency and Q is the momentum, and such that the equation of motion for this scalar field can be written in this form. And now we take this ansatz for this solution psi near the horizon at this form r minus r raised to the power alpha, and we realize that this alpha, the exponent alpha, can take two possible values. One is alpha 1 equals to 0, and the other one is alpha 2 equals to I omega by 2 pi t, so where t is basically the Hawking temperature. So for any generic values of W, there is only one solution which is regular near the horizon, namely alpha 1 equals to 0. However, if you consider these special values of W in the lower half of this complex plane, namely minus 2I by t times n, where n is some positive integer, then you find that the other exponent alpha 2 is equal to n, which is a positive integer, and hence both alpha 1 and alpha 2 are now regular near the horizon. Now, moving to the gravitational perturbations. Now, because in this case we now have multiple components of the metric perturbation delta G mu nu, so things are a little complicated in this case, but the essence is basically the same. So what happens is that in this case, so we first write the perturbation in this expansion, Taylor series expansion near the horizon, and what will happen is that this time what will happen is that at the special point, at the special value of W and Q, the VB component. So we are writing this, we are writing everything in terms of ingoing Einstein, Eddington-Finkelstein coordinate. So what will happen is that our VB component, only the VB component of the Einstein's equation this time will be trivial at the special values of W and Q. So writing the VB component of the Einstein's equation with this general form, where we have F, G, and H, some function of W and Q. So what will happen is that at the special value of W and Q, all these three functions, F, G, and H, will be exactly 0, and hence this equation will be trivially satisfied. So now the consequence is that we now have only a few equation, one less equation to solve, and that means that we have one extra ingoing modes near the horizon, just like the scalar field case. Okay, so this concludes the discussion about the basic idea of pole skipping. Now I'll go to this computation of pole skipping points for this anisotropic theory. So, okay, so first I will start with the very small discussion about this anisotropic theory. So this is basically a supergravity solution, which is first given by Matthias and Tranquinelli, and this is dual to this strongly coupled superangles theory at finite temperature with anisotropy along a spatial direction. So now this is the 5-dimensional action which involves the metric, dilaton, and the axion fields, and the solution can be realized by this metric, where the anisotropy is considered along the x1 directions, and here we define the anisotropy parameter by this small letter a, and also we assume that the anisotropy is weak, such that this dimensionless ratio a over t is very, very less than 1, where t is the Hawking temperature, which is again can be calculated up to quadratic order in a, and it is given by this expression. So let's see the pole skipping points for the pole skipping phenomena for scalar field. So this is the equation of motion which one can get by varying the above action, and then we consider linear perturbations to the to this field, and the perturbation can be written in this plane wave form, where we consider the momentum to propagate along the direction of anisotropy, which is x1, such that using these answers one can write this equation, rewrite this equation in this form, where s1, s2, s1 tilde and s2 tilde are some function of w, q, r, and rh, and one can see the appearance of this anisotropy parameter in the equation of motion, where we kept terms up to quadratic order in A. So okay, so now we have to do the near horizon analysis, and for that we write the scalar field in this form near the Taylor expand form near the horizon, and we just substitute back into the equation, and then again we do the near horizon expansion, and at lowest order near the horizon we get this equation. Okay, so here psi naught and phi naught and phi 1 are basically the components of zeroth order and linear order term in the near horizon analysis of this scalar field. So now this equation will be trivially satisfied if the coefficient of both phi naught and phi 1 are 0, and by doing so we get this result. So this is the frequency w, and this is the wave vector q1 square. So these are basically the spatial values or the pole skipping points at first order. These are the first order pole skipping points, and at this spatial values this equation will be trivially satisfied. Now, so this analysis can be extended to include the pole skip, or to calculate the pole skipping points which are appearing at higher order in near horizon expansion, and the analysis is more or less the same, so I'll not go into the details and I'll show the final result. So So here, the vertical axis is basically the imaginary momentum, imaginary frequency, and the horizontal axis is the imaginary momentum. And these are the points or the places where the pole skipping phenomenon is occurring. So this is basically the first order points, and this is the second order and the third, and so on. So one thing to note that that in this example for scalar field, all the pole skipping points are appearing in the lower half of the complex plane, and so these are not particularly related to the chaos. Okay. On the other hand, pole skipping points which are appearing in the upper half of the complex plane will be related to the phenomenon of chaos, and that will happen for the energy density Green's function, and which I am now going to discuss. Okay, so the pole skipping energy density Green's function. So for this case, we need to consider the linearized perturbation of the metric, the scalar field, and the axion. And now we consider the first, in the first case, we consider the perturbation to propagate along the direction of anisotropy, which is x1, so that the non-zero component of the metric perturbations are this in the ingoing coordinate. And then we do the same near horizon analysis. We first write down the perturbation in this Taylor series expansion, such that this time the VB component of the Einstein's equation at the lowest order is written as this. Okay. Now this equation will be trivially satisfied for this particular values of W and Q. Now you can see that the pole skipping is now occurring at the upper half of this complex plane, and now we can from this pole skipping points we can obtain the Lyapunov exponent and the butterfly expression for Lyapunov exponent and the butterfly velocity, which are given by this. Okay, so now, okay, so the Lyapunov exponent actually saturates the chaos bound. It's equal to 2 pi t. However, the butterfly velocity actually receives the corrections due to the anisotropy parameter, which is B. So B is basically the dimensionless anisotropy parameter.
Karunava, you have 5 minutes.
Oh, okay. Okay, thank you. So now let me discuss what happens when we consider the perturbation along the x2 directions. Again, the analysis is the same, and again the butterfly velocity is given. Actually, only the butterfly velocity receives the corrections due to the spatial anisotropy, and the Lyapunov exponent again saturates the chaos bound. Okay, so now so I will show by some explicit numerical calculations that the dispersion relation for transverse momentum diffusion actually constrained to pass through these pole skipping points in the complex plane. Okay, so basically the dispersion relation that arises from the pole structure of retarded Green's function. So for this case, because we are considering the transverse momentum directions, so we consider this particular component of this retarded Green's function, and we'll show that the dispersion relation is actually constant to pass through this pole skipping point. So in this case, we assume again the perturbation to propagate along the anisotropy direction x1, and with this the non-zero components for this metric perturbations will be only these two, htx2 and hx1x2. And now we can take a particular combinations of these perturbations such that now you can construct a gauge invariant variable ZV, and the linearized Einstein's equation can be written in a closed form involving this gauge invariant variable ZV, where all these are functions of W, this R tilde, S and S tilde are function of W and Q, and V is again the anisotropy parameter. Now to get this, to determine this dispersion relation, we need to solve for the pole of this retarded Green's function, and that can be done numerically using the prescription by Koptun and Sorinets. And so one needs to first impose, one needs to first write the solution as this following power series expansion, and then one needs to impose the Dirichlet boundary condition at the boundary, which is at u equals to 0. Okay, and so this equation has to be solved numerically to get the position of these poles. And so in this figure, so these blue points are basically the poles in the complex plane, and so this is basically the exact dispersion relations. If you follow these poles, so this is basically the exact dispersion relations, and the poles keeping points are basically these points where the vertical dashed and the vertical horizontal lines crosses each other, and one can see that this dispersion relation exactly passes through the first three poles keeping points. So here I have shown only the first three poles keeping points. This is the at order 1, and this is at order 2, and this is order 3. And also you expect that this will also pass through the higher order poles keeping points as well. And this computation is done with the particular value of this anisotropic parameter, which is equal to 0.5. Okay, so now let me summarize. So the phenomenon of pole skipping is basically an universal feature for a large class of holographic theories. And so this particular example of anisotropic parameter is just to support this comment. And the gravitational origin of this phenomena can be realized from the near horizon behavior of the linearized Einstein's equation. Also, we have shown that this pole skipping occurring in the upper half complex plane is related to the energy, to the parameters of chaos. Only the upper half planes pole skipping points, and also the Lyapunov exponent saturates the chaos bound, and only the butterfly velocity receives the corrections due to the spatial anisotropy. Okay, so yeah, that's it. So I just like to mention that currently me with Sandeep, who is a PhD student here at IIT Roorkee, we are actually trying to see this phenomena for a little string, gravity dual of little string theory, which is basically has this inherent non-local behavior. So we are trying to see the effect of non-locality to this pole skipping points. So yeah, thank you. That's it.
Thank you, Karunava. Thank you for keeping to time. So Loga has his hand up. Loga, please go ahead.
Hello.
Yeah.
Hi, Karunava. So one slightly, general question about this pole skipping.
Yeah.
So this particular thing that there's a place where there's a 0 in the numerator and denominator.
Yeah.
Am I audible?
Yes.
Okay. That there is a common 0. Like, why do we expect that this will survive? Let us say if you add in interactions. Let's say you calculated the 2-point function with some interactions in the bulk. Like why do you think this will survive? Why is this not just an artifact of just solving, linearized equations and so on?
So, okay. No. So you by interaction, do you mean matter fields? Adding matter fields?
Yeah. Let us say, like for example, there's some loop correction, right? Or something else. So there may be some T-level corrections. There may be some loop corrections. Let's say 2.
Yeah. So actually, this has been. Yeah. Actually, so people have done that actually. So that's why this is a very general feature of this, at least for holographic theories. So for a large class of systems, including these interactions and all these higher derivative corrections, you can also add some stringy corrections. Also, you can add different matter fields. And for all these backgrounds, people have shown that this phenomena actually is.
Okay. Yeah, I'm not like. Do you know who has done these calculations?
Yes. So this MIT group. So this basically Hong, Liu, Mike, Blake, and also Saso Grozdanov. Yeah.
Yeah, I'm not sure that they did loop corrections, but okay. So second question, and then I'll just end. So there was a paper that Hong and his collaborators wrote in this year. Hong and Blake, basically, Hong Liu and Mike Blake.
Yeah.
Where they were saying something like this pole skipping really works only when the Lyapunov exponent is maximal, unless I misunderstood that statement. Do you have any?
Yes. So I understand the question. So for the maximally chaotic system, actually this has been we have this result. But if you go away from the maximally chaotic system, maximal chaos, so this is actually done by this Mark Meji and Sarosi, all this and the collaborators. That suppose they have the example they took is basically the SYK chain with a large charge SYK chain. So where they have there is a coupling term and that can be tuned. So whenever they are going away from the maximally chaotic region, then this phenomena seems to. So it is basically giving the same answer. The Lyapunov exponent is actually saturating the chaos bound, which should not. So that's why they have, in the recent paper, they have proposed a new proposal for this phenomena, but it is just a proposal. It has not been proved. So, yeah. So where they have mentioned that the Lyapunov exponent and the butterfly velocity in that proposal, so that will be replaced by the Lyapunov exponent and the butterfly velocity, the contribution from the stress energy tensor. So only the contribution from the stress energy tensor to the Lyapunov exponent and the butterfly velocity will be important. But this is just a proposal and it is not approved.
Okay, there's a question from the ICTS room, I guess. Please go ahead. It's unmuted, but we still aren't hearing anyone. I can't hear anything. I don't know if anyone is speaking there. Now it's muted, showing as muted. If you still have a question, please try to unmute and ask. Does anyone hear anything? Is it only me? Karunava, you're not hearing anything, are you?
No.
Okay. I think then, since in view of time shortage, we will move on. And ICTS, please, you can get back to us and ask the question later on. So, yeah, you can ask the question here and we'll bring it in the discussion session. All right. So very good. Are there any other questions for Karunava? Okay. If not, then we'll move on to the next and last speaker of this session, although it's not the end of the day by any means. So the last speaker of this session is Zohar Komargodski from Stony Brook University. And Zohar will be talking about line defects and RG flows. So Zohar, are you there? We don't hear you yet. Zohar, you're still muted. Audio is muted.
Yes. Hi, everybody.
Now you're unmuted. Very good.
Hello, everybody. Thanks so much.
Hello. Welcome. Great to have you here. Please start.
Thanks so much for this opportunity to talk. And I also managed to catch a few of the previous talks, which was very nice. My talk will be about line operators or line defects, renormalization group flows, and magnets. This is based on several papers. One already appeared in the end of the summer. One will appear probably tomorrow or the day after. And then there is some work in progress that I will only barely mention. I was told that I can be interrupted with questions during the talk or at the end. Either way, it's fine with me. So please interrupt me if there are any questions. So the subject of line operators or line defects in quantum many-body systems or quantum field theory has been, of course, historically very productive and influential. Wilson came up with the renormalization group after having learned about the Kondo problem. So that's what motivated Wilson to develop the RG, in fact. There was a substantial progress on integrability, thanks to the Kondo problem again. And of course, the idea that there is conformal symmetry at long distances for many body systems came also from the study of various line defects in condensed matter physics. So the aim of this talk is to explore line defects in higher dimensions, which is a subject that is substantially less explored. So let me define the setup. The setup is that there will be some conformal filtering in d dimensions in the bulk, d space-time dimensions, I should say, in the bulk. And then there will be some one-dimensional defect placed on a straight line or on a circle in some parts of the talk. So we are familiar with many line operators or line defects in conformal field theories in d dimensions. For instance, there are in gauge theories, we have the Wilson-Hooft loops. In various conformal field theories with symmetries, there are so-called twist defects. There is something that condensed matter people call SPT defects, which I will not talk about today. And even when the bulk is just a topological field theory, there are line operators, which are the word lines of anyons in the topological field theory. So there are many constructions of line defects. And I'll try to say some things which are general about line defects in more than 2 dimensions. There will be 2 subjects in this talk. One will be that I'll make some very general comments about renormalization group flows on line defects. And then I'll talk about a very concrete example that will appear on the archive this week, which is some line operator in the ON model that we've studied in the recent couple of months with collaborators, whose names I maybe didn't say, but they're Gabriel Cuomo, Mark Mazet, and 𝗰𝗵𝗶𝗶. All right, so when we have a straight line in a d-dimensional conformal field theory, the line can or may not preserve the maximal possible conformal symmetry. So if the line defect is conformal, it would preserve SL2R times SOD minus 1. SL2R is a conformal symmetry that's associated to the quantum mechanics on the line in quotation marks being conformally invariant. And SOD minus 1 is just the transverse rotation symmetry. Now, it is in principle probably possible that there would be conformal line defects which carry transverse spin, but to my knowledge, those were never constructed up to now. At least in non-trivial bulk conformal field theories, this was not constructed as far as I know. So I'll just talk about line defects which are conformal and preserve the transverse rotation group. Well, I'll talk about RG flows, but if these line defects are conformal, then they preserve this full symmetry. Now, in condensed matter literature, this setup where there is a conformal field theory with a line defect is very interesting because it describes an impurity. And an impurity is like, you can think about it as a lattice system with some external atom or some external background field that's localized at a point in space. And there is some RG flow associated to such impurities. And if these impurities are conformal, then they preserve this full symmetry. Okay, so that's the setup. So let me tell you about an interesting but rather abstract observable for line defects. This is something that we call the defect entropy. Okay, however, it's not the same as the entanglement entropy of this impurity. You can define an entanglement entropy for such an impurity, which is conformal or non-conformal. But what I'm calling defect entropy is not the same. So the idea is you just make the line into a circle, which makes sense in Euclidean signature, and you compute the expectation value of the circle. And the expectation value of the circle is called log L. But then this expectation value of the circle is slightly scheme dependent because there is a cosmological constant term that you can add to log L. This is just because you can assign whatever mass. You can just say that your impurity has some arbitrary mass, and that would introduce some linear term in R inside the expectation value of the circle. So to define a purely an intrinsic defect entropy that doesn't depend on scheme, you act with this operator, which removes the linear piece, and you call this the defect entropy. At fixed points of the renormalization group on the line, the defect entropy is also sometimes called log G. Okay, so this is a scheme-independent intrinsic observable, which you can think about as the defect entropy log G. For topological field theories, G is also called the quantum dimension, and it satisfies this inequality. The G is always bigger than 1, bigger or equal to 1. However, as I'll show you very soon, when the ambient space equals a conformal field theory, the defect entropy does not have to be bigger than 1. I'll show you examples where it's arbitrarily small and close to 0.
I have a question.
Yes, thank you for interrupting. I was about to stop for a second for questions. Yes.
So when you say that the defect is a circle, isn't the conformal symmetry lifted to the Virasoro symmetry?
All right.
From a cell to
So
R?
here, okay. Here the setup is that the bulk, sorry, I'm going in the wrong direction. It's too early. Here the setup is that the bulk is a conformal filter in d dimensions. When you have a straight line, which is conformal, then you preserve this symmetry. You agree with that?
Yeah.
Now a circle and a straight line are almost the same. You can go from each to the other by some sort of conformal transformation that doesn't vanish at infinity. It's like an inversion. So actually a circle and a straight line preserve the exact same symmetries. It's some kind of external outer automorphism of SL2R times SOD minus 1. So it's basically the same. The circle and the straight line preserve the same because the bulk is always d-dimensional. So there is never Virasoro for d equal bigger than 2. For d equals 2, you're completely right that both the straight line and the circle preserve the full Virasoro. But I'm not talking about d equals 2. Any other questions?
So you wrote down G is greater than 1. So G equals to 1 is that the empty defect or what is that?
All right. In topological field theories, a lot is known about it. Okay, for topological field theories. So for topological field theories, G equals to 1 does not imply that it is the trivial line. G equals to 1 implies that it's what's called an abelian anion in condensed matter language. So you're right, G equals 1 could have, so G equals 1 includes the trivial line, but there are also anions which are abelian, which also have G equals 1, okay? However, every anion in the topological field theory setting must satisfy this. Now, when the bulk is a conformal field theory in d dimensions, G equals 1 does not imply that it's a trivial line either. And in fact, G can also be much smaller than 1, as you'll see in some examples below. Okay?
Yeah, thank you.
Now, another piece of setup, I'm just setting up for some terminology. There is something that's called defect operators. What are defect operators? The concept is very simple. These are operators that can live on the line. Then there are local operators that can live in the bulk. And you can ask, what is the relationship between operators that live in the bulk and operators that live on the line? So one trivial comment is that if the line is trivial, if the line defect is just trivial, there is no impurity, then of course the operators that you can put on the line coincide with the bulk operators. You just decompose them under this smaller symmetry group. However, for general line defects, there is absolutely no relationship between bulk operators and line operators. And in the context of the bootstrap, there is an expansion. So you can try to bring a bulk operator close to the line and expand it in a power series, which includes defect operators. So in this talk, hat, when I put a hat on a local operator, it always means that this local operator lives on the line. So in general, there is a bulk defect OP and this family of operators and their scaling dimensions are unrelated to the bulk data a priori. Now, if your line operator has a defect operator which has dimensions smaller than 1, you can trigger an RG flow by just integrating this operator on the line. So you could start from a conformal line operator, But if your conformal line operator is not infrared stable, namely it has an operator of dimension smaller than 1, you can trigger an RG flow. And you can ask, how would the expectation value of the circular line depend on the radius? So for conformal line defects, obviously the radius doesn't matter because there is no scale. But as soon as you have a deformation like that, then there is some non-trivial dependence on the radius for the defect entropy. And there is an RG flow from some ultraviolet line defect to some infrared line defect. So when the radius is very small, you get the log of the G of the ultraviolet line defect. And when the radius is very big, you get log G of the infrared line defect. So there's some renormalization group flow on the line. I'll show you some examples soon. So one main result that appeared a few months ago on the archive that I already mentioned is a general formula for how this defect entropy changes as you change the radius of the loop. So changing the radius of the loop or changing the mass scale with which you integrate is the same thing because the defect entropy depends only on the product of these two quantities. So here I just chose to write it in this way. So the gradient of the defect entropy as you change the mass scale is given by an integral, a double integral on the loop with insertions of the energy density on the loop. So TD is just the energy density on the line defect or at the impurity. This can be defined unambiguously. And since this is a connected two-point function, it's non-negative, and it's actually modulated by this funny factor that we found. And this funny factor is also non-negative. So one establishes that, in fact, as you change the radius, the defect entropy must decrease monotonically. And in particular, it implies a G theorem for line defects in higher dimensions. I'll make some comments and then stop for questions. Comment number 1 is that you might know that there is already a G theorem for for line defects in two-dimensional conformal field theories. So this is a generalization to any number of dimensions. And it's not just a generalization of that. We also have a particular gradient formula that holds in every number of dimensions. It follows that G must be independent of exactly marginal defect couplings. It could be that some defects have exactly marginal operators, namely operators whose dimension is exactly 1, and you can furthermore deform the defect by these operators without changing the dimension of O hat. So in such, G cannot depend on that, because if it did, you would contradict this inequality. I'll show you an example of that. And I want to make a comment about entanglement entropy. I think that this G theorem a little bit is confusing from the point of view of the connection between monotonicity theorems and entanglement entropy, because this G function or the defect entropy that I defined has nothing to do with the entanglement entropy of the impurity. In 2 dimensions, when the bulk is 2-dimensional, Cassini, Salazar, Landea, and Toroba showed that you can understand the old Affleck-Ludwig G theorem using information theory. But that's because the G theorem in 2 dimensions is the same as the entanglement entropy of the impurity. However, this relationship doesn't hold in D bigger than 2. So that's a little bit unfortunate. And one has to understand how to connect what I'm saying to entanglement entropy. Are there any questions?
Hello, Zohar.
Hello.
Hi. One question. So maybe you said that and I missed. On the previous slide, when you defined the 2-point function of T, it's a defect operator, right? This T, TD?
Yes. Oh, I'm sorry. I should have put a hat. It's my bad. It's a defect operator.
No, no, it's fine. And it is calculated at a conformal. What is the subscript C?
Connected.
Connected, I see. So this is not necessarily evaluated at the fixed point, right? This is just at any point along the RG flow.
You're 100% correct.
Okay, thank you.
If there are any other questions.
I have a question. Going back to my previous question, the diffeomorphism symmetry of the circle is the Virasoro group, right?
Yes.
So does that have any bearing to what you're trying to say?
No, usually the field theories on the circle break the symmetry completely. You're right that geometrically the circle has a large, I mean, you can make diffeomorphisms of the circle, but usually when we put a quantum system on these circles or in the bulk, then those symmetries are broken. And the only symmetries that are unbroken, if the circle happens to be conformal, is SL2R times SOD minus 1. And if there is a renormalization group flow, then even this symmetry is broken down to translations on the circle and transverse rotations.
Okay.
So it depends on these geometric symmetries are always or almost always reduced to something by the physics of these geometric objects, yeah? Okay, I'll continue. I'll just tell you in two slides what is the idea of how this a little bit mysterious formula is proven. I'll just give you the idea. I don't have time to explain. So the first step that you make is that you generalize the idea of a renormalization group flow to allow for a time-dependent renormalization group flow. So that means that the mass that you integrate some operator, which is relevant, and I again forgot ahead, I apologize for that. So you integrate some operator on the defect, but now you're allowed to do that in a time-dependent fashion. And phi t is just a background classical field. It's not a quantum field. It's just something that modulates the mass term along the circle or along the infinite line. So this is what people usually call the dilaton in the renormalization group flow literature. This allows you to define a larger class of possible perturbations, so it's useful. And the next step is that the bulk theory, being that it's a conformal field theory, has conformal symmetries. So it has topological surfaces. So what you do is you bring the topological surface from the bulk, you wrap the circle, and because this surface in the bulk is topological, by wrapping the circle, you create a new circle. Basically, you fuse the topological surface with the line defect, and you create a new line defect. And this is the computation that you need to do. You need to compute which line defect you create by fusing the bulk surface with the line defect. Okay? And so this gives a bunch of identities, in fact, infinitely many identities, for how you can change this phi of t to various other phis of t's without actually changing the physics. And so this leads to infinitely many new identities. And if you try to understand all these identities systematically, the first non-trivial identity that you find is this. This is the first non-trivial identity. That's what we've shown in the paper. We did not look at the other identities. But okay, that's what you get. Now I'll show you some examples of how it works. What is the simplest line operator in all of quantum field theory, other than the trivial line operator? It's just you take a free scalar field in any number of dimensions. Phi is a free scalar field, what they call mean field theory, in any number of dimensions. You integrate it on a line, you put some coefficient, which you call zeta, and that's your line operator. That's the simplest line operator you can imagine. If you want to think about it as a renormalization group flow, then zeta equals, well, let's say that we're below 4 dimensions, so that this operator has dimensions smaller than 1, and that this drives an RG flow from zeta equals 0, which is the trivial line defect, and it drives it to something in the infrared that we have to determine. Okay, so that's the setup. It's an RG flow from a trivial line defect, just completely empty, transparent line, to some possible non-trivial infrared line defect. So you can actually solve it completely because everything is free. This is the action. So you have in D dimensions a free scalar field, then you integrate on the defect phi. This is a classical field theory because, well, sorry, this is a quadratic field theory, not classical. It's a quadratic field theory. The one loop determinants are important for some questions. However, it's very easy to solve, obviously, being that it's quadratic, and this is the defect entropy. So this is just a bunch of factors that depend on the number of dimensions you can ignore. This is the radius dependence. You see, this is the radius dependence, and this is the dependence on the coupling zeta. The most important thing is to observe that this prefactor is negative. So you can show it by just plotting it in Mathematica. You can see that it's negative for all dimensions smaller than 4 and bigger than 2. And what the system describes is an RG flow from the trivial line defect. When the circle is very small, the defect entropy is 0, as appropriate to the fact that in the ultraviolet we have a trivial line defect. But in this system, there is a disease. The disease is that when we make the loop very large, the defect entropy just goes to -infinity, or in other words, G goes to 0 in any number of dimensions smaller than 4. So this is probably a disease that has to do with the fact that the bulk conformal field theory has a modular space of vacua. And I don't expect that this is possible in theories which have a healthy single conformal vacuum. But anyway, in this theory, the defect entropy just flows to -infinity at the infrared. In other words, this impurity is a little bit sick. You can think about this impurity experimentally as putting external magnetic field for an external magnetic field in some spin chain. And this means that effectively the magnetic field becomes infinite when you go to long distances. So it just polarizes the whole. So physically, what it means is that a localized magnetic field would just polarize the whole chain or the whole lattice. Yes.
Is the action bounded from below?
Sure. Yeah. Thank you. It is bounded from below in the bulk. This is only localized on a circle. The defect is a circle.
So let's shift the zero mode of phi everywhere in space-time.
Oh yes, that's the modular space of vacua. Indeed. Sorry, I did not answer.
It's not a modular space because you have an action. Determine the defect makes it smaller and smaller. So the action, you don't have a modular space. In fact, it's not bounded from below.
Yeah, you're right. I did not answer the question correctly. That's, yeah, what you said is another way of saying of why I think that this is due to that there is a modular space of vacua in the bulk before we've put the defect. That's, yeah. So that's why I believe as a conjecture.
It's worse than that. It's worse than that. Your path integral is not well defined.
Yes, I agree. I agree with that. This model is sick. As a conjecture, I do believe that in theories with a healthy, unique vacuum which is conformal in the bulk, this can never happen, but I don't know how to prove that. Now, in 4 dimensions, even though the same objection that Nari just raised still exists, actually in 4 dimensions, the defect entropy does not flow. This goes away. And this whole factor becomes 0 because this gamma function is gamma of 0 and that's infinite. So the defect entropy just stays 0. And this is saying that this is an exactly marginal parameter in 4 dimensions. So this line operator also has an exactly marginal.
This defect term can be written as a source term, right? Phi times some j integrated over the entire space with some delta functions thrown in, right?
Yeah, that's what I did here. That's what it's written here.
Yeah, so it can be written as a source term. I mean, some source j times phi.
That's what I did here.
Yeah, so if you integrate out the phi, it would be simply a function in terms of the, I mean, it would just be e to the minus j delta j, where delta is the Green's function, right?
Yes. This is just free field theory. It's very easy to solve. You can solve it by, you can solve it by either integrating out phi, or you can solve it by integrating out the bulk and getting a non-local theory on the defect. It all leads to this answer.
Yeah, so I don't see why it leads to any pathologies.
We can discuss it later. I just have 7 minutes and I have a huge amount of stuff that I wanted to tell you. But it's amusing that in 4 dimensions, it is actually exactly marginal. The G function doesn't depend on zeta, but other observables do, such as the 1-point function of the energy momentum tensor. I just wanted to tell you something.
Still not bounded from below.
Yes,
even
you're
in 4
right.
dimensions.
Right, but everything makes sense, it seems. But you're right. Now I'll study a healthier system, which is also experimentally much more interesting. And as far as I know, people already started trying to reproduce what I'm going to tell you experimentally. So this idea of just studying RG flows that begin at the trivial defect is obviously generalizable. Every time you have a bulk CFT with an operator of dimension smaller than 1, you can integrate it on some dimension 1 line. And the simplest example that comes to mind is the ON model. Okay, so in the ON model, we have a vector phi, which is called the order parameter, and phi1 is the first component of the vector phi. You take phi1, you integrate it, and that's it. This leads to a renormalization group flow from the trivial defect all the way down to some non-trivial conformal defect conformal field theory. I forgot to say that in this example, you can also check this identity with a 2-point function. It will be important for some things very, very soon. So from the G theorem, it follows that this must flow to a non-trivial defect conformal field theory, because G is 1 in the ultraviolet, being that it's a trivial line defect, and G must decrease, and therefore it cannot be a trivial defect. So just by the G theorem, it follows that this must result in some non-trivial defect conformal field theory. And in fact, this problem makes sense even in 2 dimensions, but just for n equals 1, where it's the Ising model. So it's some particular interface in the Ising model. So this is physically realizable just by putting some localized magnetic field in a quantum critical point. It's pretty easy to realize in Monte Carlo and also with quantum Hamiltonians using these quantum simulators that people have written about recently. And also it's probably something that can be analyzed with the bootstrap, this particular defect conformal field theory. I'm going to tell you a few things about it in the remaining 5 minutes. This external magnetic field breaks the symmetry from ON to ON-1, and also the translation symmetry is broken by the existence of a non-trivial defect in the infrared. And so this leads to some protected operators on the defect, which are called the displacement and tilt operators. I'm going to ignore them because, well, I'll tell you about the non-trivial facts about this defect. So this is the line operator. And I have 3 quick comments to make about it, other than that it has to flow to a non-trivial defect in the infrared. Comment number 1 is that in the 2-dimensional case, where n is equal to 1, it's very easy to guess what's the endpoint of this RG flow. It's some conformal line defect in the Ising model, and they've been classified. And there is one that is completely stable for infrared perturbations. It has G equals 1/2. And actually, the operator phi1 undergoes huge renormalization. It starts in the UV as the phi1 operator, as the spin operator of the Ising model, which has dimension 1/8. But it ends up being one of the operators in this particular interface, which is composed of the fusion of 2 Cardy states, and it has dimension 2. So it undergoes pretty big renormalization. That's comment number 1. Comment number 2, which I'm going to just mention quickly, is that actually this line operator can be studied in the epsilon expansion. That's not obvious. So the bulk coupling is very small in the epsilon expansion. That's well known from Wilson and Fisher. But the defect coupling, this coupling also undergoes an RG flow from H equals 0 to something in the infrared. The defect coupling is actually not small parametrically at the fixed point. Yet an epsilon expansion can be obtained, and you can make lots of predictions in the epsilon expansion. The reason that you can do the epsilon expansion, even though the defect running is sort of large, is because the dependence on H is polynomial to every order in lambda. So the fact that there is a small coupling in the bulk is sufficient to have complete control over the system. But this is just a sketch of a few observables. So this is the logarithm of the G function of the defect in the epsilon expansion. This is the dimension of the lowest operator, which is ON-1 singlet. That's the same operator that in the Ising model undergoes large renormalization. So I'm just, for the record, putting some concrete results here. You see that this is bigger than 1, so it becomes irrelevant in the infrared, as you would expect. And this is the 1-point function of some bulk operator. So in the bulk, phi1 measures the magnetization, and it decays away from the defect. And that's the coefficient with which it decays up to the obvious scaling. So that's the non-trivial bulk to, this is what I called the A coefficient in the bulk to defect OP in some slide in the past. Here, this is this coefficient. Okay, so you can do the epsilon expansion, you can obtain a lot of predictions and even extrapolate to 3 dimensions where this is experimentally realizable. What you find is that you expect, roughly speaking, a rather weak n-dependence, and that the dimension of the first non-trivial ON singlet operator, ON-1 singlet operator, is going to be 1.5. So that's roughly speaking the prediction. The last thing I want to tell you about is what happens in the large n limit. This is probably the most interesting part of the story, but I have only 2 minutes, so I'll just tell you the idea. So it turns out that this has a smooth large N limit, but you must define a 't Hooft coupling, very much like we do in other large N limits. And in this normalization of the defect coupling, the 't Hooft coupling is actually order 1 in the infrared. And what we argue is that there is a new classical action, like a master field action, that governs this defect conformal field theory at long distances. So what is the idea? The idea is that at long distances, this defect becomes conformal. So you can map the problem by a wild transformation to ADS2 times SD minus 2, where the ADS arises from essentially some plane that's transverse to the defect. And there is, you do some transformation to ADS2 times SD minus 2, you do a Hubbard-Stratanovich transformation, and you try to find a self-consistent conformal solution for this defect in the large N limit, which is described by some classical action. So after a lot of work, we found this kind of Schwinger-Dyson type action. And it's a classical field theory with H bar, which is 1 over N. So it's a quantum field theory with a very small H bar. And our claim is that the critical points of this action and fluctuations about this action compute the properties of the defect conformal field theory at long distances with this external magnetic field. This is the boundary to boundary propagator in ADS2 times SD minus 2. This is just the curvature. This is the Laplacian. And this is some field. This is the master field, essentially, that you have to vary and compute the fluctuations of. So this is the main part of the problem at large N. And well, we've used a lot of recent progress on ADS loop diagrams, especially from this paper. And this is the bottom line. I'm just sketching a few of the results. This is an exact result in the planar limit for the G function. You see that it's exponentially small. So that shows that G doesn't have to be bigger than 1 in defect conformal field theory. There is a minus sign and there is an N. So it's really exponentially small. This is the dimension of the field phi1. And as I said, it's pretty close to 1.5 with seems like rather weak N dependence. And this is the 1-point function of phi in the bulk. And we have lots of other quantities that we computed in the large N limit by solving this Schwinger-Dyson system, by looking for a self-consistent conformal solution to the Schwinger-Dyson system. And now I'm just going to summarize quickly. Obviously, it would be interesting to understand if there are some lower bounds on G, maybe along these papers. There is something that's called the VE flows. So in quantum field theory, you can have flows with operators, or you can have flows by activating some vacuum expectation values for gauge invariant local operators. Like we have a Coulomb branch in N equals 4. People claim that this might happen even for line defects, though I don't understand that. Obviously, one can try to contrast these results with experiments. And well, there are some comments here that one should definitely apply the conformal bootstrap for this problem. And that's it. Thank you so much. Sorry for going over time.
Thank you, Zohar, for that beautiful talk. I see a hand raised from the TIFR node. I think it's Abhijit.
Can you hear me?
Yes.
Yes. Hi,
hi, Zohar. Thanks very much for a wonderful talk. So in the talk, when you derived this flow condition for the G, the monotonicity condition, you use some sort of a topological operator. Could you say a little bit more about that?
Yes.
What exactly was that operator?
Am I, like with time-wise, am I rushing, or can I make an effort to explain?
Well, we are going into the discussion session now, so I think it's okay.
Okay, I'll tell. Okay, so I can maybe say more than a few words. So the bulk doesn't have many topological surfaces. The bulk has topological surfaces that are given by choosing a conformal Killing vector, essentially, right? You can integrate T mu nu contracted with a conformal Killing vector on an arbitrary codimension 1 surface, and that's a topological operator. So there is a particular conformal Killing vector which fixes the line. So this is a conformal Killing vector that is associated to this SL2R times SOD minus 1.
Mm-hmm.
So we pick one of those. There are 3 such things because SL2R has 3 generators. So one of them is stupid. It's just translations along the line, and it doesn't give anything interesting whatsoever. And then there is one that's non-trivial. So we pick one of those that's non-trivial.
This is part of the SL2R.
Yes, we integrate it on the surface. And then we ask what happens when we fuse the surface with the line. Now, this is a computation that you have to do. And it's a very subtle computation. But this is the main claim, that we claim that we did this computation. And what is, so obviously, if you fuse it, you get some new line defect just by the axioms of locality. On the other hand, if you blow up the surface, you get 0 because it acts on the conformal vacuum. So you get an identity. The identity is that whatever line defect you get after the fusion should be the same as the line defect that you originally started from.
I see.
But when you do this computation, you find that it generates a non-trivial transformation of phi. Basically, it shifts phi by a cosine times phi dot. And then you choose some particular phi for your convenience, and you generate a huge amount of identities. So that's the main thing.
Okay, thanks. So maybe my second question is perhaps related to this one then. Does this way of thinking give some insight about state operator map for such defects? Or more generally, how does one think about classification of such defects?
Oh, classification is difficult, I guess. There is a paper by this gentleman, I believe this paper, João van Rijsselien, that claimed that free field theory doesn't have non-trivial defect. Free field theory, let's say in 3 dimensions, doesn't have non-trivial defects, line defects. That's consistent with what I've been saying, because this doesn't flow to an infrared DCFT because of this issue that Nari pointed out, that the whole thing is not very bounded and it's a little bit sick.
I see.
So for instance, for free field theory, people claim that maybe there isn't any non-trivial defect. But for the ON model, classifying them would be probably insurmountable.
I see. No, but even conceptually, how would one go about classifying such defects?
Well,
I mean, for local operators, we have state operator maps, so one could classify them by looking at Hilbert space on sphere.
It's the same. There is a bulk defect OPE, and there are 2 channels. You can first expand. You can do a 2-point function in the bulk. You can first do an OP in the bulk, expand in the defect, or first expand on the defect, do OP in the defect.
I see.
It gives an equation.
I see.
Unlike the bootstrap equation, it's not a semi-definite equation. So there is no positivity. Maybe it's more difficult.
I see. But what I had in mind, I mean, if I have a defect, then I could always couple some quantum mechanical system or some higher dimensional system on the defect and flow down to to get another defect. So it seems that I can keep on doing that and get richer and richer, more and more defects. So
of course, I didn't talk about Wilson lines, but Wilson lines. So the defects that I talked about here, just for pedagogical purposes, are defects that start their life as trivial defects in the ultraviolet. So we start with the empty unit operator defect, we integrate some bulk operator, we get an energy flow. And this must have G smaller than 1 by the G theorem, so it has to be a non-trivial DCFT. Of course, you can do something much more general. You can add quantum mechanical degrees of freedom, couple them to the bulk by gauging or by just direct coupling, like Yukawa type coupling, and then trigger our G flows. This is what in condensed matter is called magnetic impurities. That's what appears in the Kondo problem.
Okay.
While what I did here is more like an external field impurity. You model that by taking a spin system and putting some external field at some point in space. But you can do what you said, of course, and it seems like it leads to a large zoo of possibilities. I agree.
Yes,
but it may also be discrete. We have no idea if it's discrete, continuous.
Yeah, exactly. That's what I was asking, because it seems like possibilities are endless. However, the bootstrap approach seems to tell me that I am constrained in some way. So that is the question that I was trying
in 2 dimensions, the problem is understood for minimal models. So for the Ising model. So in the Ising model, there are infinitely many conformal defects, but they come in 4 families. And the families have exactly marginal parameters that are basically interpreted by integrating the epsilon operator. So in the Ising in 2D, we know the answer. And that's probably the only case where we do.
Thank you. Thanks a lot.
Thanks. We have now a question from Nati. Please go ahead.
Back to the problem which is not bounded from below. Where is the action? What if you replace phi by phi square? Then it is bounded from below and it remains free, so it should be solvable.
But it's irrelevant.
I see. So if you write phi square, it's irrelevant?
Yes, because phi squared has dimension close to 2 near 4. Well, let's say you're in 4D, it's highly relevant. If you're in 3D, okay, in 3D, it's going to be marginal. In 3D, it's going to be marginal. That means that with one sign, it will be marginally irrelevant. And with the other sign, it's going to flow to minus infinity. So there you'll have your instability again.
No, but that's a different. Is the sign where it flows to minus infinity the sign where the potential is not bounded from below?
That would be my guess. That would be my guess, Nari. I didn't do that computation. My guess is that if you put phi squared with a positive coefficient, it flows to 0. And if you put
with one
squared,
coefficient, I don't know your conventions. With the positive coefficients, it's a meaningful question to ask. With the negative, it's not that it goes to minus infinity. It's not even meaningful. It's as bad as the linear one.
Yeah, Nari, with a positive coefficient, it goes to 0. I'm sure of that.
I see.
With a negative coefficient, it goes to minus infinity.
Well, with a negative coefficient, it doesn't mean anything to ask how it flows because the problem is not set up properly.
Yeah, I think what physically happens is that phi wants to go negative and the bulk doesn't stop it because there is no potential in the bulk. So just phi goes to minus infinity.
Well, that's a statement that it's not bounded from below. So the problem is not well posed when it's negative.
Yeah, I think with positive coefficient for phi squared, Appendix A in the paper that will come out tomorrow shows indirectly that it goes to 0. That's the right sign of the beta function.
Thank you.
Okay, we have maybe time for one last question and then we should move into the discussion session. So Somdat, you had a question? A brief one.
Yeah, this defect term can be understood as j times phi. So I get that before integrating out the phi, it is unbounded from below. But if you integrate out the phi, once you integrate out the phi, it is in terms of the j's, right? And then that is not unbounded from below.
Let me think about what you're saying. There is an instability, obviously, in that language too. Well,
I think J is not generic, right? J is delta function localized. So
J will be some funny delta function. There will be some box in the denominator. There must be a way to see the instability in that way too. I didn't think about it in that way.
J would just be a delta function.
Yeah, but there will be some boxes in the denominator if you do it. You check it out, you'll see that there are boxes in the denominator.
Yeah,
if you integrate out phi, there will. Yeah, J will be the delta function. Yeah.
Okay, I think let's thank Zohar for a very nice talk. Daniel had a question. Daniel, did you want to ask?
Oh, I just said if you integrate it out, maybe the effective action you get is non-analytic. It's at equals 0.
No, it's just that there is a box in the denominator, and the box has a 0 mode because the bulk field is massless. So that will be the issue.
Yeah.
The 1/box will not be properly defined because there is a 0 mode in the bulk.
Exactly.
So I think it's gonna be the same thing. Anyway, these problems don't exist for the more experimentally interesting problem of ON, where you do get a completely healthy DCFT. So that's the reason that we looked at the ON model.
So would you say that if you integrate out a massless scalar coupled to a source, the resultant action is unbounded from below?
I don't want to make sweeping claims, but in this particular example, we just solved it, and you see that it goes to minus infinity. It's not in doubt.
Yeah, I think now let's thank Zohar for a beautiful talk, and let's move on now. As per the program, there was to be a discussion session, and that was from 6 to 6:30. We are now at 6:35. But I just chatted with Daniel a little bit separately, and so he's agreed kindly to start after 15 minutes from now, which is 6:50 Indian time. And so we have 15 minutes, and during these 15 minutes, if anyone would like to ask a question from any of today's speakers who are present, you're free to do that. I'm sorry there isn't any kind of break, but that's the program. So yeah. So Sachin has a question. Sachin, please go ahead.
Yeah, my question is for Loga. Is Loga around?
Let me check. Loga?
Yes.
Loga, in your last slide, you had a comment about DS cosmology. Do you mean in the super versus sub-horizon modes? Is that what you meant, or what exactly you meant in that comment?
Yes, something like that. Yeah, and there's something that I'm thinking about, but this is probably not the right time or the place to talk about it. But if but we can talk about it. Okay. Yeah, but the short answer is yes.
Okay.
Okay. Somebody was asking if Shiraz is around. I think Shiraz is around. Shiraz, would you confirm?
Yes, I'm here.
He's around. So whoever it was, I think 𝗰𝗶𝗶𝗶 had a question.
Yeah. Am I audible?
Yes.
Yes.
Okay. Shiraz, just one confirmation. So the theories that you talked about today, so that is defined in any three-dimensional manifold? I mean, one can compute those things in any three-dimensional manifold?
Well, it's defined on any three-dimensional manifold.
Yes, but
computations are hard outside the sphere. And the reason for this is as follows. You see, suppose you take pure Chern-Simons theory, for instance, on a torus. That theory has a very large number of zero energy states. Okay, the number of states grows like some high power of n. In some sense, the entropy of that is like e⁴ Now, this is like the dominant effect, and then matter is in the sense of the 1/n expansion a subleading effect in that.
Yes.
Okay, so doing the large n expansion of this theory is hard because of these very low energy states. The sphere is great in that regard because on the sphere, pure Chern-Simons theory is really trivial. There's only one single vacuum state. So matter gives you everything, and so the large n expansion is easy. So I don't think anyone's I think the theory is well defined on every manifold, and there are interesting things to compute, but it's hard to do. Actually, many years ago, there were these papers by Shankar and Shamik Banerjee and so on, where they tried to do they try to make some progress on looking at some questions with matter and higher genus manifolds. But it's a hard problem.
So I was basically just thinking about for R2 cross S1 also, it should be very hard.
R2 cross S1 is fine. Of course, you have to define R2. So one way of defining it is as the large radius limit of S2, and then
yeah, that is what I would. So let me ask this question like this. My interest was to use your formulation to say something about flat space holography. Okay, so for flat space scenario, these Chern-Simons actually appear with a non-compact gauge group, which is ISO 2,1. The corresponding Chern-Simon gauge group is ISO 2,1, and it is defined on R2 cross S1. So I was just thinking that if a partition function for the same is anyway one can compute, even in presence of some matter field, if that helps, then probably one should be able to say something for the corresponding dual theory. I mean, so you were there in Tadashi's talk, right? So
yes, I was in Tadashi.
Tadashi was doing it for DS3 and the corresponding field theory. And he actually needed a Chern-Simon with SU2 gauge field, but he was doing it probably on R3 or maybe on S3. S3, yeah. So I was just so a parallel for flat space case is not known. I mean,
let me make one little comment about this. The problem with flat space is that that space-time has a boundary. Okay, so for instance, you can think of Scri plus and Scri minus as the boundary of space.
Yes.
Now, when you put Chern-Simons on a theory with a boundary, you typically get boundary modes. This chiral Wessel-Witten model that Nati and friends worked out so many years ago. I mean, if you really honestly want to do something in non-compact space without thinking of it as a limit of a large compact space, I suspect you have to think carefully about those boundary modes.
But yeah, in this case, it's only those boundary modes which are non-trivial because there is nothing in the bulk.
Without the matter.
Yes, without the matter. Yes.
Right.
So you were saying that those computations are not known, right?
Well, I think if you were really interested in a pure, I haven't thought about your ISO whatever theory, but if you were just doing SU2 John Simon's theory, that would probably just give you these chiral Wessumino-Witten words on the boundary.
The ISO 2,1 will also, that also has a Wessumino-Witten counterpart, but it's just that the partition function for the, one can construct the theory and that would be like a chiral Wessumino-Witten theory with ISO 2,1 as its gauge group. But the corresponding computations for the partition functions probably are, I was just trying to ask you if that is anyway known or if you think that is doable.
But you're really interested in the pure Chern-Simons theory. Is this right?
Pure Chern-Simons would, I think in this context, pure Chern-Simon would be the simplest one. But like if having some matter helps in the calculation, that's fine.
Okay. I just wonder if there are some issues having to do with the fact that the gauge group is non-compact.
I think that is.
But I haven't thought hard about it. But let me say one more thing. Just in the context of matter Chern-Simons theories, there is a hint that these boundary modes cause trouble. Or not trouble, they cause interesting physics. And the hint for this statement is that if you compute S matrices in these theories, S matrices of the matter, you find funny properties. You find that these S matrices do not appear to simultaneously obey both unitarity and crossing. Sort of define an S matrix that looks unitary but then seems to violate crossing. And I think that this is a sign that when you want to deal with really this infinite flat space, you need to carefully deal with this boundary modes that does not ever care and their interplay with the matter. I think this is not ever really carefully been done. I'm not sure it's related to your question, but just to say.
Okay, thank you, Shiraz.
Okay, ICTS AV team has a question. I assume that's the seminar room there.
Huh? Hello.
Hi.
Mr. Karunava,
Yes.
I want to. Can you hear me, right?
Yeah, please.
With breaks, yeah.
Yeah. So my question was in this group from TFR relates this maximal chaos kind of property to the growth of some scattering amplitude, right? So is there a similar statement you could make about from the pole skipping perspective,
So there's a recent paper by Natsume. I'm not sure. I have not read that completely, but yeah. You can look into that paper. Just I think 10 days ago. Yeah.
Thanks.
Okay, maybe I can take the opportunity to ask a question to Shiraz since I still see him here. Shiraz, you had, I came in unfortunately a little late to your talk, but I read the slides later. And somewhere you actually made a conjecture about properties of integrable representations of Wessumino-Witten models, which roughly, or which simply can be stated that if there are two representations, 1 and 2, that appear when I tensor a bunch of sequentially fused representations together, then the number of times 1 appears over 2 is the ratio of their quantum dimensions, right?
Correct.
And so just trying to understand that formula. So this number you're talking of is the number of times a given representation arises by tensoring what representation with itself?
It doesn't matter. Any sufficiently large number of representations.
Any representation, but with itself sufficiently.
Not necessarily itself. Any sufficiently large number of representations.
Any sufficiently large number of representations.
Maybe I can put this conjecture in context.
Yeah, please do.
Okay, let's first do classical group theory. Okay, so now suppose I tensor, I've got representations R1, R2 up to Rn. Okay, I keep my group, let's say SUN fixed. So these are two different n's. So R1, R2 up to Rm. I keep my group SUN fixed. N is fixed and I take M to infinity. Okay, now what I want to know is in the product of all these representations, how many copies of some other representation, let's say some RP appear. Okay, so I can get that by taking the complex conjugate of the character of RP. Okay, multiplying it with the product of characters of all the representations I have, and integrating over the unitary group using the Weil integral formula. Okay, but now since there are so many representations inserted, the integral, you've got a parameter in your problem, and the integral is going to be localized on the unitary matrix that maximizes the integrand. But in classical group theory, that's very simple, because there is one element, namely identity, on which all characters are as large as they can be. Right? There's the obvious inequality that chi r of identity modulus is greater than equal to chi r of any u. Okay, so
it's just the dimension of the representation.
Just the dimension, the classical dimension of the representation.
Classical dimension. Yeah.
Okay, so in this case, as you just pointed out, we've got the sequence of representations, and then we add another one, and the dependence on which one you added comes just through chi evaluated on identity of that representation, and therefore it's classical dimension. Okay, so in classical group theory, what I said is sort of obviously true. Okay, now our conjecture is that there is a quantum analog, the quantum group analog of the statement, and that it's actually a slightly more precise statement there, and that when you do the same thing, you get the quantum dimension rather than classical dimension of the operator. Okay, and one last remark about this. This is something we've not proved, but we've got a reasonable amount of evidence for, I think. Okay, and one last thing about that is this. Unlike in the classical case where you have to integrate over all unitary matrices with the Haar measure, in this, in the Verlinde formula, you need to sum over a finite set of discrete eigenvalues. Okay, now the Verlinde formula establishes a map between these discrete eigenvalues and integrable representations of the Wess-Wiener-Witten theory. And there is one, of course, very distinguished integrable representation, namely the identity representation. Okay, and that representation maps to a non-trivial configuration of eigenvalues, because the identity as a unitary matrix is not an allowed eigenvalue configuration, because the rules are that, for instance, you have to be a kappa at the root of unity, but all eigenvalues have to be different.
Different, right?
Okay, so the identity maps, in some sense, to the representations that's as close as you can get to the identity matrix, staying within the set. Okay, and our conjecture is that that in that sum over the Verlinde thing. So now the integral over U is replaced now by a sum over these discrete number of eigenvalues. For the same reason that the saddle point dominated in the integral over U in the classical problem, the sum here will be dominated by one term. It will be the term that maximizes the characters. And effectively, our conjecture is that the character of every integrable representation, modulus of the character of every integrable representation, is largest on this special eigenvalue configuration, namely the one dual to the identity representation.
But since we know these characters explicitly for Wess-Wiener-Witten models, right? So they're just the Kurzweil formula.
Yeah, it's actually even simpler. The character the character I'm talking about is the classical group theory character. Just okay. It's like the sign for SU2. It's the sign by sign. It's not the character of the Wess-Wiener-Witten. It's just character of the group. Okay.
Sorry, either I froze or you froze.
Yeah, sorry. Can you hear me now?
Yeah, I can hear you.
Okay, so for instance, if you are making this conjecture for SU2, it's just a simple conjecture about a function.
I see.
Okay, and for SU2, we're pretty sure this is right because we've checked it on Mathematica all over the place. Okay, but yeah, somebody more mathematically powerful than me would be able to prove it, I think.
Okay. Okay, we have, let's move on. We have 2 more minutes. Sachin has his hand raised. Maybe that would be the last question and then we should really stop.
Okay, so I have a question for Traksu. Sorry. So is it Traksu?
Yes.
Yeah, so, there was this recently a paper in de Sitter space, given a flat space amplitude, there was a unique way to, for example, a simple way to uplift it to the de Sitter amplitude, let's say for 3-point function or also 4-point function with a particular exchange. Okay, And of course, so the kind of formula that you showed, is that what you have showed, that given a flat space amplitude, I have some differential operator, I differentiate, and I just get the anti-de Sitter amplitudes?
Yeah, not exactly, because given a flat space amplitude, you can you can go to different like in the ADS limit, you can have different corrections in 1/r, because the derivatives don't commute, right? I mean the covariant derivatives do not commute. So in general, you can have different expression in corrections in 1/r given the flat space S matrix. So, but still you can get some information. Does it answer your question?
I see. Okay. Maybe I'll ask you later.
Yeah, we will discuss offline.
Okay, thank you all. So I think this concludes today's discussion session, and in principle, we have no break, but oh, there was a question for Zohar. I'm sorry. Chethan had a question for Zohar. Chethan, go ahead quickly.
Yeah, it's basically just the question that I've written there. It's just that I was wondering if, oh yeah, so I was just asking if it seems like if you, for instance, I mean, I was thinking of like analogy with this in some sense in D7 or D8 brains or something. It seems like you might back react too much or something like that. So just wondering if this is really tied to CFTs or not.
Yeah, this is a very good question. So the question is whether these flows on the line defect can destroy the bulk in some sense, right?
Yeah, that's
so, right. So the example, for instance, with the free field in 3 dimensions, you could interpret it in this way, because the instability that's caused by adding a linear term on the line somehow leads to some instability in the bulk. That's why it goes to -infinity. More generally, I think more generally it's only possible in free field theory. That's my understanding. That only in free field theory there could be some logarithms that would back react on the bulk too much. I do not believe it's possible for interacting bulk CFTs, but I may be wrong. That's my understanding.
Thank you.
Okay.
I can say okay. I can write in the chat why I think that this is true. I'll write in the chat.
Yeah, I mean, I asked the question right as he was closing the thing, so it's okay. I mean,
yeah. I'll write in the chat why I believe it's true.
Thank you.
Yeah, I think we really have no more time, and it's if Daniel starts immediately, which he's going to do, it will still be much beyond 8 by the time we end with questions and so on, 8 Indian time. So I really think we should start now. So it's a great pleasure to ask Daniel Harlow to give his survey talk titled Recent Progress on the Black Hole Information Problem. Yeah, good. We can see your presentation. We can full screen it probably, and please start. Yeah.
Very good. And everyone can hear me, I hope so.
Yes, yes.
All right. So let me first start by saying thank you for the invitation to speak here. It's an honor. I've always enjoyed my time in India with the strings community. It's a pity that I can't be there in person this time, but hopefully sometime soon. I wasn't exactly sure. So what I was supposed to do with this talk, I tried to put it kind of somewhere in the vicinity of the kind of review talks that are given at the Strings Conference, but maybe with a bit more still of a focus on recent results of my own, just so liven it up a bit for me. So I am happy to take questions throughout the talk. I don't need to wait until the end. So if anything bothers you, feel free to, I guess, type in the chat or raise your hand, and maybe Sunil, if you can look to see if people raise their hands.
Sure, I'll do that.
And I'll try to look at the chat too, but if I somehow miss it, then just, interrupt me, please.
Okay.
Okay. So let's just start with the big picture, since this is a review about the information problem. So combining relativity and quantum mechanics, that's the biggest problem in theoretical physics. But yeah, we still haven't solved it. And by solved it, I mean we haven't succeeded in constructing a realistic theory of quantum gravity. We've constructed many unrealistic theories of quantum gravity, but not yet a realistic one. Unfortunately, I think part of the reason why we haven't succeeded is the lack of experimental data. We do have, sometimes people say there is no data. That is not correct. We certainly do have data. For one thing, we know that gravity exists, but beyond that, we know that black holes exist. We've measured some of their infrared properties. We know the sign and the magnitude of the cosmological constant. We know how many large space-time dimensions there are. We know about the density perturbations in the CMB. I mean, so these are all pieces of information which do give us information about quantum gravity, I would say, at least in some sense. But so far, this kind of thing hasn't been enough for us to identify a unique, consistent theory, or even any theory which is consistent, even just with the data that I mentioned so far. So in some sense, the quantum gravity problem is theory limited, right? Even just the things I'm mentioning here, we don't have a theory that explains all of them, even though we've had this data for a while. Okay, so what do you do if you don't have detailed experimental evidence? Well, the next best thing is you take the theories that you do have and you extrapolate them to extreme regimes where they run into trouble, they become paradoxical or inconsistent. And then you think about what needs to be added to the theory in order to resolve this tension. There's already a chat. Okay. Oh no, that's to Zohar. That's Zohar. Okay.
Yeah, that's between Zohar. That's Zohar replying to Chethan.
Okay, so for example, Maxwell thought about capacitors that are charging up really fast, or Einstein thought about trains moving close to the speed of light. And even though we still don't have trains that are moving close to the speed of light, this was a good thing to think about in terms of understanding better the structure of the theory and how it needs to change. In quantum gravity, the most obvious regime where you get into trouble is in high energy scattering, right? So general relativity is a non-normalizable theory. And so if you try to compute even perturbative quantum corrections, right, you can't reliably compute them without further input from short distance, right? You can make up some kind of rule, but what you get out will just be your rule. It won't be something that came from a theory, really. The great accomplishment of string theory, at least historically, was, and supposedly string theory is the subject of this workshop, right? Although I didn't go to all the talks, but I guess not that many of them were about string theory. But anyways, the great success of string theory is that it gives concrete, UV finite, although vacuum dependent predictions for what these quantum corrections should be. Okay. On the other hand, there's actually another regime where if you try to combine gravity and quantum mechanics, you get into trouble. And this one actually may, in some sense, be of greater importance. And this is the regime where you go to finite, but not necessarily large temperature, but then you think about very long times. So in this regime, gravity has long-lived quasi-thermal excitations, very generically, which are, of course, black holes. And thinking about them in this regime where you're away from large regions of large energy density, strong curvatures, nonetheless, you can get into paradoxical situations. And the most famous of these is the information problem, which is the situation that I'm going to talk about in this review. So hopefully you're all familiar with the basic setup of the information problem. So so I've drawn it here in asymptotically flat space. So you collapse a shell of matter, which I've taken to be null for simplicity here, to create a black hole, and here's its horizon. And then you think about what the state of the system looks like as time evolves on Cauchy slices like this one, sometimes called nice slices. And so because of the vacuum entanglement between modes on either side of this horizon, for example, these two blue modes are entangled with each other, and these two red modes are entangled with each other, and then this keeps going down the chain and also deep into the UV right near the horizon here. So because of this vacuum entanglement, it causes the black hole to radiate, right? This is Hawking's famous calculation. So these exterior modes, they have some probability for making it out to infinity. And this causes the black hole to lose energy, which, that by itself, okay, maybe it's not so bad. But then the real problem is that if you look at this picture, right, the information about how the black hole was made, like in this infalling shell, is way in here, very far inside on the Cauchy slice. There's, at least if you believe in sort of any sense of locality, it seems like there's no way for the information way in here on this Cauchy slice to somehow get out into this radiation. You could hope that by the time the black hole reaches Planckian size, well, then maybe this radiation and that in some vague sense are not so far away, although actually I would say they still are far away. Then the black hole, by the time the black hole is Planckian size, it doesn't have very much energy. And so if you think it's just gonna, radiate into some reasonable number of particles afterwards, there's just no way that radiation that it produces will have enough information to take out to tell us how the black hole was formed. So there are three standard options for how we're supposed to respond to this observation of Hawking, right? These are the three classic options. So option number one is remnants, where you just say, okay, the evaporation stops when the black hole is a mass which is of order n Planck. But this is bad because in a remnant scenario, the entropy of a black hole is not really equal to the area over 4G. And so then the apparent success of black hole thermodynamics in a remnant scenario is just a coincidence. It's an accident. The black hole behaves as if it had an entropy A over 4G, but actually it doesn't. Okay, and so that's not very satisfying, at least to me. Option number two is information loss. So then you say, okay, the evaporation goes all the way. It doesn't stop with a remnant. But then so as a result, most of the information just doesn't make it into the radiation. It's mostly just in this baby universe that is created. So in this scenario, usually the nicest way to think about it is this kind of piece of the Cauchy slice here, when the black hole finally finishes evaporating, that just kind of finds its way off into some closed universe that no longer talks to our universe, and that's where the information is from now on. So that actually doesn't bother me so much if the information goes into a baby universe. I mean, sometimes people say, oh my God, that means that the exterior S matrix is not unitary, but I mean, who cares, right? I mean, there's still unitarity. It's just that you mix with the baby universe. So I think saying S stagger S is not equal to 1 maybe is not such a big deal. Actually, what bothers me more about this scenario is that it again implies that S is not equal to A over 4G, because when the black hole, just before it finishes evaporating, right, it's basically the same as a remnant. You have some object which is storing much more information than A over 4G. And if you could throw, for example, that into another black hole, and that would give you a black hole where S is not equal to A over 4G. And so to me, that's much worse than having the information go into a baby universe. And then finally, there's the option of unitarity, which says that the evaporation goes all the way, but actually now the information makes it out into the radiation. And so that can be consistent with S equals A over 4G, which we like. But it seems to be some apparent tension with the smoothness of the horizon, which is sometimes called firewalls. And whether you believe that or not, in any event, if this option is going to have any hope of working, it really requires massive non-locality in order for the information in the interior to make it all the way out. And I emphasize that in order for it to make it all the way out, it can't just make it out at the end, right? It has to at some point start coming out earlier. So that's something that 𝗰𝗵𝗶𝗶, I think, explained very well. So let me review a bit his picture of this, right? So most days people go for the third option. But I think a lot of the people who go for it don't really appreciate how radical it is. So for example, sometimes you hear people saying things like, well, anytime you have a bunch of corrections of order e to the minus s, and you have a lot of them, so then you get to multiply by e to the plus s, and then, why should you believe anything that Hawking said? Okay, that's kind of a phenomenologist point of view on the information problem, if you like. But as Samir explained, I think very clearly, this is not a good argument, right? Like, there's not a sense in which a small correction to Hawking's story can restore unitarity. And the easiest way to understand this is by using this page curve, where you plot the von Neumann entropy of the radiation as a function of time. So I put a star here in case Suvrad is here. I'm not sure if he's actually here, but anyways, I'll just comment. So when I say the radiation, I mean the radiation. I don't mean, the holographic description of everything that lives at spatial infinity, right? I mean, I don't expect to obey a curve like this, but I'm talking about the radiation that is actually in the space that you go around and measure with beam splitters and photons, and mirrors and so on. And so, so if you look at the von Neumann entropy of the real radiation, right, then Hawking predicts that it will just go up, 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 up until the black hole evaporates, and then it'll saturate its infinite value, whereas Page argued that by unitarity, since the state has to be pure in the end, the curve has to turn over and go back down. So unitarity changes the slope of this curve at order 1, not at order e to the minus s. That's really the point that Samir was making. And so if you want to change this story, you have to somehow explain why this curve turns over here. Just kind of mumbling about e to the minus s corrections is not going to do it for you. So for this reason, a reliable calculation of this page curve has been viewed as one of the major requirements for a satisfactory resolution of the information problem. I won't say that just having this computation solves the problem. I think that's not true, and we'll talk about that more as we go on, but it's clearly major progress. And in fact, this was done right a few years ago, which came as a surprise, I think, to many people, especially people who weren't paying attention. But you can indeed do this calculation. And so there were these groundbreaking papers in 2019 by Pennington and then by Almeri, Engelhardt, Merrill, Maxfield, which explained how to do this, which was really in advance. It's one of those things that in retrospect, as maybe we'll see it's kind of obvious that that this was possible and should have worked, but everything is obvious in retrospect, right? I mean, at the time, this was a very daring thing for them to attempt, and it was amazing that it worked. So the main input to this calculation is the quantum extremal surface formula, which was introduced by Engelhardt and Wall in 2014, which is basically just, at least in the way they were thinking about it, it's a refined version of Ru and Takinaga's formula for computing the von Neumann entropy of a spatial subregion in a holographic CFT. So the justification for this formula, right? So this formula is really the workhorse of this page curve calculation. And so we're going to spend most of the rest of the talk talking about this quantum extremal surface formula, right? So the justification for it rests on some tripod of quantum information theory, Euclidean gravity, and semi-classical intuition. I think I meant to change semi-classical intuition to holography, and then I forgot. Okay, but either one is true. And actually, the subject has grown so large that already any systematic review is impossible. So I'll instead just kind of give you my view of how the logic goes. I'll try to condense it down to something which maybe is not necessarily how things were originally said, but maybe how they should be understood now. And I'll also talk about some new results in the end. So that's it for the introduction. Let me pause and ask if there are any questions or comments. I'm surprised I made it this far, actually. Everybody's happy?
Yeah, I think so.
Okay, yeah, I think I don't see any raised hands, so, okay. All right, I apologize if my son contributes to the talk in the background. He's a very enthusiastic 3-year-old. Okay, so then let's go on to this quantum extremal surface formula. So let's just recall a little bit what the formula looks like. So here I'll present it first just in ADS CFT. The idea is if you have some boundary subregion. So here I've drawn ADS3 CFT2 just because that's the limit of my drawing abilities. If you have some boundary region R, which here is just this circle half interval here, or circle interval. In an interval, it's half of a circle. That's what I should say. Then there's a formula for, at least if you have a state of the dual CFT where the bulk description is somewhat reasonable, then you're supposed to use this formula here to compute its von Neumann entropy. So what does this formula say? Let's try to unpack it a little bit. So the idea is we look at the set of all codimension 2 surfaces in the bulk, which are homologous to R. So like this XR here is a candidate surface that's homologous to R. Okay. Just to show that although I was trained on the west coast of the US, I know what homologous means. It means that there's R of X here, and then there's a minus sign here. Okay, so the boundary of, there's some spatial region R of X, which I've drawn kind of in between here, and it's behind this other stuff that I'll explain in a sec. And then the boundary of this kind of piece of the bulk Cauchy slice is R minus XR. Okay, that's what it means to be homologous. And then the domain of dependence of this homology surface is called the entanglement wedge. But let's finish going through the formula first. Okay, so we consider the set of XRs, which are homologous to R. And then among that set, we extremize this quantity here, which is the area of XR over 4G, plus the entropy of bulk fields living on this homology surface, R of XR. Okay. So then first we extremize that over XR. So we are only interested in XRs where this thing, which is called the generalized entropy, is extremal. That's why we have the name quantum extremal surface. And then if there's more than one such quantum extremal surface, then we take the one which also has minimal generalized entropy. And then if there's a tie for the minimal ones, then we don't care because it gives the same answer for the entropy. And so finally, just for future reference, this domain of dependence indeed is called the entanglement wedge of R. Okay. So hopefully this kind of picture you've seen before. In general, the domain of dependence, for example, the null geodesics can focus and make a seam. That's what I tried to draw here to just make it a little more generic. Now, if you're given a formula for entropy in a microscopic theory of quantum gravity, like ADS-CFT, it's natural to ask if you can use it to compute the page curve. Surely some people, asked that immediately after Rudin Takenagi proposed the first version of this formula. However, there are a few obstacles which prevented the calculation from happening until recently. So the first one is that, big black holes in ADS don't evaporate. And if you want to talk about the page curve, at least in the usual sense, you need a black hole that evaporates. But we don't understand the duality well enough to trace the evaporation of a small black hole in the dual CFT. So we can certainly, in principle, set up the information problem in ADS by just collapsing a shell of matter to form a small black hole and then waiting for it to evaporate. But yeah, good luck following that in the dual CFT.
Daniel, I think Shiraz has a question.
Oh, okay, sure. Please go ahead, Shiraz.
Hi, Daniel. In the term which said matter on your previous transparency, you had a piece which was S bulk. Does that include the entropy of gravitons?
Yeah, it's supposed to, although I don't claim that the community has fully understood the systematics of that.
Could it be that when you understand that very well, we would need to include some sort of path integral over the entanglement entropy surface as well?
Well, in perturbation theory, that doesn't seem to be true. There's some, to deal with that, you basically have to fix a gauge. Is one, at least the most obvious way of dealing with it, although not probably the most pleasant way of dealing with it in the end. One could hope that somehow properly doing that would introduce this area term as well. I guess that's what you're trying to get at.
Yeah, but just the feeling that if you're extremizing something in a classical limit, feels natural to sort of let it fluctuate away from classicality.
Well, yeah. So there is a there is a understanding of this as coming from a saddle point approximation to a path integral, but actually, which is due to Lukowitz and Malosena. I'll talk about it later. But in that approach, actually, the gravitons are still more of an annoyance than something rather than something essential. Yeah, because So in that right, in that story, there is some there is a way of phrasing it where there's some integral over the surface and then you extremize and get this. Yeah, but you in some sense you have that even before you think about the gravitons.
Okay, so away from in the large end limit, apart from the S bulk, should we also be integrating over some fluctuations of the surface? I suppose. Should we be
no. Yeah, no. There's no. We don't think that there's like some brain action or something on the surface, right? Yeah, I mean, it's just. How shall I say? No, I mean, this formula is supposed to be like to all orders in perturbation theory, there's a particular surface that wins this computation, right? Because in the end, you will just want to get a number for the entropy. So you don't want it to be like if H bar is finite, now the entropy is the expectation value of something, right?
Okay, thank you.
Yeah. Okay. Okay, so problems with other questions? I'm happy to do more. I'm not in a big rush.
Yeah, I have a question. Like usually quantum corrections lead to log terms in the entropy. So why aren't such terms there here?
Yeah, that's so okay. I'm not actually sure. I think it's possible that the graviton loops do lead to logarithmic terms in this formula. It's something that a few people thought about, but I think nobody has come up with a systematic understanding of that yet. Yeah, but I'm certainly, I mean, it's certainly possible. Yeah, the set of people who understand the logarithmic corrections to entropy is kind of orthogonal to the set of people who understand this formula, but hopefully that'll change. I mean, I guess there are people of both kinds in India, right? So.
Okay.
Yeah. I mean, maybe I'll just make one comment, which is that usually those terms are like temperature independent, I guess. So, which somehow seem less important for page curve type calculations, but there's just some vague comment. I mean, it's still certainly important to sort that out. Any other questions? Okay, so we were talking about problems with trying to compute the page curve using the QES formula. So one was that big black holes don't evaporate. Another problem was that until recently, this formula, the quantum extremal surface formula, was just understood as describing perturbative corrections to the classical Ru-Takeyanagi or Hubei-Rangamani-Takeyanagi formula. So like in this formula here, right, we understood this term as being order 1/g, these corrections as being smaller, and then we understood this term as being order g to the 0. Okay. So then if this term is the dominant term and this term is small, then this quantum extremal surface should be close to some surface that just extremizes A, right? That's what you would expect, which we call a classical extremal surface. But there's just no classical extremal surface around in the page curve discussion that that would have the right properties to do what we want. And so then, naively you just say, okay, so why would including perturbative corrections help? And so, for example, like I was in the camp that thought this, although I didn't think about it that hard, apparently. So the first of these problems, right, you can solve it by coupling the dual CFT to a non-gravitational reservoir, and then that allows big black holes in the dual CFT to evaporate. And so that was one of the steps. That idea actually had occurred earlier to some guy whose name I don't remember, who was a student of Pachinski. He wrote a paper about it maybe 10 or 12 years ago, maybe 15 years ago now. But he didn't know about the quantum extremal surface formula, so it didn't help him very much. But then if you try to play this game of coupling the dual CFT to a non-gravitational reservoir, then there's a third problem, which is that, well, okay, so far this QES formula, right, it was proposed as giving von Neumann entropy of the CFT subregion, but then, okay, so are we allowed to use it for a non-holographic system like this reservoir that we coupled to? And if not, then how are we supposed to compute the page curve? Okay. And so these are kind of all the issues that had to be overcome. All right. So the great insight of these 2019 papers of Pennington, Almeri, Engelhardt, Merrill, and Maxfield, although this is not necessarily quite how they would have phrased it, is that the second of these arguments is wrong, right? That it's not actually true that a quantum extremal surface needs to be near a classical extremal surface. If you include the bulk entropy term in the QES formula, then actually it can give rise to new quantum extremal surfaces, which are far from any surface of extremal area. Jorge Roja, that's correct. Yes, thank you, 𝗰𝗵𝗶𝗶. Has put the name of the author in the chat. I apologize for not remembering it. I should have cited it. So let me just explain how this works. First, for the situation where you have, so now here, so this will take, we're going to spend a bunch of time on this, so I apologize, there's a bunch of text and a complicated picture. So here's how the new quantum extremal surface works in the situation where, so if you think about the dashed line and the red dot here, that's the microscopic description of what's going on. So I have a holographic CFT, which I'll call S, here it is sitting there, and it's coupled to a reservoir R, which has some time slice like this. And so the dimensionality of the reservoir is the same as the bulk description of the gravity theory. Okay. And then the idea is I have some black hole in here, which is since this dual CFT is coupled to the reservoir, then radiation that's produced, so the black hole horizon is over here, and radiation that's produced by the black hole can actually leak out into this reservoir system from the gravity point of view. So for example, this Hawking mode here, which is out in the radiation, it came from somewhere down here outside of the picture, and then it was entangled with some mode, which I squeezed over here so I could fit it into the picture, this one. And this one is in the interior of the black hole. Okay, so that's kind of Hawking's picture of the evaporation. It's the same picture I drew before, except now we're interpreting this line here as the kind of joining between the reservoir system and then the dual CFT, which is then dual, really they're both, the union of the two is dual to this picture of the gravity region over here. Okay. So let's think about the entropy. So to avoid this issue of how do we think about the entropy of the reservoir, let's first think about the entropy of the holographic CFT. Okay, so then we can just use straight up quantum extremal surface, no funny business. Okay. So let's think about what the quantum extremal surface is. Well, at early times, say right after we collapse we collapse some matter, it's just right over here to make the black hole, then the natural quantum extremal surface for the, if we take the whole CFT boundary is just the empty set, right? So the CFT boundary, let's say it's a sphere, right? So the empty set is homologous to it, of course, because I can just take this Cauchy slice here to be the homology hypersurface. And then the entanglement wedge of that quantum extremal surface is just this shaded red region here, meaning that the entanglement wedge of the CFT contains everything in the bulk, at least inside of these null boundaries here. And in particular, it contains this interior Hawking mode. Okay. And so as the evaporation proceeds, you get more and more of these interior Hawking modes. And so as a result, the quantum extremal surface formula via the bulk entropy contribution says that the entropy of the CFT is increasing, which is what you expect, right? Because it's interacting with the radiation. Maybe they started out not very entangled, but then because of the coupling between them, they're getting more and more entangled as the radiation from this CFT kind of goes out, propagates out in the bath system. So that's just the usual story, right? The quantum extremal surface is the empty set, so there's no area term, and you just get the bulk entropy here contributing in the QAS formula. But eventually that entropy becomes so big that you actually win by switching to a different quantum extremal surface. So this is the new quantum extremal surface over here, the one that's not near a classical extremal surface. And then the advantage of switching here is now so now there's a lot of modes out here in the radiation that are entangled with a lot of modes over here. And so if I had used this quantum extremal surface, then all these interior modes would give a big contribution to the bulk entropy term. But if I take this small one here instead, then the bulk entropy contribution to this is small because it no longer includes these modes here and these modes there. But then the price we pay is that now this surface has a finite area, right? And so that area comes with a over G, which is very big. So at early times, it's not worth it to pay the price to include this. But at late times, it's worth paying the price because even though that area is big, it's smaller than the entanglement of all these interior modes with the radiation. And in fact, that you get into that problem, right at the so-called page time, which is where you expect the page curve to turn over. And so once this situation takes over, then now that you have this new quantum extremal surface XS, and this XS, it's close to the black hole horizon, and so that gives you something that as the black hole evaporates, it decreases with time, and that gives you the page curve that's going down. And so that, I mean, that's really the essence of what happened here, was finding this this quantum extremal surface. I mean, people will say that there's lots of other things that were important, and I'll talk about the other things later. Okay, but this was the new ingredient, was finding this quantum extremal surface. Everything else just happened, within a few months, right? This was the thing that was the bottleneck for progress. And so, I mean, that's why I would say these papers are really the papers that push this. Everything else is, in some sense, follow-up. In particular, you notice here, I didn't say anything about, islands or replica wormholes or whatever, right? I mean, that's all important, but that's kind of secondary. Here, you can see everything without any of that. Okay, now I just want to comment, right? So what happened to this perturbative argument that it couldn't be near a classical extremal surface? Well, that it had to be near a classical extremal surface. Well, what happened, although you have to do the calculation to see it, is that you really balance the 1 over g in the area term. So if we look back at the quantum extremal surface formula, right? So to find an extremal surface, I compute the variation of these two terms. And naively, this term has a 1 over g and this term doesn't. So this term determines the location of the extremal surface. But actually, there's a short distance singularity in this bulk entropy. If you have an entropy of a region and you make the region small, then that creates a divergence. And then when you compute the variation, so in 1 + 1 dimensions, which is the relevant dimensionality for doing this, it's a logarithmic divergence. And so when you compute the variation, you get a 1 over r here, and you can balance that short distance singularity against the 1 over g, and that's how you find this quantum extremal surface that's far from a classical one. Okay, and so daring to do that was kind of the main new input of these papers, while daring to do it and then finding that indeed it works. Okay, so let me pause now again and ask for questions before I go on to talk about the entropy of the radiation. I don't know, maybe everyone's already an expert on all this.
Hi, Daniel, I had a question. So
yes.
So when the two terms balance each other, I mean, in the formula, you have the other quantum corrections, right, coming from quantum gravity, which, so when these two terms balance each other, is there a good argument why those subleading quantum corrections do not?
Right. So this bothered me a lot, right? So like, for example, there's the ... here. What about that, right? So, if we, yeah, exactly. I mean, and so that is why nobody did this sooner, right? Is because there was just this intuition that this is this should be understood perturbatively, and so then you're not allowed to balance the terms against each other, right? But what was appreciated was that although there are higher order quantum corrections, they all go into this ... and those corrections are all extensive. They're all the integral of something local on the quantum extremal surface, okay?
Mm-hmm.
So even though you include those, you can include all those if you want to, but they're not going to help you balance against the short distance singularity here, because none of those are going to produce this logarithmic divergence. So it's kind of a kinematic argument. The S bulk term is special. It's the only term that's able to produce a logarithmic divergence. And so I'm allowed to balance it against the leading term over here, even without worrying about the other terms. Does that make sense?
Yeah. But my question was that when it's minimized at the extremal point, I mean, even there, I mean, these wall terms do not matter. I mean, when these two terms are sort of it, yeah.
Well, so actually, yeah. So I mean, so this bulk term is important for finding the entropy, but it's actually not important for evaluating the generalized entropy. That's in the inverse dominated by the area term.
Okay, thanks. Yeah.
Sure.
Sorry, is this a dimension-dependent statement that this cancellation or this balancing happens?
No, it's actually not, because although what I said sounded two-dimensional, the information problem really is two-dimensional. You're kind of reducing everything to the sphere, on the sphere. So the two-dimensional scaling is always the right one.
Okay.
You know, because the black hole horizon is always just Rindler, right? Okay, anyone else?
Could there be quantum corrections to the the action term as well? The
S bulk?
Bulk action. S bulk, yeah.
I mean, in principle, yes. Somehow, you know, I mean, this is already a quantum thing, right? It's so the way this is usually understood is this is S bulk to all orders in perturbation theory. So somehow
But
by definition there aren't.
Summing over all loops.
Yes. Yeah. I mean, so let me be clear. Like, this is supposed to be. This is only perturbative in G Newton. It's not perturbative in, like, you know, the QCD scale or something else, right? Like, so there could be strongly interacting matter fields, and this is supposed to still be true. It's only important that gravity is weakly interacting.
So what is the form of S bulk usually?
Well, I don't. It's minus trace of rho log rho. Yeah.
And that is supposed to sum over all perturbative corrections.
Well, certainly, yeah. That's. I mean, yeah. Like the entropy of the vacuum for a region in a quantum field theory is certainly going to depend on whether it's interacting or free. I mean, it depends on many aspects of the theory.
No, rho log rho. I mean, trace rho log rho is.
Well, yeah, because rho will depend, right? Because the state rho will depend on the interactions, right? Like, for example, it could be the vacuum. We certainly think the vacuum in quantum field theory depends on the couplings.
So what is the form of rho?
Well, that's the form of. It's the state we're interested in, right? I mean, this formula is supposed to work for a broad family of CFT states. You know, it depends on. You know, it probably won't work for states which are so non-semi-classical that there's just some huge black hole that ate everything. But at least for ones where there's some geometry like this, it should be true. And then you just use the bulk state, which is dual to that. You know, including quantum fluctuations and so on.
Okay. Can I add something? Did you say the extremal surface changes because of the divergent terms from the S bulk?
Well, it's not the divergent terms. It's that this function is divergent if you make the region small. So it gets big. So it's not like a boundary counter term that we use. It's the part of the entropy which has a logarithm. So that's not something you can remove by adding boundary counter terms.
Okay, thanks.
Yeah.
Subramanya, you had a question?
Yeah. Hi. So I have a naive question. So this adding this extra non-gravitational reservoir, how should I think of it from the bulk point of view? Like, let's say some part of the ADS CFT dictionary, like the partition function in ADS is equal to the one in CFT. If I have to state something like that, then this.
So roughly speaking, I mean, you know, in detail, this has only been worked out in a few cases, but roughly speaking, what you would expect is that, you know, you have some low dimension single trace operators here, okay? And they're in the bulk, there's some weakly interacting matter fields. And so I can just take those matter fields to be simple without gravity and put them here, and then introduce some sort of single trace coupling here that talks to the boundary conditions of these matter fields. So you could try to do that like in the microscopic description, right? And then this is kind of what the dual of that should look like. You know, there might be a little bit of sort of energy density or something right around the gluing, which I would say needs to be understood better than it's understood now. But I think it's pretty plausible that this is what it'll look like.
Okay, thanks.
Mm-hmm. Okay, so maybe I'll go on. So that was the story for the page curve where you compute the entropy of the black hole. Okay, it goes up here because there are more and more of these modes in here in the entanglement wedge of S, so they contribute to the generalized entropy. But eventually, there's so many modes there that you need to switch to this quantum extremal surface, which now doesn't include the modes, but then you now have a big area term, and then that area curve term goes down as the black hole evaporates. Okay. Now, once we understand the rules for computing the page curve for the CFT S, then it's pretty easy to guess what the rule has to be for the reservoir. You just take the complement of everything I said here, right? So in this picture, the entanglement wedge of S was this, so then its causal complement is like this. So at early times, the entanglement wedge of the radiation is just the obvious thing. You just take this time slice of the radiation and take its domain of dependence. But then the novelty is that at late times, if you take the complement of this and the causal complement of this entanglement wedge on this Cauchy slice, then you end up with an entanglement wedge of the radiation that looks like this. And so now it has the obvious part, but it's also got this new island region in here, right? And you can kind of tell the same story as before. So over here, right, the entropy is going up because there are more and more of these Hawking modes getting in here. And eventually there are too many, and then you win by including their interior partners over here as part of the entanglement wedge, so that since now they're pure, they give a 0 contribution or a small contribution to the bulk entropy. But then you pay the price of now it's this surface that you included, you again have to include its area. And so that gives a page curve for the radiation that also goes up and down. Yeah, so this is what I said. So at early times, the reservoir has the obvious entanglement wedge, but at late times it includes this island. Now, it may seem strange, actually to me it doesn't, but to a lot of people it apparently seems strange to include part of the gravitational region in the entanglement wedge of the reservoir. So below I'm going to talk about some information theoretic understanding of the QES formula, where in terms of that it's basically obvious, because, but an argument I can already say is that in the end, there isn't really a sharp description between a holographic distinction between, holographic CFT and some other weakly interacting quantum field theory. Just one moment, if there's a question. And indeed, if you think about sort of tensor network models, which are one of the few tools we have to kind of understand these things from a Hamiltonian point of view, it's clear that there's no difference between these. From the point of view of the QES formula, if it's going to make any sense at all, you're going to have to include this island here. So I'll say some more soon about how to justify this, but some people say that in the original papers they weren't justified in including this, but I don't think this is right. I think they were quite justified, especially in Pennington's paper. He knew about some of these information theoretic examples, and it was obvious that from those examples that it was correct to include this. Okay, so that's the story for the entropy of the radiation. So that's it for my review of the page curve calculations. I'll just give people one more chance to ask questions. Then I'll go on to sort of talking about what it means. Okay, I guess we just had a bunch of questions. Maybe I see one. Is there a question? Karen Fernandez?
Yeah, Karen, go ahead.
Yeah, I have one. So maybe I missed this, but is there the coupling of the ADS with the reservoir? Are there some universal features about this, depending on the black hole spacetime in question that we're trying to emulate in this case? Is the coupling allowed to be generic, and does the page curve depend on the form of the coupling?
Well, you probably don't want it to be generic, because you want it to couple the weakly interacting fields in R to the low dimension operators in the dual CFT. So you probably don't want to just add some like huge crud that mixes all that up, right?
So then are there any constraints on the form of the coupling?
Well, there's the one I just said, I guess. Yeah, it should.
That's about it. It should not.
Yeah, but I think that's kind of probably. I would guess pretty much anything that just pick. Even just pick one single trace field, and just have a direct local coupling to the boundary values of one field out here. Okay, I feel like that would already work.
Okay, thank you.
Yeah. I should say that this, it would be nice to, in 1+1 dimensions, people understand this a little better. In higher dimensions, it's something that could stand to be understood better, I would say.
Okay, maybe a quick follow-up. There are these pictures about near ADS2 geometries around a black hole. Could this picture be fit into that in some sense? Has it been done so far?
Well, that's certain. Yeah, in the 1+1 dimensional models, it's all about that. Yeah, you have some ADS2 here, which is approximately JT. I didn't describe these calculations here, but there are equations that go with all this in 1+1 dimensions. You can really compute everything, and there's a formula for the page curve that you compute using this nearly ADS2.
technology.
Okay, thank you.
There's a question from Debajyoti.
Hi, yeah. So, Daniel, isn't there a way to see this information recovery by calculating like some bulk 2-point correlators, and that they show small, so if there is an information loss, it will decay exponentially, but otherwise at order S time scale, it will show some small fluctuations?
Yeah, so I mean, you can try to study that version of the information problem also. I chose not to talk about that today, but there are some things like that you can talk about, and they seem to work, right? There's this things about the spectral form factor and so on.
So with this island, is it possible to recover that behavior? Has this been done?
I'm not sure. It's that story is kind of okay. There's a word self-averaging that I won't really try to explain, but this page curve calculation has the convenient property that the von Neumann entropy is a pretty robust observable. This page curve is a pretty good thing to compute. These things have to do with tiny little fluctuations they're very theory dependent, that are of order E to minus S, and so to compute them in any robust way, there needs to be some kind of averaging or something that you do. Which complicates the story.
Averaging of what once again?
Well, that's kind of the issue. Averaging of what, right? For example, like you can try to average over the time where you compute the correlator. You can try to average over the theory, right? Which we can debate about to what extent that makes sense. But the story for the page curve is a lot more robust because it's a self-averaging quantity. It's not, this function that goes up and goes down. It doesn't depend on which compactification of string theory you're living in. Whereas the so-called spectral form factor would.
Mm-hmm. I guess I mentioned it because those small fluctuations should still be observable around this page time, I believe.
Well, yeah, page time. Yeah, I mean,
it's not a very late time.
That's a story for a black hole that doesn't evaporate, right? So the things are a little bit different. I mean, yeah, why don't we not get into that, because that's a whole different version of the information problem, and it comes with its own problems. And maybe in the discussion we can talk about that.
Absolutely. Thanks.
Yeah. It looks like there's one other question from Sundata, but then let's try to go on after that.
Yeah, so I was just wondering, the vacuum energy, for instance, the log p square plus m square integrated over p, that sort of term would give rise to a quartic divergence. Why aren't those sorts of terms considered here?
Well, I don't, yeah, maybe I don't. Let me try not to get into that in detail. I'll just say that this generalized entropy is something that's supposed to be finite in the continuum limit. So there are some divergences in G Newton associated to renormalization of the Planck mass. There are divergences in the entropy that are local terms, which are not the one I'm talking about, and those combine to give you a generalized entropy that is scheme independent. But there's a lot more that could be said about that, but let me leave it there. Okay, so all right, so that's it for the quantum extremal surface formula. But okay, great, woohoo, that's awesome. We can compute the page curve. Okay, but what do we really learn from it, right? Why is this formula true? What is it telling us about quantum gravity? So there are two approaches to thinking about the quantum extremal surface formula. I'll begin with the one which is based on Euclidean quantum gravity. So let's first remember what Euclidean gravity says about ordinary black hole entropy, right? So we can also use Euclidean gravity to compute just the entropy of the black hole, never mind these more complicated time-dependent things. And hopefully you all know the algorithm, right? You just you have this Euclidean Schwarzschild geometry. The thermal circle contracts somewhere in the bulk, and you evaluate the action to find the free energy, and then you differentiate to find the entropy. Okay, so this is what Gibbons and Hawking taught us back in the 70s. More recently, in 2013, this idea was generalized to explain how at least the first two terms, up through order g to the 0 in the QS formula, can be derived from Euclidean gravity. And the idea is almost the same as what happened here. It's just that you have to deal with the fact that you no longer have a time translation symmetry here. And so you have to use this replica method to compute the entropy. So the idea is you take the state whose entropy you want to compute, you take n copy, raise it to the nth power and take the trace. to give this twisted partition function. So here's some graphical representation of that for n equals 3. And then you analytically continue in n, which you just sort of boldly do, hoping not to get in trouble. And then you take this derivative to find the von Neumann entropy. And so Lukowitz and Maldacena, so this is a sort of boundary prescription for computing the entropy. And then Lukowitz and Maldacena explained how if you kind of fill in these boundary conditions by solving the bulk equations of motion, then what you end up with is the QES formula. It's really, I should say it's not just Lukowitz Maldacena. That was the first, that had the idea, but then to get the quantum correction, there's further work by various authors, Faulkner, Dong, Rangamani. So I should have added more references. It was late last night and I didn't put them all. I apologize. In particular, you can so these Euclidean saddles are qualitatively similar to the Schwarzschild solution. There's some quasi-thermal circle. It contracts, and then you take advantage of the fact that it contracts to find an entropy which is of order 1/g, yeah, it gives you the QES formula. And in particular, you can take this idea and you can apply it to the reservoir of an evaporating black hole, and this confirms that indeed you should have included the island that we had before. Okay, so it's just this Lukowitz-Maldacena idea. You take the Euclidean gravity path integral, and in fact, at the time when Lukowitz and Maldacena wrote the paper, most of us just interpreted this as deriving the RT formula, but their paper was not called derivation of the RT formula, right? It was called generalized gravitational entropy. And they wrote the paper in a way that seemed very annoying to many of us at the time, because they didn't talk about ADS-CFT until the end, right? But actually, their whole point was that this doesn't really rely on details of ADS-CFT. Sort of anytime you have a Euclidean gravity description of what's going on, then this works. And so in particular, like in this case where you have the reservoir coupled to a holographic CFT, the argument goes through just as before. And tells you that indeed you should have included the island. And so that was discussed in these papers a few months after the first papers, after the breakthrough papers. Now, opinions vary, I would say, on how satisfied we should be with this justification of the QES formula based on Euclidean gravity. There's clearly something to it, right? There's some internal coherence that gives you the right answer. But on the other hand, it leaves a lot to the imagination. The basic problem with using Euclidean gravity to compute entropies is that the entropies that you compute are not manifestly equal to the minus trace of rho log rho in some Hilbert space and for some appropriate choice of rho, right? Like if we look at this, the Gibbons-Hawking saddle, right? This is the thermal circle, but then the thermal circle contracts to 0 size, right? But if it contracts, you see that destroys the interpretation of the thermal circle as a trace, right? Does this look like a trace to you? I don't know. To me, it definitely does not look like a trace, And this bothered me for years. It seems there's two kinds of people. There are people who are bothered by this and not bothered by this. People who aren't. I've had trouble convincing the people who aren't bothered by it to be bothered by it, but I'm definitely one of the people who is bothered by it. Okay, it's not a trace. At least it doesn't look like it. But then if it's not a trace, or at least it's not obviously traced, then why should we believe this answer? Okay. And to say it in a different way, why should low energy effective field theory know the number of microstates in a black hole? Okay. And I can say this just one moment, Sundara. I mean, I could say this more provocatively, right? Like we think that one of the great successes of string theory is that it's able to count black hole microstates. Okay. But should we take away its credit because Euclidean gravity already knows the answer, right? Who needs string theory, right? We just do Euclidean gravity. It tells us the entropy of a black hole, right? I mean, clearly there's something that string theory did that Euclidean gravity didn't do, right? And I would say what string theory did is it computed the entropy using the formula minus trace of rho log rho, okay? And so to me, that's what it really means to understand an entropy, is to compute it using its definition and not using some other sort of oracle that seems to give the right answer for reasons that we don't necessarily understand, right? I mean, that's why we thought Strominger and Waffe was progress, after Gibbons and Hawking. Okay, Sundara has another question, or no? Okay, the hand is down. Okay, well, maybe I should try to continue because I don't want to go too far over the time. We'll have a discussion at the end. Okay, so this issue of what exactly does Euclidean gravity mean, right? I think it's very clearly illustrated in 1+1 dimensions, right? So for example, like Jakiv-Teitelbaum gravity is a renormalizable theory of gravity. Here's what it looks like, and actually there are two different ways that you can try to quantize this theory. So the first approach is the sort of textbook one. You just, say study it with two asymptotic boundaries and do canonical quantization, right? So there's a phase space of this theory. It's classical phase space. It's two-dimensional if there are two asymptotic boundaries. And if you quantize this phase space, then you get the quantum mechanics of the particle scattering off an exponential potential. So this was explained by Dan Jaffers and myself back in 2018. So it's very simple, no funny business. On the other hand, you can just say, okay, well, that particle quantum mechanics is boring. Let's try to do something else instead. So let's try to do the Euclidean gravity path integral. So we don't know what it means, right, in terms of a Hilbert space, because we're allowing circles to contract and so on. But let's just do it and see what we get. Okay, so that was the approach of Sod, Schenker, and Stanford. And indeed, right, what you get is that it's not quantum mechanics, right, which is not too surprising. If you take something that's not manifestly quantum mechanics, why should it be quantum mechanics? Okay, in this case, it's actually not. It's some average over quantum systems, basically matrix quantum systems. And so then there's been a lot of follow-up on this over the last few years. And then, so there's this question, okay, like, which of these quantizations is correct, right? I put quantizations in quotes because this one isn't even quantum mechanics, but we'll be charitable to Sod, Schenker, and Stanford and call it quantization. But which of these is correct? So in some sense, both, in some sense, neither, right? So, both of these are self-consistent mathematical things that you can do. There's nothing wrong with either of these from a mathematical point of view. But on the other hand, neither of these is a quantum theory where S equals A over 4G, right? And my goal for understanding the quantum mechanics of black holes is to have a quantum mechanical description of the situation where S, which is computed using minus trace of rho log rho, is equal to A over 4G. And so somehow this Euclidean approach kind of doesn't really get there. And then here the canonical approach doesn't either, because in the canonical approach, okay, at least you get something that's quantum mechanics, but it's something that doesn't have any black hole microstates. And so that's kind of boring. The black holes don't really have entropy in this theory. It's kind of, okay. Okay, so that was it for my comments about Euclidean gravity. Let me just see briefly if there are any short questions. If there are big philosophical questions, maybe let's do them at the end. Okay,
maybe I can ask a short question.
Yeah, sure, Sunil.
So you seem to have a critique of Euclidean gravity based on the fact that asymptotically there's a Euclidean time circle, but in presence of a black hole, it's a contractible cycle. So does that, in your view, prevent us calculating essentially anything in Euclidean gravity, or is it a specific?
No. So yeah, let me be clear about that. So it's not that I don't like the answers from Euclidean gravity. I think they're actually correct. I just think it's a mystery in some sense why they're correct. It's not something that we understand from the bulk point of view. Because Euclidean gravity is this magic box that lets us know the entropy of a black hole without having to know anything about strings or brains, right? And it's very useful to have a magic box, right? And every time it gives the right answer. So I don't think there's any doubt that it's right, okay? I'm just not satisfied with our current understanding of it.
Okay.
I wrote a paper recently with Edgar Shigulian that I don't have time to get into, where we argued that in some sense, assuming that Euclidean gravity is correct is the same as assuming that the theory emerges from a holographic description. And I think that's really the right idea, is that in any theory that's holographic, Euclidean gravity is correct. But for example, this canonical quantization of JT is not holographic, and so Euclidean gravity is not correct. But that's fine. Yeah, this theory has other weird features, like it's allowed to have global symmetries, right? Like that's what we were talking about in the paper. So theories that aren't holographic don't need to have many of the properties we think quantum gravity should have.
Thanks.
I have a naive question.
Yeah.
The circle in front of the cigar, that's supposed to be the boundary of the horizon, right? Is it supposed to
No,
be
this is at asymptotic infinity. So the horizon is the tip of the cigar. Yeah. In Euclidean short cell geometry over here, that's asymptotic infinity. So this is the asymptotic thermal circle, which is what you want, right? The circle that's the temperature that's dual to the ADM Hamiltonian.
Yeah. So this thermal circle, if you consider it from the boundary point of view, from the field theory point of view, there is no problem, right?
Yeah, but then you're assuming holography, right? Yeah, exactly. So in a holographic theory, this is the thermal circle, and then it's fine, right? Then you don't care that it contracts. I mean, that's kind of the part of this argument that holography is the real reason why Euclidean gravity is correct. I just emphasize it because people seem to think that Euclidean gravity is a sort of completely satisfactory explanation by itself, and this I don't agree with. But I'm happy to use it as a tool for understanding holographic theories.
So the bulk computation is just the computing the thing over the surface area of the cigar, right?
Well, it's you just compute the action of this geometry. Yeah.
Yeah. So
and then that gives you minus the log of the partition function.
Yeah. So what is the problem with that? Why is it pathological?
Well, because it's not a trace, right? I mean, my understanding of Euclidean path integral is that you derive it from the canonical formulation by, starting with the trace of e to the minus beta h and inserting complete sets of states. And if you follow that rule, you're never going to get a thermal circle that contracts. So this is not doing that, right? Like, and it can't be because it's counting the microstates without knowing what they are. It's amazing, right? Like, when Strominger and Vafa or Ashok or somebody is counting black hole microstates, they're definitely, in string theory, they're definitely not doing this. They have to know the details of string theory for each example they consider.
I thought the trace of the e to the minus beta h was relevant for the field theory, and for the dual gravity theory, it was something else. It was just an action.
I mean, no, we want to compute. That's what we want to compute is the microstates from the gravity point of view. But I think we should go on.
I think we should go on. And Daniel, roughly how far are you away from the conclusion?
I have 23 slides, and right now I'm on slide.
Just go on then. Yeah.
Yeah. Okay, so I'll try to speed up a little bit. The last part is some new stuff, which probably will be hard to understand in detail anyway. So I'll just try to give a flavor of it. So I would say to really understand the QES formula, and thus the page curve, we would like to compute the entropy of the microscopic theory using the real definition of entropy, not using any funny business. Okay. On the other hand, this is hard to do, right? Because then we have to have a non-perturbative description of black hole microstates, right? And so for the non-supersymmetric black holes, which are relevant for the page curve, I mean, we only know how to do this in toy models that, frankly, I mean, I'm one of the authors on these, but they're rather crude. I mean, things like tensor networks, things that throw out a lot of the structure of the bulk that we like, the Einstein action and things like this, right? So one approach, which is sort of in between, which has been helpful for me at least, is that it's possible to reinterpret this quantum extremal surface formula as a feature of, as a really general feature of something called quantum error correcting codes, which gives a rather general way of understanding how bulk quantum information is encoded into the boundary theory in ADS-CFT. So, so in particular, so here's some result back from 2016. So I showed that pretty much any quantum error correcting code obeys a version of the RT formula. I should have written the QES formula here. So here's just a sketch of how it works. So here's a time slice of ADS. I have some boundary subregion capital R. I have its complement capital R bar. And then in the bulk, there's an entanglement wedge of big R called little r, an entanglement wedge of big R bar called little r bar. And then there's this quantum extremal surface sitting in between them. Okay, so this is the bulk picture of what's going on. And so then what I showed in this paper is that for any isometry which maps the Hilbert space of the bulk degrees of freedom in this picture into the microscopic CFT Hilbert space of capital R and capital R bar. So what I showed is that if it has the property that the observables in the entanglement wedge of R are accessible from big R, and the observables in R bar are accessible from big R bar, which is some feature of ADS-CFT that you can justify in many cases by using, solving bulk equations of motion and so on. Then this encoding map, or this encoding isometry that maps the bulk Hilbert space into the boundaries Hilbert space has to have this structure that I show on the right. So you take the bulk input in little r, you take the bulk input in big R, you throw in some entangled state between big, and then you hit half of the entangled, you mix half of the entangled state together with little r using some unitary to give you the state here. And then you mix little r bar together with the other half of the entangled state to give you the state here. So this is some theorem. I'm not telling you how to prove the theorem, it's just true. Okay, and so in other words, ADS-CFT is a code that looks like this. This is just how the bulk quantum information gets mapped into the boundary. But you see, as soon as you have this picture on the right, it's clear there's going to be a QES formula. It's essentially obvious, right? Like I take some state rho. This should be a little r bar here. Yeah, it was getting late last night, so sorry, the typos are increasing. This should be little r and little r bar. So I take some bulk state living on this slice here. I conjugate it by this map to push it into a boundary state, rho tilde. And then if in the boundary theory, I compute using the definition of entropy, the entropy of the state rho tilde on this subregion R. Over here, you see immediately what you're going to get. So if I compute an entropy here, the unitary is irrelevant. Okay. So if I compute an entropy here, I just get the sum of the entropy from half of this state chi, and I get the entropy from the bulk degrees of freedom in little r. Okay, that's what I wrote here. But you see, if we define this area to just be this entanglement from chi, then you see this is exactly the QES formula. Okay. Okay, I could say a lot more about that. You could say, is this really the QES formula? Yes, it really is. You can study it in many examples, and this is really the QES formula. So now we'd like to understand this, we'd like to apply this understanding to an evaporating black hole. So that would give us a kind of Hilbert space understanding of this page curve calculation. So here's, sorry, did someone say something?
On the last slide.
The previous slide? Yeah.
So why is that now, it seems to me that the answer depends on the choice of chi, but at the bulk, the RT surface was featureless, right?
Chi is part of the map, right? So chi is not chi is part of the map that tells you how to turn this state of the bulk to the state of the boundary. So yes, that's part of the theory, if you like. So yes, it definitely depends on that.
Bulk, where do I see that freedom? I'm confused.
Well, it's not a freedom. The idea is if you pick a specific example, like n=4 super-Yang-Mills, that will come with a particular UR bar, and chi. Okay. But to figure out what those are, I have to be very, very good at studying n=4 on the lattice or something. This theorem just tells you that they have to exist. Okay. So here's a bulk picture for the evaporating black hole. So I'll just kind of a caricature. So we have left moving modes in the interior, we have right moving modes in the interior, and then we have the radiation out here. And so that's the bulk degrees of freedom on this Cauchy slice. Then I want to have some encoding map V that takes these degrees of freedom and maps them into this dual picture where I have the dual CFT S sitting here, and then I have the reservoir R sitting there. Okay. So this is what I said, left movers, right movers in the reservoir. Just to pad things out, I'll allow for some extra bulk degrees of freedom O that I keep fixed. Like that could be, say, the fields right here, or some fields in between, or something like that. Okay. But for this to work, when the black hole is old, there's an immediate problem, which is that when the black hole is old, these interior modes, little r over here, and the Hawking radiation, big R over here, are very entangled. And so if you want to have an isometry so you see big R is the same on both sides, but you see if little r, if the entanglement is very large, then the dimensionality of this little r needs to be large compared to the dimensionality of the black hole Hilbert space, which is this S. But then if that's true, there's no way this map V can be an isometry, right? Because isometries can only increase the dimensionality of the Hilbert space, right? But see, R cancels in the dimensionalities on both sides of this, and then little r is here and S is here. So if the dimensionality of little r is already big compared to S, no way this V is going to be an isometry. So the traditional response to this is you say, well, okay, you're taking Hawking's picture of the bulk too seriously. At late times, the radiation isn't really entangled with the black hole, you dummy, stop trying to do this. Okay, that would be, maybe that's what I would have said to myself, 4 years ago or something. But what we learned from the island calculation actually is that we should take Hawking's picture of the bulk where the radiation and interior mode are entangled. We should take it at least a little bit seriously at late times, right? Because we use it to find the island. And actually this sort of wrong entanglement between the radiation and interior mode is crucial for the island calculation to work, right? Like if we didn't have it, then we wouldn't justify including the island, all right? So just in the last few minutes, I'll sketch, and it's only a few slides, I promise, some model that we've recently introduced, which, so this is a real problem. So avoid maybe is the wrong word, that somehow suggests a resolution of this problem, which gives up the requirement that the map from the bulk to the boundary is an isometry. Okay. So that sounds scandalous, right? Like, how can the map from the bulk to the boundary not be an isometry? That's nuts. But actually, in the model, you see that the failure of V to be an isometry can only be seen by measuring very complicated observables. And in this model, actually, it has enough structure to show that this island rule, applied to the wrong state, the one Hawking suggested, that applying the island rule there is actually computes the entropy, which actually is the entropy that you get out of the microscopic computation just by using trace over log rho. So I'll just kind of zip through this. So just to kind of show you, this, maybe if you just remember a sentence or two from this. So here's what the model looks like. So we have our left and right movers in the black hole. We have some fixed state for these extra, just to pad the Hilbert space dimension. We have the identity map on the radiation, the reservoir, because that's not part of the system. We have some random unitary. And then here's the crazy part. We throw in a final state projection onto some potentially large subsystem, which allows this U to have a dimensionality which is much larger than just the dimensionality of S. Okay. So, that maybe that sounds crazy. I'll try to reassure you in a minute, but okay, that's the model. We just have this post-selection at the end. So in this model, then, when we have an evaporating black hole, okay, so here's what the state of the system would look like, right? So we have some entanglement here between the interior outgoing modes and the radiation. This is the Hawking entanglement. I just put it in some state chi2. Then just to keep track of how I made the black hole, I throw in a reference system L that I entangle with the left movers, just so that I can keep track of the microstates of the black hole, how it was made all in one go in one state. And then I just pass this state on this time slice down here through this map to give me a state which now lives in the Hilbert space of the reference system for how the black hole was made, the dual CFT, or the black hole microstate degrees of freedom, and the reservoir, which is what I want, right? The microscopic description is supposed to live here. And then the nice thing about this model, you can compute everything. There's nowhere anything can hide. You can figure out what's going on. And so I'll just tell you a few results without giving the derivations, and then we'll be done. So calculations in the model are done by using tools from integrating over random unitary operators. Okay, so if you know that, you know it. If you don't, you don't, but you should learn it. So here are some facts, right? So if I pick two states in the bulk description, and then I take various dimensionalities to be large, then even though V is not an isometry, if I look at the inner product between psi1 and psi2, and then what happens to it after I hit it with V, it's actually very close to being an isometry, okay? When I average over the unitary, because it gives me something that's suppressed like the dimensionality of the final black hole Hilbert space dimension, okay? So if you try to interpret what this says about a fixed generic U, which is what I really want, I don't really want to have an average. I want to pick a fixed U, but just have it be generic. Then what this says is that the map V behaves like an isometry on simple states. Okay, it can't really be an isometry. There are a bunch of states which it annihilates, but it's very hard to find those states. Okay, the states that you get by starting with the Hawking state and acting with a few operators for those states, it will behave like an isometry. And so in particular, simple observables on the radiation will tell you that the radiation is mixed, just as Hawking would have predicted. Okay, but on the other hand, you can compute here it's easier to do the Renyi entropy rather than the von Neumann entropy. You can compute the second Renyi entropy of the radiation. And so here I emphasize you're computing it using the definition, not using the quantum extremal surface formula. And it gives you some page curve that looks like this. So you have a minimum between two things. There's this chi R2, right? That was this entropy of the radiation in the bulk picture. Okay, and so that is one of the options, but then there's another option which starts out big because it has this logarithm of the dimensionality of the black hole Hilbert space. But eventually, if you make the radiation big enough, then actually this term wins, and that's the page curve of the model. And in fact, and I'll just say this, I have one more slide, which I won't explain much. This page curve actually, now the key point is that this also follows by, instead of taking the output of this map and using the definition of the entropy of R, you can also instead apply the quantum extremal surface formula down here in the bulk picture, including this wrong entanglement, and you actually get the same answer. Okay, and that's the main result of this model. And so, okay, sorry, I don't have time to explain the details. I'm running over, but so let me just have one slide to comment on the calculation. So a key ingredient is that my 2016 results were recently generalized just a few months ago by Akers and Pennington. And my version of the QES formula, so in that version, I only gave a prescription of the area of the true QES, not for other surfaces, but to compare to the island story, it's useful to have a more general result that tells you what the area should be also for non-minimal extremal surfaces, because you want to have this story of you have the island or not, and they compete and you see who wins. Okay. And so you need to define the area of the wrong quantum extremal surface. Okay, and so Akers and Pennington give a very nice idea for how to define that. And so in the code we've been discussing, I'll just tell you the answer. This is what their area looks like for the island, where I define the island to be both the union of the left and right movers inside the black hole. Okay, so this is what the area looks like. And then once you have the area, it's easy to plug it into the island, into the quantum extremal surface formula, see what you get, and what you get is exactly this page curve that we computed here from the microscopic description. Okay, so that's all I was going to say. I'll close with just some comments on some open issues, some we're thinking about, some for the future. So what's the relationship of this model to the final state projection of Horwitz and Molesena? It seems to be different, but on the other hand, they both involve a final state projection, so we need to understand that better. How do we think about when the black hole is old, reconstructing the interior operators on the radiation? Is there a connection to the null states of Meroff and Maxfield, who also, for some reason, like to say there are a bunch of states that are annihilated by some quantum gravity map? And of course, we'd like to have a more realistic version of this model. I mean, a random unitary. I mean, come on, right? On the other hand, there's going to be a limit to how well we can do, because we're really keeping track of the non-perturbative quantum gravity description degrees of freedom here. So, doing this for some realistic string compactification seems like a long shot at the moment. And indeed, right, so, at what point are we actually going to need to know about string theory, right? I mean, we didn't use it much in this talk, although we certainly use holography, which I would say is a consequence of string theory in some sense, but shouldn't we have to know it more explicitly? I think we will sooner or later, maybe sooner. All right, that's it. Thank you. Sorry for going over.
Thank you very much, Daniel. A beautiful survey of this field and your work. So yeah, given that it's very late, we should still have a few questions, I guess. Somnath, can you wait a bit and let other people also ask their questions? Then we'll come back to you. Is there anyone else who has a question? Arnab Kundu has a question. Go ahead and ask it. Arnab?
Hi, sorry, I typed in the question, but I can very quickly ask. So I was curious. Sorry, ignore if you hear any noise, background noise from my end. But I was just curious about the statement that you made, regarding that Euclidean gravity is meaningful when you have holography. I was just curious. Does that statement make any assumption about the asymptotics of the geometry where you want to have a holographic picture? Or
well, I certainly understand it the best when it's asymptotically ADS. Okay, that's where I would say most of the evidence for this claim comes. Because I don't know what holography in flat space is, right? I mean, if you I somehow think that in this Euclidean picture you have this thermal circle that's going off to infinity. I mean, that makes sense also in flat space, and so I guess I would hope that in the holographic dual to flat space that becomes some thermal circle in the dual description, the BFSS model or something like that, some fancier version of that. But yeah, I'm not sure I can justify it in general, but in ADS I think we had some pretty solid arguments, which are relating it to modular invariance and the dual CFT and so on. And yeah, I recommend looking at those. And basically we argued that Euclidean gravity is sort of the minimal thing you can do in the bulk theory to make it consistent with modular invariance. Because why should it not? If in the boundary point of view the spatial and the thermal circle are the same, then probably we should. If we allow, certainly we allow the spatial one to contract in the bulk, that's fine. But then probably we better allow the time one to contract too.
But you would agree that, I mean, even if I take it literally, that even in flat space, or even let's say in de Sitter, I mean, in some sense, Euclidean gravity throws in answers that that are hard to ignore. You might even, I mean, you might even take that literally, right?
I'm not saying they're wrong, right? It's just that saying that I don't understand something is different from saying that it's wrong, right?
No, I was not trying to say that you were saying it wrong. I was just trying to understand the statement better that you were making.
I mean, there are theories of quantum gravity in flat space where you shouldn't use Euclidean gravity, like the CGHS model, right? That's another one of these renormalizable theories. You can just do canonical quantization, right? But,
okay. Thanks a lot.
Chethan, go ahead. You're muted.
Yeah. So I just this last part was a little too quick for me. I probably should read the paper, but
which is not out yet.
Okay, I see. So so the general idea is that final state projection together with an explicit trace rho log rho can reproduce the quantum extremal surface calculation. Is that the idea? Is that the?
That's correct. Yes. Okay. Yeah. I mean, and of course we without the final state projection, you know, in more conventional settings, like where you have a subregion of ADS and you're near the vacuum and so on, then this works without the post selection, right? That was the story from 2016.
Yeah.
Here, right? You see here, there's no post selection, right? But the new ingredient is if you try to make the bulk Hilbert space too big, then this picture runs into trouble, you know. But somehow the and the black hole wants you to make it too big, but somehow even in this situation, the quantum extremal surface calculation is still correct.
Thanks.
Okay, thanks. Okay, Somdat, I think you can be the last to have the last word, and then we will end.
So in the page curve, does it mean that the state starts off as a pure state and ends off as a pure state?
Well, yeah, that's naively what you would expect, right? Like if you don't have to make a black hole in a pure state, right? But theoretically, at least, the simplest thing to do is to make it in a pure state. I mean, of course, the astrophysicists would laugh at us for saying that, but you know, we could collapse.
And in the end,
yeah, go ahead.
And in the middle, it's a mixed state.
Yeah, the radiation in the middle is a mixed state. Yeah, so I mean that's what this page curve says, right? I mean, and this is not at all surprising. I mean, if you have a piece of coal that's in a pure quantum state and you burn it, right? Like this is also what the entropy of the radiation looks like, right? Where radiation now includes the ash. What I'm concerned is
how can a mixed state evolve to a pure state? Because
because you're looking at a subsystem. No, because you're only looking at part of the system, right? Like so it's the same when you burn the coal. While the coal is burning, some of the coal is still there, and so if you look at the radiation, it's entangled with the coal that's still burning. It's just that once it's done burning, then it has to be pure.
Okay, I think then it may be a good time to close this. If there are no more pressing questions, then on behalf of everyone, let me thank Daniel as well as all the previous speakers of this session. Well, see you all tomorrow. Thank you so much for coming. Thanks for your talk.
Thanks, everyone. Bye-bye.
Bye. Alok, all good?
Yes. Yeah, absolutely. More or less. Yeah. All right.
It's quite late. So I guess we see everyone tomorrow, right?
Yes, absolutely. Thanks a lot. Thank you so much, Sunil, for
Bye.
doing this. Thank you. And thank you. Thanks to all the speakers. Thank you.